I should correct a minor impression. I'm not doctor. I don't have an earned doctorate. All right, well, let's talk about magic cubes and hypercubes. Okay, this is a multi-level talk in that it's got all kinds of levels in it. And I hope there will be something for everyone, and there will be things which you find either too hard or ridiculously easy. First off, here's what a magic square is. You arrange the numbers from 1 up to n squared, in this case 1 to 9, and all the rows and columns and diagonals have to add up to the same thing. That's sometimes called the magic constant. And I'm going to flip through some of these faster than you're able to do the arithmetic checking, so you'll just have to trust me on this one. Okay, wait, we lost? No, there we are. Okay. We're talking about magic squares and generalizations into cubes and hypercubes. These are some of my variables. I use the size, the length of the side in one of these things. I'm calling S. So for that last square you saw, S is 3. And the dimension of our object, I'm calling D. And for the square I just showed you, D is 2 for two-dimensional. You place the numbers from 1 up to S to the dth power in the cells. And all the lines, the orthogonals, diagonals, and so on, have to add up to the magic constant. There's a simple formula for the magic constant, which is K is equal to this product. And what that means is it's the number of things in a row, which is, of course, S, multiplied by the average value, which is, of course, the average of the first and last term for the arithmetic sequence. And I'm excluding some special cases to avoid making all the theorems complicated. I'm always assuming the length of the side is at least 3 and the dimension is at least 2. There are a lot of different definitions for magic cubes, since it turns out to be a little bit difficult to make them. And so people made partial ones, and they had a bunch of different definitions depending on what ideal property was omitted or what they were substituting instead. The terminology shows signs of becoming standardized, but it's always a good idea to say exactly what kind of magic cube you're talking about. Okay, the critical thing is, what is it you expect to add up to the magic constant? And that in turn is, what are the lines you're allowing? Of course, you have to have all the orthogonal lines. Those are the normal things that are horizontal, vertical, everything's at a right angle. You want your diagonals to add up, and I want all the diagonals that are length S to add up. And sometimes you'll find a definition of a magic cube in which only the diagonals that are on the outside faces line up, for example. I want all the diagonals to line up, and then I want what I call triagonals to line up. Those are diagonals that are not simply, they avoid being parallel to various things, like we could go from one corner to another of a cube. Every line has to have S cells, and it has to be an actual geometric line, rather than something that is bent, broken, wrapped around into pieces, bouncing off an edge, whatever. People have defined magic squares with all these different properties. We're ignoring all that. We say nothing about whether those add up or not. The number of lines has an interesting formula. If you imagine your cube or hypercube or whatever to have a wrapper around it that's one cell wide going all the way around, so that the total thickness now becomes S plus 2. Then the number of lines is the volume of that wrapper. It's the dth power of S plus 2 minus the internal thing being wrapped, which is the dth power of S, and that's all divided by 2. And it turns out there's a very cute proof of that, where you look at any line going through the inner cube or hypercube, and it projects out into exactly 2 cells in the wrapper. And those 2 cells all match up, 2 cells for every single line and vice versa. There's no duplication or overlap, and that gives you the line count with this exact formula. Okay, so these are my magic cubes. Now, sometimes these are called perfect, but the word perfect has been used to mean other things as well. So I'm just going to say that's what I'm talking about today. One property of those is that every included hypercube of a lower dimension, I'm calling it a subhypercube here, within a magic S to the D hypercube is also magic. And that includes orthogonal and first level diagonal. The slices in the hypercube are obviously magic. You can also place a diagonal subhypercube in any hypercube. And that's what I'm calling first level diagonals. And then, of course, by induction, if you go to smaller and smaller dimensions, everything still remains magic. And you can get into more things that are more diagonal at the lower dimensions. Now, it happens that the sizes for which cubes exist are closed under multiplication. So, for example, if you have in front of you a magic cube of side 5 and a second magic cube of side 6, which both of these were discovered about 10 years ago, then you can automatically create a cube of size 25 or 30 or any other product of 5 and 6. Similarly, if you have a magic tesseract of side 17, then you can take any power of 17 and create a magic tesseract of that size. It's all an automatic, simple procedure. Okay, our lines, the cells of the cube contain the individual numbers. Each of them will have D coordinates corresponding to the D dimensions. So our cubes will have X, Y, and Z coordinates. The values of the coordinates range from 1 to S. It's the length of the side. Lines are some collection of cells that are in a line. And so they will have coordinates of the form A, B, C, D with some X's spaced in. The X's are the changing values, and the early letters of the alphabet are constant values. So those, like A might be 2 here, and B might be 3. And then X would run from 1 through S for the different cells on the line. Because the diagonals can go both up and down, some of the X's might be increasing while others decrease. But they always increase or decrease together. So at the end of the line, all those X's are going to have values of either 1 or S, or some mixture of 1s and S's. Okay, names. If you have only one X in that pattern, that's an orthogonal line. If you have 2 X's, it makes a diagonal line. 3 X's make a triagonal, and so on. Next, I'm going to talk about what I call linear combination proofs. And we're going to do 2 very simple examples to get the idea across. The first simple example is that the center cell of a magic 3 by 3 is 1/3 of the magic constant. So in that 3 by 3 magic square we looked at earlier, the magic constant was 15. The center cell was obligated to be 5. That's one of the theorems. And then the second theorem is that the sum of the corners of a 4 by 4 square is also the magic constant. So that's definitely not a line, but it's another pattern that has to add up to the magic constant. Now, these things follow simply from the statement that all the equations add up to the same value. And you don't necessarily even have to use all the numbers from 1 to n. You could stick in complex numbers, for example, and these theorems would still be true. Often people like to make magic squares out of things like primes and so on, which of course are not consecutive numbers. Or maybe they'll say this is all the square entries. When squared, it's still a magic square. These still follow these properties because the properties depend only on the addition. Let's see. Okay, that came out pretty well. I've drawn in a 3 by 3 square there. And I've drawn in 4 of the lines for that 3 by 3 square. That's that star pattern. It's got a horizontal line, a vertical line, 2 diagonal lines, and they all cross in the middle. Now we can imagine adding up all those lines. So that's 12 numbers total. And there's some repetition in the center, obviously, because it's got 4 lines going through it. So it gets counted 4 times. We can then subtract off the second pattern, which has the 3 horizontal lines in it. That has the effect of removing, canceling out most of the cells in the magic square, because they were only covered once in the first pattern. But there are 3 copies of the center cell left, and that's the meaning of that third square. It says the center cell is weighted 3 times, everything else is ignored. And this is a visual proof that 4 times the magic constant minus 3 times the magic constant is 1 times the magic constant k, and 3 times the center cell is equal to that k. So that's what I mean by a linear combination proof. We put a bunch of lines in, we subtract some others, maybe we add some more back, and we wind up with a pattern like this. Here's a similar one for a 4x4 square. We bring in 6 lines, which is all the lines around the edges, and we pick up all the internal cells that are not edge cells by drawing that cross in the middle. Now the intersection there is not actually in a cell, because the 4x4 doesn't have a middle cell. But those diagonal lines cover the 2x2 square in the middle. And again, we subtract the 1 copy of the entire square with the 4 horizontal lines. And what that leaves us is with all the stuff that was double counted, actually triple counted in the first pattern. We now have 2 copies of all the corners added up, and we had 6 lines in the first bunch. We're taking away 4, that leaves 2. So that tells us that twice the sum of the corners is equal to 2k. And from that we get the theorem that the sum of the corners is the same as the magic constant. Here's just an example of something you can do in a 5x5 square. It tells you that all those cells that are knights move from the center. If you add up those 8 cells and then subtract 3 times the center, you get the magic constant. I like to make my magic constant 0. So I subtract the appropriate value from every cell. The reason I like 0 is because it simplifies some of the equations. I don't have to count my k's. For an odd size square, I subtract off the average value of a cell, which is the sum of 1 and s to the d power divided by 2. And that just makes the range is now a symmetric set ranging from minus s to the d minus 1 over 2 to the same positive value. So I've just offset the range for the numbers there. Now for even s, that unfortunately makes everything end in a half. So for an even one, I'll multiply all the numbers by 2, so I get whole numbers. And I'll say, okay, I've got all the odd whole numbers in the range. And here's an example of what 0 centering does to a magic square. On the top, we have the regular 3x3 example, where I've subtracted the center value 5 from everything. Now the center is 0, and we have a symmetrical distribution of positive and negative numbers around the edges. And similarly, for the Dürer 4x4 square, we subtract off, let's see, it'd be 8.5 from everything, and then multiply by 2. And now we have a collection of odd numbers ranging from minus 15 to 15. And we see that these are also symmetric about the center. And the pattern of the sizes of the numbers is a little bit interesting. It jumps around kind of back and forth. Sometimes, occasionally, it's also useful to recenter the coordinates so that the coordinates of the middle cell become 0, 0, 0. We'll do that later, but for now we're going to not do that. Okay, what sort of magic objects exist? Okay, it turns out for magic squares, all sizes of magic square exist except 2. And it's pretty easy to see that you can't have one of size 2. For cubes, there's always a magic object of side 1. It's sort of trivial. But then the cube sizes start at 5, 6, 7, 8. And there's a whole bunch of different sizes that people have done. And the first size I didn't find on the web explicitly is 14, but that's probably because I didn't look hard enough. it seems very likely there are magic cubes of all size bigger than 5 and larger. In addition, we have proofs that sizes 2, 3, and 4 are impossible, so that problem is pretty much completely solved, modulo the problem of giving explicit constructions for the larger cubes. Now, in higher dimensions, the situation is basically there are a lot of examples of magic tesseracts and so on of different sizes. Typically, people just show the numbers, and of course, these tend to be large files. You know, you can have a megabyte very easily if you're just doing a 4th or 5th dimensional object of, size 20 or something. We have a few non-existence proofs. For example, there's no magic tesseract of size 5. For dimension 5, there's nothing of size 6 or 7 or smaller. And for dimension D, we have a construction. Well, we have a proof that there's nothing of size 2D minus 3. We have an explicit value for the center, which is that it's 0 if it's 2D minus 1 to the dth power. And then we have constructions for some larger dth power objects. Okay, a little bit of history on cubes. It was recognized very early that there's no magic 3 cube. Fermat and friends made a bunch of almost 4 cubes in which they had most of the lines right, but a few didn't add up. And they were well aware of this. They were just trying to do best possible. But of course, if you can't quite do what's perfect, then you get to define your imperfections and name them. In 1866, Mr. Frost found a 7 cube, and Mr. Frankenstein, a few years later, found an 8 cube, which he published in a Cincinnati newspaper. For a lot of the time, most of the work has been done by amateur mathematicians, and it's not published in the regular journals, which makes it an interesting historical exercise to try to go back and collect all these early things. When Martin Gardner wrote an article about this stuff, I think in 1976 for his column in Scientific American, he did not find the earlier attributions for either the 7 cube or the 8 cube. He credited them to relatively contemporary people. Now, I have an actual theorem that there's no 4 cube, which I did around that time, but it's very unlikely that I'm the first person to find this. I'll be blunt. It's just too easy. Around 2003, Walter Trump decided he would go after a 6 cube. So what he did was he took a 4 cube that wasn't quite right, but that was close, and he put in a computer search, and it did things like move the numbers around to try to make it right. And he said he found one with his program relatively quickly, and that it could easily have been done with 1980 kind of resources. And of course, our computers now are like 1,000 times faster than they were 25 years ago. He then sent this off to Christian Boyer and said, look what I found. And they decided to go after a 5. And they worked jointly, and they involved Mr. Trump's son's computers. He lived next door. And they ran this on a handful of computers for a few months, and were about to give up when they finally started to score and found a few magic cubes of size 5. I think overall they found 6 such cubes. They just sent them to me a couple days ago, but they published one of them really promptly, and that's been circulating for about 11 years. And their approach was basically to take something that was almost right and to grow it into something that could be where you move the pieces around until you get it right. Okay, the impossibility arguments all come down to showing that if the arithmetic is right, if all the equations are satisfied, then it turns out that 2 of the cells have to have equal values, which means you can't do the conventional magic object of that size. Now, that doesn't mean that you can't arrange a bunch of numbers so that they all add up. It just says that some of the numbers will have to be equal. And they all depend on this linear combination argument like the ones I showed you earlier. A lot depends on identifying non-obvious symmetries in the cube or other object. Okay, I'm going to briefly do the no magic 4 cubed argument to sort of get us in the mood for later stuff. Suppose we've got one. Then each face is going to be a magic square of size 4. And there are also some magic squares that are on diagonal planes going through the cube. And by an earlier theorem, we know that the corners of those magic squares have to add up to whatever the magic constant is for the cube. So we might have a pair of adjacent faces that share an edge, which I've labeled A, B, C, D, and C, D, E, F. And then the edges that are not shared between those two squares are two edges on the opposite sides of the cube. And there's another 4x4 magic square connecting those two edges, and that's ABFE. The corner sum of each square is 0, and a bit of algebra allows you to conclude that the pairs on the edges must add up to 0. So here's a diagram. Okay, the line survived. So ABCD is the front square, CDEF is off to the side, and ABEF is that diagonal square I've drawn some lines in for. And our equations are the sum of the four corners on each of those squares is 0. You total them all up, and each thing turns out to be counted twice, which gives you that twice the sum of all 6 numbers is 0. And you do a little bit more adding and subtracting, and you wind up with the A plus B is 0, and so on. Now that turns out to be a nice result, but it also means you can't have a magic cube, because our argument applies not only to squares oriented vertically, but also to squares oriented horizontally or in other directions. And that means that A added to several different values, everything it's connected to along an edge. In this case, A plus B is 0, and also A plus D is 0, and A plus this unnamed corner on the far back is also 0. And that means, of course, all those three values are equal to minus A, and that means you've got equal values, and that means there's no cube in the conventional sense. Okay, now I'm going to digress a little bit and describe the group of the hypercube. I'm going to tell you what the generators are. I'm not going to prove the group because it turns out to be tedious. You have the usual group of the cube. In the two-dimensional case, that's the group of the square with 8 elements. In the three-dimensional case, it's the group of the cube. And you can get half of those in real space, like if you take your Rubik's Cube and set it down and start turning it over and so on. There are 24 different ways you can orient it. And then you magically put it through one of Lewis Carroll's mirrors, and you get the other 24 orientations. Okay, there are more generators. There's one I call slide reflect, and it's probably better described by a picture. Okay, this is slide reflect on a magic square, or actually any square of numbers. You exchange the red column and the pink column, and then you also exchange the green column and the pale green, green row and the pale green row. You leave the rest of the square alone. It turns out that has all the lines in the new square will add up if all the lines in the old square added up. And you can do this for a whole bunch of selected columns, rows, and so on. You always have to do every dimension when you do one. So you've got to do whatever you do in one dimension, you've got to then go in the other dimension and do that. You can also permute slices. This is a very simple example. You select half, 1/2, like the left half, in this case of your square, and you do an exchange between the red column and the pink column. You do it in the mirror and flip over, and you do the similar exchange, and then you have to do it in the other dimensions. And that gives you what I call slice permute. And that identifies all the generators of the group for the cube, hypercube, and so on. Of course, you can combine these in strings and get a bunch of other stuff. The group order is given by this formula. The first d factorial 2 to the d is the size of the group of the square, group of the cube, and so on in conventional. And then this business with greatest integer in s over 2 and so on, that's what you get from all this slice messing around. Curiously, this formula has a symmetry between d and s over 2. I have no idea why that should be true, but it's there. And the other curiosity is that for an even s and an odd s, the next odd s, they have the same size group. And in fact, the groups are just very similar with a bunch of modifications for the middle stuff, for the odd size thing. But if you cut out everything that's a middle, you just take out all those middle slices and collapse down everything into the holes, then you have the ordinary group for the next smaller thing. It turns out that's the same group that you get in analyzing tic-tac-toe. And curiously, it turns out that if there's a first player forced win for a certain size object like the 4-cube, that seems to be equivalent to there not existing a magic object of that same size. So we know that there is a first player win for the 4-cube, thanks to Orrin Potashnik. And we also know that there's no magic 4-cube, thanks to whoever actually discovered the proof that I showed you a few minutes ago. And my main observation about this is so far it's unrefuted, rather than there's any good reason to believe it's true. Okay, I have a scheme for naming cell types and line types, which names a canonical element in each of the various classes of things that the group creates. When a group moves around a bunch of objects, it'll often happen that there's certain subsets of objects that get moved by elements of the group, but you don't get motion from one subset to another. Those are called, I think, orbits in fancy group theory. But the basic idea is that a cell can get moved to some other places by the group and not others. So like if a cell is on a corner, then it generally stays on a diagonal or a triagonal or something, rather than moving off that, no matter what the group element is. The middle element in an odd object is always fixed. Here's a hypothetical example. Suppose we have a hypercube of dimension 10 and side 9. Then the coordinates of a cell might be 3, 1, 4, 1, 5, 9, and so on, just as a hypothetical. Then the type we give to that is given by this formula with AAA, BB, and so on. And the rule for creating the type is you reflect all the coordinates down into the lower half by subtracting from s plus 1 if it makes it smaller. Any middle coordinates are replaced by the letter m. So here the 5s are replaced by m's. You sort the other coordinates so that the largest group is at the front, and any m's are placed at the end. And so that produces this triple 1, 3, 3 pattern. And then you fill in with low order letters, A, A, B, B, and so on. So the cell type for this cell would be AAA, BB, ... The thing about cell types is any two things that map to the same cell type can be moved to each other by the group. Line types are the same, except we put in x's for the coordinates that vary. And we put all the x's at the end. Okay, now we're going to do something a little fancier. We're going to show that the middle cell of a magic cube of size 5 has to be the average value 63. And this is a proof sketch. I'm leaving out details just to get the ideas over. And it turns out the group order for this size cube is 192. And there's a paper by Rollo Silver in the late 1960s showing the same thing is true for a tic-tac-toe cube of side 4. He was interested in analyzing the cubic game. Okay, it turns out there are 6 types of cells. So for example, a corner cell, one example of a corner cell is 111, and that has type AAA. So we have a column with the types, a column with the examples from the picture, the number of each cell type. So there are 16 cells of type AAA. Every triagonal in the cube running through the center it'll have 5 cells on it. The middle cell is special. The other 4 cells are of type AAA, and there are 4 of them, so you've got 16 cells of type AAA. And it turns out each cell of type AAA has 7 lines going through it. And that includes some diagonals, orthogonals, and the body diagonal or triagonal. And similarly, we have other cells, and M means that there's a middle coordinate, 1 or more. So MMM is the center cell of the cube. It turns out there are 7 types of lines. Every type of line has an X in it, and whatever isn't an X just follows the usual rules for canonicalizing a cell type. Now, the diagram survived. These are the various lines. 3 of them are orthogonals going through a face, and there are various diagonals, and the body diagonals are triagonals. And again, we have the type, a sample where you've got a from and a to, saying what the 2 endpoints are, and the number of lines of that type. And if you total up the number of lines, it comes out to the magic formula I mentioned earlier. Every line type gives rise to an equation of cell types. And the reason that's true is you can imagine you take your cube, you start with that, and you make 191 copies of that cube where you've applied all the different group elements. So you have all these cubes stretched out in a row, 192 total, and then you add up all the cubes by individual elements. So up in the corner, you add up 192 numbers that get moved into the upper right front corner. And then you divide by 192 to make the number smaller and work with the average. And you apply that, and that gives you a bunch of line equations, which apply to line types based on averaging out the lines. So for the line type AAX, which is the bottom horizontal line here in the diagram, you have an equation that says it's 2 times a corner cell type, which is AAA, plus 2 times an edge but not corner cell type, which is AAB, plus an edge middle cell, which is AAM. The sum of those line types weighted appropriately is 0. And we get one equation for each line type. So we have 7 equations altogether. It turns out we only have 6 variables in this case, which are the cell types. So it wouldn't be a great surprise if all of those turned out to be 0. And it does turn out they are 0. But it's by no means guaranteed simply from having having more equations than you have variables, but it certainly can happen. So if we actually get to sit down and solve the equations, we first discover, by looking at the bottom equation here, that there's a relationship between corner or triagonal cells and the center cell. And that says that the average of all those other non-center cells is minus 1/4, whatever the value of the center cell is. To which one might respond, duh, since that's what you would discover immediately just by examining the cube. Some of these are a little less obvious. But the critical thing is that a lot of the cell types have values that depend on the center. They're simple multiple of the center. Then at the end, we get something that shows that one of those cell types has to have the value 0, and thence all the others also do. And that shows that every cell type averages to 0 in this example. Since MMM is a cell type that contains only the center cell, we then conclude that the average of the center cell with itself 192 times is 0, and hence the center cell is 0. And now if we undo the 0 adjustment that I made at the beginning, we have to add 63 to every cell. And so for a conventional 5 cube, the center is 63. Now the reason I've walked you through this is because the same proof works for 7 to the 4th, a tesseract of side 7, or in general, a d-dimensional object of side 2 to the d minus 1. And the proof that that works involves analyzing the equations you get from the line equations and so on. And I'm going to kind of skip over this. I'll mention an idea or two. The cell types have what I call a tier, which is the number of kinds of the early letters of the alphabet. You count how many distinct letters you have, and you ignore the M's and the X's, and you only count each letter once, each of it's repeated multiple times in the type symbol. So the cell type for this AA, BBB, that's tier 4 because it has the letters A, B, C, and D in it. A line type is the same deal. You just ignore the m's and the x's. So a closely related type is that same type. That's also tier 4. From looking at that, we can analyze equations and discover that in any given line equation, there's usually one single type of maximum tier, whatever the highest tier is, and every other term in the equation is of one lower tier. And that allows us to start at tier 0, which is the equation for the center cell only, and work up and say that at each tier, each higher tier, there's a simple multiplication that you can use on the lower tier object to get the higher tier object. And those coefficients depend only on the tier, it turns out, and the cube dimensions, but not the particular cell type that has the tier. Okay, this is the same thing over again. It notes that the multiplier in all cases is going to be a negative number to move up one tier. So that says the averages for tier 1 are all going to have the opposite sign from whatever the center cell sign is. And the averages of tier 2 will be the same as the center cell and so on. Okay, consequences. If there's no middle cell, then it turns out to be very easy to show that every cell type averages to 0. If S is odd, this defines the relation I've been describing, where there's a simple way of going from whatever the center cell value is to saying what the other averages are. If S is 2D minus 1, you get the property that the center cell has to be 0, and all the other cell types do too. If S is 2D minus 3 or smaller, then there is no magic object, because the lower dimensional hyperobjects will all have the same center cell value, and you get this violation of the rule that every number has to be different in the cube. If S is bigger than 2D minus 1, then the center cell might well be non-zero, but you have equations that tell you the values of all the other cell types, at least, the averages. Now we're going to switch gears to a simpler group. It's a subgroup, of course, the big group. This is what I call the mirror subgroup. You take your magic cube and you slice it down the middle vertically, and you reflect everything over to one side. And then you repeat that for every other dimension. So your final result is going to be about 1/8 of the volume of the original. And most of the cells will have had 8 numbers added together. In cube case, tesseract, it'll be 16 numbers and so on. And we're going to stick to even sizes for now. The odd stuff is a lot more interesting, but it gets real complicated fast. For the even sizes, the mirror never cuts a cell in half. There's always an exact copy on one side or the other. So the volume of the resulting cube is some power of 2 smaller than the original. And it's useful to analyze that smaller cube. We're able to do it in some cases. So we can do a little bit of work on the 6 cube this way. By folding it down, we get a 3 cube that we can look at. Some of the diagonals of that 3 cube come from diagonals of the 6 cube and preserve the appropriate equations. There will be new diagonals in the 3 cube that are not from diagonals in the 6 cube, and we can't actually say anything about those. Now, if we look at the top face, you have a 3 by 3 kind of magic square. The orthogonal lines still have to add up to 0, and one of the diagonals has to add up to 0. If we just look at the orthogonals briefly, we can fix 4 of the variables, A, B, C, and D here, and figure out what the remaining 5 have to be just by doing adds and subtracts. And then we can do the diagonal equation, the one valid diagonal equation here, which is the sum of A plus D plus that sum of 4 copies adds up to 0. And that gives us an equation which we might say, okay, we can substitute that back for D and make things messy. Now for the second level of the cube, we need to fill in E, F, G, and H and do the same exercise. The third level of the cube we can just calculate by knowing the top 2 levels. So here's what these equations look like. There's one equation for the triagonal which starts at A and runs down through A plus B plus G plus H. And we do a bunch of algebra. And in particular, we noticed that there seemed to be 7 independent relationships in this with 8 variables in this cube. We've got orthogonals and diagonals and a triagonal. And it turns out this is the result of a folded object. Up in the upper left corner, we have a 0 that corresponds to the 8 corners of the original cube. And that gives us our theorem that the sum of the 8 corners is 0. And because that turns out to be of the same cell type as the inner 2 by 2 cube, we have a similar theorem for the inner 2 by 2 cube. And there's another set of cells left over on the diagonal, which are the corners of that inner, sort of the inner cube that make a 4 by 4 by 4. And those also have to add up to 0. And so do a bunch of other things. If you place these 3 squares on top of each other, you can see there are diagonal layers that either add up to b or minus b or 0. Okay, with our theorem about the sum of the corners of a cube of size 6, we can then say there's no magic 6 to the 5th object. And the argument is very similar to the one I showed you for no magic 4 cube. You identify magic subcubes within the 6 to the 5th object. You make the appropriate triangular pattern with overlap, and that tells you that some magic squares have to have corner sum 0. And then you can sometimes apply that argument, but it tends to go down to magic lines with 2 elements. And that's where we need to stop to prove values are equal. However, we need another dimension in order to fit in all the diagonal and extra diagonal cubes we need. Now, if we go to even sizes bigger than 6, the argument about using triangular objects to drop the dimension down still works easily. However, getting the proof that the corners add up to 0, so far all I've got is ad hoc methods rather than some general method that proves the theorem here. I think it's certainly true, but that's not the same as having the result. And then I'm going to finish off with a construction for some odd hypercubes. This is really a generalization of the old just write it down method for an odd square. Many of you will probably have read an article about this a long time ago. If you want to write down a magic square of an odd size, you start in the middle of the top row and you write a 1. And then you move up diagonally, which immediately takes you off the square. So you wrap around to the bottom cell that corresponds to that and you write a 2. And you keep going up diagonally, 3, 4, 5, and so on. Eventually you'll fall off the right edge and wrap around to the left edge. And then you'll come back and bump into your 1. Now, if you're about to bump into your 1, you instead step down 1 cell and resume. So you're gradually filling in this square with this pattern. And you can just write it down without having to do any arithmetic or anything. You know it'll come out. And I've generalized that to higher dimensions. I'm pretty sure that whoever came up with the first 7 cube did a similar thing of generalizing that rule because it's been known for centuries. What we have to do is specify for each size step what change you make in the value. And this slide describes the rules that you use for stepping in each direction. If you want to step 1 to the right in the x direction, you add 1 to every coordinate. If instead you want to go back in the y direction, you add 2 to every coordinate, except for one of them you subtract 2. And similarly for 4 and 8 and so on. And whenever this is where we use centered coordinates. So the center cell is 0. And whenever you wrap around a coordinate going beyond s over 2 or minus s over 2, you add in an s to bring it back within the cube. So in essence, it's like a gigantic torus in n space. And you no longer have to follow this strict pattern of always going in one direction. You can just, in essence, walk out from the center in whatever set of steps you want. Okay, you then get, in effect, a combinatorial design in which all the different s to the D patterns occur exactly once, and the sum of every row and column and diagonal and multiple diagonal comes out to be 0. The rule is you change the coordinates so they're reduced in a balanced residue system. So instead of going from 0 to s minus 1, your coordinates go from minus s over 2 to s over 2, plus or minus a half. Okay, for any given set of coordinates for a cell, you have a vector that describes that cell. You can make these 1, 1, 1, 2, 2, 2, so on into a matrix and just multiply it by the cell coordinates, reduce everything to the balanced residue system mod s, and finally you say, okay, that's a representation of an integer base s, radix s. And you calculate that integer, and that's what you stick into your magic object. So here's what you do for the 7 cube. The 3 vectors are 1, 1, 1, 2, 2, minus 2, 4, minus 4, 4. You look at the king moves in all directions to make sure that there are no zeros in any coordinates. So you've got the diagonals, they're all fine. There are no zeros or 7s there. The triagonals, it's okay to have zeros, it turns out, as long as it's not all zeros. The reason that that's okay is all triagonals go through the center, and the coordinates of the center are all 0. So adding a 0 along a diagonal or triagonal is just fine, doesn't disturb anything. It means that the sum of those digits, when you add them up, will still be 0. And here are some examples with moving in different directions. Okay, there are a bunch of stuff we need to check that this still works, that it all comes out correctly. You have to make sure every number is used. And for that, we make a note that the determinant of the matrix is a power of 2. Well, actually, a power of minus 2, but good enough. And we need to check that every line adds to 0. And the reason for that is every direction, except for the polyagonals, maxagonals, has no zeros in its coordinate system. And that means that if you walk along that diagonal for s steps, that coordinate runs through all of the values mod s. And since we're using a balanced coordinate system, that means it adds up to 0. Maxagonals can have some zeros, but for the reason I described earlier, that's okay. And that means that when you do the addition, every line adds up to 0 in all coordinates. Okay, what can you do with this? Okay, for d equals 2, this is just the regular write it down magic square. And you get all the odd size squares as a result. This is what we call very old news. For cubes, the first place it works is 7. It turns out you want a prime side for this in order that the wraparound stuff works properly. So it'll give you a cube of size 7 or 11, all the primes bigger than 7. And I have a suspicion this is also well known, although I haven't seen it. And similarly for dimension 4, starting with the prime 17, you get all those sizes. Dimension 5 starts at 31, because 31's prime. And here we have similar things for the higher dimensions. And since you also get the products of the primes, if we ask what is the set of things this doesn't produce in dimension 3, for example, the answer is anything that's not divisible by 2 or 3 or 5. As long as all the divisors are 7 and larger, we can get a cube this way. We might have to combine using the multiplication algorithm I described near the beginning of the talk and work out each individual prime, and then there's a simple way to combine them. Now, it turns out that the set of numbers that are not divisible by 2, 3, or 5 encompasses 26% of all numbers. That's an easy calculation. And that means we've shown that at least for 26% of the possible size cubes, there is a cube of that size, magic cube. And similarly for 4th and 5th powers and so on. And notice that the fraction doesn't drop off all that rapidly. So when we go from cubes to tesseracts, we still have 19% of the tesseracts. And if you look at what the product of those terms comes out to be for the higher dimensions, it turns out that even for 10 dimensions, you can show that something like between 5 and 10% of all numbers have a 10-dimensional cube. And that'll have to pass for the advanced math for this talk. Here's some good web pages to go to. Christian Boyer and Walter Trump did the 5-cube and the 6-cube. Harvey Heinz has an excellent resource for magic squares. Unfortunately, he died recently, so if you want to look at his page, you'd probably do well to look at it yesterday. It was still there yesterday. Eric Weinstein works for Steve Wolfram, and he's got a good page on magic cubes in the Math World Encyclopedia. And thank you for listening. And I have... Are we doing questions, or should we? Okay. At least 6. I don't actually know the answer to that. I think it's probably, gazillions. The problem you run into is there actually is a method for estimating how many magic squares of a given size. And it does a decent job on 5. We figure it's probably at least got the order of magnitude right on 6. But you need to know the number of independent line equations. And because the independence is a complicated issue, so each independent line cuts down the number of magic objects by some fraction. And not knowing even how many independent lines there are, you're sort of stuck. The only way I know to get it for sure is to actually write out the matrix and find the rank. And for even small things, it's certainly doable for an object with 1,000 lines in it. But that only covers you for actually a very small number of these magic cubes and so on. There's also a question of, is there some interaction given the numbers you're using, so that whether it's valid to correctly multiply all these numbers together and use that as an estimate is up in the air. All liquid?
Okay, thank you very much again.
And I guess Jeff is next. Well, let me get rid of this.
Okay, so our next speaker is Jeff Harris, and he will be available momentarily.
Thank you for the invitation. I'm going to speak on work of Dürer and work on polyhedra and shadows of polyhedra. This is a conference, NYU Polytechnic. The word poly in Polytechnic is the same as that in polyhedra. Here are some credits. I'm going to mention some work of Hassan and Lubia on equiprojective polyhedra. They have one paper and one preprint on the archive. I borrowed 2 slides from one of their talks because they can draw polyhedra better than I can. So the contents of this talk are, I want to discuss Dürer and his history to give background. That will be a good fraction of the talk. Then some brief remark on polyhedra and shadows. Maybe I could demonstrate. And then 2 modern topics, equiprojective polyhedra and the Moser shadow problem. So Dürer was born in the imperial free city of Nuremberg. He lived from 1471 to 1528. He is originally Hungarian. His father moved from Hungary to Nuremberg. His Hungarian last name was Germanized to, which means Dürer was Germanized to Dürer, which his father used, and then he changed it to Dürer. His father was a jeweler. He learned the trade of goldsmith and jeweler originally, and then was apprenticed to a painter and woodcut designer. After 4 years apprenticing, he had sort of learned everything he could from his master, and he was sent traveling. He went to Ulm, Constance, Basel, Colmar, Strasbourg, and returned home 4 years later. Got in a marriage which was arranged, and left very soon after and went to Augsburg, Trento, and Venice. This was his first visit to Italy. And there he met the painter and printmaker Jacopo di Barberi. And he was introduced to some mathematics at that point, and he became extremely interested in mathematics and art. And when he went back to Nuremberg, he studied Euclid's Elements, Vitruvius's book on architecture, and then some mathematical books on perspective and proportion, books of Alberti and Luca Pacioli. Of course, he did a lot of artistic work in this period, but I'm going to concentrate on the mathematical aspects. He made a second trip to Italy, 1505 to 1507, mainly in Venice. He was lent money for this trip by his lifelong friend Willibald Pirkheimer. He wrote letters to Pirkheimer, so we know a lot about things from that on this trip and later trips. He was now pretty famous for his artistic work. While in Italy, he may have made a side trip to Bologna to attempt to see Luca Pacioli. I'd like to say something about the 2 related figures, Jacopo di Barberi and Luca Pacioli. Barberi was an Italian painter. He was in the Venice area for a long time. He was an engraver and printmaker. A portrait of Pacioli, which I will show you, is attributed to him. That is to say, his signature is on the painting. Apparently, there's some dispute. He's famous for a very large woodcut view of Venice that he made that appears to be made from the air. It was made using surveyor's measurements. It took him 3 years to cut it, and the publisher got out a patent on it when it appeared in 1500. Well, after he finished that, he emigrated to the north and brought some Renaissance art to the north. And in particular, he spent a year in Nuremberg, and he must have interacted a great deal with Dürer while he was there. And later on, he moved to the Netherlands, where he had aristocratic patrons, and he received a pension in 1611 from one of them. Luca Pacioli was a Franciscan friar. He wrote a 600-page book, Summa de Arithmetica Geometrica Proportioni and Proportionalita, and published in Venice in 1494. He was presumably in Venice overseeing it when it came to the press. It has the first written treatment of double entry bookkeeping. This book incorporates at least some fraction of the books in this summation of mathematics at the time, incorporated work of Piero della Francesca without attribution. Francisca had died in 1492, so in particular, Francisca was a well-known painter and did a lot with projective geometry and also with polyhedra. Certainly, Pacioli knew of polyhedra, and in particular the Archimedean polyhedra going beyond the regular polyhedra, and he had wooden models built. They were sold to a set was made for the city of Florence. He had models constructed in wood and glass. Presumably the glass was made by glass blowers in Venice. A few years later, he was in Milan and with Leonardo da Vinci, where he was instructing da Vinci in mathematical things. He wrote a book there, Divina Proportione, referring to the golden ratio. It was written in the 1490s, circulated in manuscript, and published in 1509. It was illustrated by Leonardo da Vinci, so it's quite famous, and I assume it will be in Günter's talk later. So here is the portrait of Luca Pacioli. The person at the right is unidentified. There are a bunch of arguments over who it might be, whether it was the aristocrat to whom the painting was dedicated, or perhaps Dürer himself. He's got open a book of Euclid to Book 13, Proposition 8. That's the book on the construction of the regular polyhedra, the last book of Euclid's Elements. You will see in the upper left corner, you will see a glass Archimedean polyhedra that seems to be half full of water. At the bottom, you'll see a regular dodecahedron. So here's an enlarged copy of that glass polyhedron, presumably drawn from life. It's hanging from a string, and it appears to be half full of some fluid. So if you will check, its faces are squares and regular and equilateral triangles. Here's a portrait that Dürer drew of himself at age 28 in 1500. So one time I'm going to flip back if you want to see whether there's any resemblance between that and the person in the right in this figure in 1495. But the figure in the right has blue eyes, and Dürer had hazel eyes. Here is the De Barberi map of Venice that appears to be taken from the air. You will see that it's several large woodcut pages, so this is actually quite a big thing. And the date is at the middle of the patent date is at the middle of the picture, MD. So continuing with Dürer, in 1508, after the return from his second trip to Venice, he started collecting materials for mathematics and applications to the arts. And one person has described his viewpoint as being that art must be based on science, in particular on mathematics, as the most exact, logical, and graphically constructed of the sciences. He received commissions from the Holy Roman Emperor Maximilian I to do art for him starting in 1512, and he didn't meet the emperor until 1519 when he traveled and there did the emperor's portrait, 1518. In this period, while he's in Nuremberg, he produced 3 famous engravings that may be a series, and they include Melancholia 1, which is the subject of this conference. So now I'd like to say some things about Melancholia 1. So here is a small reproduction, very blurred, of the Melancholia. It has an angel or a female figure with wings. It's got a lot of things which I will show in a little more detail on subsequent slides. So let me summarize some of them. It's packed full of images of significance. Almost every one of them has a meaning. I won't get into them, but I think there was a two-volume book written trying to analyze everything that was in this print. More recently, Dan Brown included it in one of his novels. What is it? The Lost Symbol. So there's an angel. Is it contemplative or brooding? There is a putto, a secular symbol, often of a passion. There is a bat with a slogan. There's an emaciated dog. There's a comet. There's a rainbow. And there's a big polyhedron. And there's some debate as to what it is. It appears to be approximately a cube with 2 corners cut off. It's got 2 triangular faces and 6 pentagonal faces, but it's not exactly that. I think there are samples of the Dürer solid over there. There is a magic square. So here is a blow-up of the corner of the plate with the bat with Melancholia 1 on its outstretched wings. So I will say a little of the symbolism of the Melancholia, but the melancholy temperament of the 4 temperaments is associated with the planet Saturn of Earth, and the bat and the dog are apparently associated with that symbol. There is a comet, which you see in the background. The comet appeared in January, February of 1514 in the constellation Leo. There is a rainbow. Here's a putto, the cherub-like figure, but is secular. It usually symbolizes a passion. If you look closely at this, you will see that the child is holding a tablet and a graving tool. So I guess that's saying something about the passion in this case. Here's the emaciated dog down in the side of the figure. There's a sphere. What's that a symbol of? There are some woodworking tools. Here is the polyhedron. It's pretty big. It appears to be of stone. Notice that it's casting a shadow. So you will see, since I want to talk about shadows, you will see a little shadow underneath it to the right. And if we went back and finally, here's the magic square. So the magic square is a 4x4 magic square, and he presumably he presumably chose the 4x4 magic square, which has the date 1514 down in the bottom row. So the date appears twice in this engraving. It appears in this magic square in that row, 1514, and it also, Dürer always signed his paintings AD, and that's down with a date, and that's down in the right-hand corner at the bottom, not visible. An interesting question about shadows in the Melancholia is, where is the light source? Because if you go back and you look, you will see that the drapes are casting a shadow, and apparently the shadow, maybe it's on the front cover of the program, the shadow appears to be, the light source appears to be up and to the right, especially from the shadow On the other hand, if we're looking at the comet and the rainbow, it looks like that area of the painting is in darkness. So now the background. Well, the background is partly the occult. So the occult, the word occult means hidden from view, and from astronomy, one astronomical object occults another if it comes in front of it and blocks its view. And so, if you like, shadows also fit with the occult. And at about this time, Cornelius Agrippa, who was approximately the same age as Dürer, he's a little bit younger, was writing. He studied with, in 1510 with Johannes Trithemius, a Benedict monarch, abbot who wrote one of the first books on cryptography, the Steganographia. And Agrippa wrote a manuscript which collected together all a compendium of stuff on magic and alchemy, the De Occulta Philosophica Liberi Tres, 3 volumes on the occult. Copies were already circulating in manuscript in 1510. It was rewritten many times, and it was published in 1531 with a long preface saying, I don't believe in any of this stuff, in order to get permission to publish. In Cornelius Agrippa, he discusses the 4 temperaments, and he discusses several kinds of melancholy. One kind, inspired melancholy, comes in 3 grades. Melancholy of the imagination, of reason, and of the intellect. And Melancholia 1 is probably signifying the first of these, according to various authorities. So let me mention 2 of them that are extremely well known. There's Erwin Panofsky, who wrote several books on Dürer. He emigrated from Germany and was at the Institute for Advanced Study for a long time. He feels the engraving in Melancholia expresses the frustration of creation, the suffering at being unable to express your visions the way you want, and inactivity, just sitting there. Whereas Dame Frances Yates' view is that the angel in Melancholia 1 is actually in an intense visionary state of creativity. So either you're depressed or you're not depressed. By the way, I was very happy to be invited to give to this conference to speak on melancholy, because I definitely have the melancholy temperament. There are 4 humors, and melancholy is one of them. There's an internet quiz. You can take it and find out what type you are. So I took it, and sure enough. Going on with Dürer, he made another trip, this time to the Netherlands in 1520. So this was to attempt to collect a pension from the emperor. The emperor had died, and the follow-up said, we don't want to give you any money. So he was going there, and he was well off enough that he didn't need the money, but he wanted to just get it as a matter of course. Also, he wanted to, de Barbari had died at that point, and he had apparently left a manuscript on perspective, which his patron supposedly had. So he wanted to visit Margaret, Archduchess Margaret, and try to recover a copy of this. And he got there, and she said, oh, too late, I gave it away to somebody. It's not here anymore. And then it got lost. Also, while he was in the Netherlands, he may have caught malaria. He went out to the islands to look at a whale that had washed up. And anyway, when he returned to Nuremberg, he was ill, and he remained in bad health for the rest of his life. He concentrated on his studio, on writing up stuff, and publishing. So like many authors, he found he needed to become a publisher. He had his own printing press. He designed type and had it executed, so the later German fonts are actually based on some of Dürer's fonts. And he wanted to write a book on human proportion, but then he said, I need an elementary book on mathematics to explain this, and this is his Unterweisung on drawing. One might say it is one of the first German books on mathematics in the vernacular. He had another book in the middle on fortifications. So now let me come to his geometry book, the Unterweisung, which, by the way, also, like Knuth, had designs for letters. So all the letters are in there and a possible font for them. Published in 1525, it consists of 4 books. It's several hundred pages long. There's a facsimile version that's been reprinted, which I looked at. This is only a very limited sketch of what is in those books. The first book is construction of curves and many spirals and the conchoid and other curves. The second book has a construction of regular polygons, and he also had cutout models for the polygons, so you can cut them on a strip and then fold them up to make the polygons. Various constructions. It has a construction that approximately trisects the angles. The third book has stuff connected with pyramids, cylinders, solid bodies, and sundials. So then he wanted to deal with shadows and perspective and how you draw shadows. So the fourth book has constructions of the Platonic solids and the Archimedean polyhedra, and it has material related to shadows and perspective. So here is a plate from the book having to do with shadows. You see a light source at the top, which is the sun, and it's projecting down to a cube. He also, in some of these plots, they fold out to 2 pages. He has an eyeball and lines drawn from the eyeball to seeing an object, and it's in order to figure out how to draw it. I would like to say that some of the projective geometry goes back to Piero della Francesca, who died before he published things. But Pacioli published a whole lot of stuff which made it available to the general audience. So here's a second his page with his German print font, and down at the bottom you see the sun projecting rays onto a cube and then casting a shadow onto a flat surface. And as they say in teaching, it's all repetition. So now he draws you a picture of the sun with his cube and casting the shadow. And as with actual light, where there's diffraction, it's actually lighter around the edges than it is further in, because there's some light diffracting around the edges of the object. Here is going back to the other book is a cutout for making an icosahedron. So the triangular strips there with the 20 triangles can be folded up to give you an icosahedron, which he has drawn at the right. Well, that's what I have to say about Dürer. And now I would like to say some things about polyhedra and shadows. So I didn't do this before, but I wanted to actually try. I wanted to actually try displaying some of this stuff. And you should test everything in advance before you do it, like how to put up the... Okay, here's a dodecahedron. It's a Rubik's Cube. Did you know that Rubik's Cubes now come in dodecahedral size? You can turn them this way. I got this prop at the last minute when I was coming here. I thought, well, I should bring along some polyhedra, so I went to the undergraduate math office and tried to find some. Okay, here's a dodecahedron. It's casting a shadow. I'm interested in mathematical shadows, so the point of a polyhedron is the shadow is going to be a polygon. In this case, the polygon has 10 sides. when I put it on a flat face. So now I distort it. This is not going to work. This is the problem in light. You see, light does diffract around edges, so you see the blurry thing. This is, if this were physics and not mathematics, then I would have to. All right. Better if I'm close to the screen. As I move it around, the shape distorted. So that is Euclidean geometry. And now, if I want to get, this is not going to work either. I want to do projective geometry by changing the perspective, and you will see that it's now no longer a regular octagon in this projected version, but it's still got 10 edges. Here is Dürer's polyhedron with a small model made by a 3D printer. I guess, well, how many sides does this projection have? Well, what I want to observe is that if you turn the polyhedron around, you get different numbers of sides showing. So the shadow depends on where the polyhedron is in the general case. Okay, well, that's all for now. Okay, so you can consider the shadow of a polyhedron as cast onto a flat screen behind it like I was doing here. And the shadow will be a polygon having a finite number of corners, which I'm going to call K, and it could vary according to what direction you project, you hold the polyhedron. And there are two models for shadows that I'd like to think about. One view of shadows is they're coming from a point source which might be nearby, as in the picture of the eyeball looking in Dürer's print. On the other hand, the shadow could be from the sun. It could be very far away. And then our image can be that we view the shadow as coming from a source in infinity, in which case the light rays we treat as parallel. And then if you project them onto a screen perpendicular to the direction of the light rays, then you will get orthogonal projection. And the orthogonal projection will be Euclidean geometry, a Euclidean object, whereas the projection, when you project obliquely, you will get a distorted image that's projective geometry. But you notice as you move the screen, it won't change the number of edges on the polygon. If you leave the light source fixed and you I want to leave the light source fixed and the polygon fixed, and I want to move the screen. It will change the shape of the polygon, but the number of vertices on it will stay the same. K will stay the same under moving the screen. Okay, so I had two slides on polyhedra. So a bounded polyhedron, or the n-dimensional version is a polytope will be the word for bounded polyhedron, is the smallest convex set containing a given finite set of points. So I take a finite set of points, and then I take all viewed with coordinates, and I take all vectors which are points x that are linear combinations, lambda 1, lambda 2, lambda n, where the lambda i's are non-negative and add up to 1. So the barycenter of a triangle is an example, the central point, which is an average of all the vertices of the triangles. If you take all such averages, then you get, that's one way to construct a polyhedron. For a polyhedron, the minimal set of points you could use would be the vertices of the polyhedron. You're taking all linear combinations of the vertices. This set P, when you're given a set S, which a finite set of points, that's called the convex hull of the set of points. So in this case, this polyhedron is a convex hull of its vertices. All the averages of the vertices will be points on the faces or interior to it. You could be redundant. You could include other points inside or on the boundary. They wouldn't give you anything extra. The vertices do it all for polyhedra. So the bounded polygons are the two-dimensional version of this convex hull construction, and bounded polyhedra are the three-dimensional version. There's a slight mistake there. I leave that to the question period. Find the mistake. Okay, there's another method for constructing polyhedra which constructs them by a dual thing. It's intersection of half spaces. So a possibly unbounded polyhedron is a set cut out as an intersection of a finite number of half spaces. So a half space is specified by a set of linear inequalities. The AIs are real numbers, the XIs are vectors, less than B, so that will give you a half space. You intersect these half spaces. If you pick things properly, you'll get a bounded object, and if they are bounded, they will give exactly the same set of objects as we get with the convex hull construction. These sets are also convex, but they might be unbounded. Let me say that the use of coordinates here is completely anachronistic. Dürer didn't have anything like that. They're due to Descartes, and Descartes lived 100 years later. Before getting to mathematical results having to do with shadows, I should mention what are polyhedra and shadows good for? Well, in the unbounded version, they show up in mathematical optimization, in linear programming problems, which of course are used all over the place. And in fact, there are variants of the simplex algorithm in linear programming that actually use shadows. They use the so-called shadow vertex algorithm. You try to crawl uphill to the maximum thing. You try to get on the boundary, and you try to crawl uphill, if you're a bug, on the outside of the polytope to get, when you're maximizing some quantity. The shadow vertex algorithm projects down to a two-dimensional shadow and uses that to decide how to crawl. In computational geometry, subjects such as robotics, a lot of things are motion planning and how do you move things around. The original models, the original simplified mathematical problems involved using polyhedral obstacles, and so polyhedra appear in that framework. And then finally we come to shadows. So what are shadows good for? Well, shadows are good for hiding things, and also nowadays you can possibly use shadows for fraud detection when there are people photoshopping images that they're putting in journals and so on, and if the shadows are wrong, you can detect this. And there's an interesting case that has to do with that painting of Luca Pacioli. I don't want to go flip back through the slides, but there are two people in the image. There's Luca in the front pointing at his geometry, at Euclid's geometry book, and there's a second figure off to the side. So there are some shadows in this picture, and the orientation of the shadows is such that the person who's standing behind should have a shadow on his glove, but there is no shadow on the glove. And so one art historian has theorized that, in fact, there was a second painting of Luca Pacioli without the second person in there, and that De Barbari was making a copy or an imitation in which he added extra stuff. And in particular, the first painting was attributed to Della Francesca, and it is lost if it ever existed. But there's a record somewhere that somebody saw in the Duke's Palace in Urbino. He saw this other picture and described enough of it for this historian to guess that it wasn't the same picture. But he did say it had polyhedra in it, but he said it had many. Perhaps many means at least three. Okay, so the funny shadows are one of the favored argument that the original painting was used as a model for the second painting, if any of that is true. But such is the occult. So now I'm coming to two mathematical topics that are related to polyhedra and shadows. These are topics about the mathematical shadows cast by polyhedra. The topic, I think the announcement for this conference said the greatest mathematics of the 20th century. These are interesting topics in mathematics that somehow are directly related to stuff that Dürer was doing. So a polyhedron, we will say, is equiprojective if it has the following property. If it's orthogonal projections from infinity, that's parallel light rays, to a plane is a k-gon in every direction, except there's a finite number of directions that are parallel to the faces of the polyhedron, and in that case you will see fewer. So the idea of studying such polyhedra was due to Shepard, who is well known for a book on packings and tilings. He had a list of problems and he studied these things. So not all polyhedra. So here's a slide, a borrowed slide. A convex polyhedron is K equiprojective if all its orthogonal projections except those parallel to the faces of P all have the same size. And one can show that any k-gonal prism is K plus 2 equiprojective. So here you see a triangular prism, a quadrangular prism, which could be a cube. It doesn't matter, and a hexagonal prism. This shows, by the way, but not every polyhedron is equiprojective. In fact, they are incredibly strongly constrained. They have to have, as we will see. So here's a tetrahedron held at two angles. So at one angle, you see K is 3 on the left, and K is 4 on the right. So on the right-hand side, all 4 of the vertices of the tetrahedron are visible along the edges of the shadow, but in the leftmost one, the one vertex is hidden. It's not visible in the shadow. You can't see it in the shadow. And some theorems about this. I think the original, the prism is due to Shepard, that it's K plus 2 equiprojective. That shows that equiprojective polyhedra exists with any number of sides bigger than or equal to 5. And the case K equals 6 gives you the cube. And in my example here, the dodecahedron, I believe, is also equiprojective with K equals 10. And one theorem that can be shown about this is a necessary condition is that an equiprojective polyhedron has to have two faces that are parallel. And in the case of the prisms, they have arbitrarily many faces, but exactly 2 are parallel for the prisms with an odd number of edges. And the work I'm describing gave a characterization of equiprojective polyhedra. And I want to say, what is the idea? So the idea is that if a polyhedron is going to be equiprojective, as you rotate it around, there's going to be, you can put it for any polyhedron. If you pick an edge, you can find a light source that will see that edge. You can rotate it around so that edge will be visible on the outside. So clearly, you can move the polyhedron around. You can get every vertex so it's on the shadow. So as you move it around, you can see every vertex of the polyhedron. But at any one time, the shadow only sees the vertices that are on the outside, which might be a very small set of these vertices. And so how many is that? Well, getting back to equiprojective polyhedra, when you rotate it around, there's going to be a point where one edge disappears and the change of the outside changes. So when one edge disappears, to have this equiprojective property, a new edge must instantly reappear at that point in order to compensate for it. And that edge could be on the same face when you make a face flat and then you turn a little more and you switch from one edge to another, or it could be on a different face entirely. So you can label the faces in pairs where you have a pair consists of an edge and the face it belongs to. And so when you do this move where you change things, you change one edge and face as you cross over, as you rotate, and you'll get another edge and possibly another face. And that will be a before pair and an after pair. And this is the this is the characterization due to Hassan and Lubin. So we need some combinatorial data that's attached to the polyhedron. And that combinatorial data is a graph indicating its vertices and edges and faces. So typically you can get that by projecting a hollow version of the polyhedron with just the skeleton of the vertices and edges onto a screen. And Leonardo was the first to make pictures like that, where you can see what's going on. And we need some extra data, which is for each edge, we look at the face that it's on, and we give it a clockwise orientation viewed from outside the polyhedros. So viewing from the outside, there'll be a clockwise orientation. We orient the edges with arrows going clockwise. And their result is that a polyhedron is equiprojective if and only if this combinatorial graph with the marked parallel edges, with the edges marked with the arrow, can be decomposed into pairs of edges with the arrows having opposite orientations. If you want to get the exact theorem, please see the paper. And they also showed that the structure on the graph with the arrows, if you have a polyhedron with n edges, then there's a fast algorithm to determine whether it's equiprojective by finding this compensating pair structure. And as a corollary of this, you can show that if you have any polyhedron that has, I have it labeled here, that has n edges and a given k, you can find all the different abstract types of equiprojective polyhedra that have n edges and with shadows having k vertices, because you can describe them in terms of these graphs, and then you can find all of the graphs. There are finitely many, then check their orientations, and then check which ones are constructible. By the way, if you're relating vertices, edges, and faces on a polyhedron, I want to say that they're polynomially related, that if the number of edges, right, vertices minus edges plus faces equals 2, so the number of edges dominates the sum of the vertices and the faces. So the number of edges will be greater than or equal to either. And in the other direction, if you have n vertices, then you have at most n squared edges, because there's at most one edge between each pair of vertices. And then by duality, you get that for faces. So now let me go on to the second topic, which is the Moser shadow problem. So Leo Moser was born in Vienna, and he emigrated to Canada, and then went to the US and got a PhD with Alfred Brauer at North Carolina in 1960. In 1950, he worked in computational geometry. He's well known in this field for a problem list that he wrote in the middle 1960s, which was called 50 Poorly Posed Problems in Combinatorial Geometry. And problem number 35 is this shadow problem. It is estimate the largest function f of n such that every convex polyhedron of n vertices has an orthogonal projection onto the plane with n vertices on the outside. Sorry, it's a misprint. F of n vertices on the outside. So what we're trying to do is we're trying to find the worst polyhedron with n vertices that casts the shadows that are smallest in every direction. And the question is, how well can you do? I'm repeating this slide here, and I think I got it right in the next slide. So let's try to define that again. We have a single polyhedron, and we're going to compute its shadow number. And the shadow number will be the largest shadow it casts as measured by the number of vertices of the polygon. So we're going to look around at every direction with parallel light rays, and we're going to find the direction where the shadow has the maximum number of vertices. That will be the shadow number for the polyhedron. That's the maximum number of vertices you can see on the outside. And now we're going to minimize that over all polyhedra with n vertices. So this is a minimax problem. The shadow function will be the minimal shadow number of any polyhedron having n vertices. And the question is, how small is this function f of n? And in fact, is it even unbounded? So this is the thing. We don't even understand 3 dimensions because this problem has stayed open until last year. So for example, if you have an equiprojective polyhedron, then its equiprojectivity number is going to be the shadow number. And I would like to say that this shadow number is an invariant of Euclidean geometry. It's determined by the Euclidean shape. But if you use projective transformations to skew the polyhedron, you can change the shadow number. So it's a problem that's related to Euclidean geometry and not projective geometry. Okay, but it's natural to consider the projective version, and so now I will. The projective shadow number, or sometimes called the silhouette number, is the largest number of vertices on any shadow that a polyhedron casts from a point source at a finite distance. And it can be shown that the projective shadow number is at least as big as the shadow number, because if you take a finite light source and you move it very far away, you can match any light source at infinity. You get sufficiently far away and you won't be able to tell the difference, at least for the number of corners. And the projective shadow function f star will then be the minimal shadow number taken over all polyhedra with n vertices. And again, the result on the individuals will apply to the function. The function f star of n has to be at least as big as f of n. Okay, well, when Moser thought up this problem, he also had a construction. He didn't write it down, but it's fairly straightforward. You can use it to show the shadow function f of n can't be any bigger than a constant times log n. That is, you can manage to find a polyhedron that has 2 to the n vertices, but every shadow in every direction is at most constant n times vertices showing along the side. You can take a tetrahedron and you can start gluing triangular faces on the tetrahedron very flat, and then glue 4 triangular faces, little tetrahedra on each face, and just keep iterating this. And you can concoct a polyhedron with this log n shadow number. And apparently he believed this was the right answer. But then 20 years later, Chazelle, Edelsbrunner, and Giebos improved on this. They got an upper bound of log n over log n, which is really a crazy answer. And furthermore, they showed this is the correct answer for how the projective shadow function behaves. But the proof is complicated, and also the construction is not entirely obvious. And in fact, it's not obvious from the way they did it, because they used projective duality, and then they concocted something in the dual version projected onto a plane, and then you can try to reverse that to figure out what the actual thing looks like. And in particular, this gives the upper bound constant log n over log n for the shadow function. But they didn't get any lower bound. But last year with a summer student, we were able to resolve this problem. And the answer turns out to differ for bounded and unbounded polyhedra. So in the unbounded polyhedra case, you get unbounded shadows. You get a polygon, an unbounded polygon. Or sometimes if you look in the wrong direction, you don't get anything at all. You just get black. And here are the answers. The answers are the same for bounded polyhedra. For n bigger than 5, the shadow number is bounded above and below by a constant log n over log n. And I would like to say that the proof is an adaptation of the proof of Chazelle, Edelsbrunner, and Giebos. It improves on their front end. They were using purely projective geometry. And since the projective geometry can change the Euclidean shadow number, it cannot be used to bound the Euclidean shadow number. So you can put a reduction front end, which uses a spherical transform followed by a central projection to get this result. And it has a corollary that it explains there's a difference between the bounded and unbounded case. The unbounded case, in fact, the shadow number in the full unbounded case is finite. It's bounded by 6. So So you can get unbounded polyhedra with arbitrarily many vertices, and nevertheless, any shadow will show at most 6 of the vertices. And this is an artifact of this Euclidean proof which uses central projection from a sphere. And so it only sees a hemisphere. The projection only sees a hemisphere, and you can get it, you can find such a projection for a bounded polyhedron that will fit in the hemisphere. But for an unbounded polyhedron, it will always be bigger than the hemisphere, and you won't be able to see it all. And that has a kludge that allows you to get a construction that's not convex around the outside. So convexity fails in that more general situation. So this talk, these are the concluding slides. In this talk is about shadows, or in general about things occulting other things. So here is the famous Zen Buddhist rock garden, which is famous in that, among other things, from the veranda there are, I think, 13 or 14 rocks here. It's arranged so that you can never see all the rocks at one time on the veranda. Always there's one rock that will be obstructing one of the other rocks. Now, shadows do the same thing. You do not see the vertices interior to the shadow. You only see the vertices on the outside. The end. This topic of shadows illustrates ars longa vita brevis. Thank you for your attention.
Many thanks. Any questions?
Do I think that Dürer was a true mathematician? Well, I think he was mainly an artist, and he also knew, he was interested in very many things, and I would say he was more an artist, that certainly his orientation was more as an artist as a mathematician, but he certainly was extremely interested in mathematics. He studied mathematics, and he wrote mathematics. So in that sense, he was a mathematician. But I wouldn't want to argue with all the art historians claiming him as a mathematician over being an artist by any prospect.
Any other questions? Well, thank you very much again. Now, Professor Stanley is going to do the next lecture.
How do I get this off?
Do we need to?
I didn't do anything with it.
Somebody take it? I don't. Did the other presenter take it? He has it. Oh, but we have to plug this in.
Ah.
So did you take his?
That's his.
Yeah.
So can we put that to the other side, or
Did you put this on to the?
right now
the
it's being projected right from the disk.
Yeah, I see it. Thank you very much. Let's put his presentation on the computer itself.
Okay.
So that way it's Dürer
I don't know if he needs
PDF. Is it?
PDF. Yeah.
Okay, should be fine though.
Let's make sure it'll go all. Oops. Away.
No, that's a different one. Oh no, that's okay.
That's
right.
him. Yeah. View. Full screen. All right. So.
All right.
I should, okay. Okay, well, traditional magic squares, such as the type that appear in Dürer's engraving, have many elegant, ingenious, and beautiful constructions, but there's really no good theory that involves all of them, or no nice structure that involves all magic squares. And if we want to develop a sort of more unified theory of magic squares, we have to really weaken the definition of magic squares. So we could call these magic squares of the third kind. This is what I'm going to be discussing in my talk. It'll be an n by n matrix, such that every line sum, that is, by line sum I just mean rows and columns. It's a matrix of non-negative integers for every row and column sums to R. That's the only condition. Nothing about diagonals or distinct entries. So there's no longer any interest in constructing them. Here's an example where n equals 3. N is the size of the matrix, and R is the line sum, or row and column sum. And even more trivially, the matrix of, say, all 2's would be a magic square. So it's not such a challenge to find them, but we want to put some kind of structure on all the magic squares of a given size. So we want to understand them well enough so that we can say something about this basic question: how many n by n magic squares have line sum R? So we want to count all of them. So we'll call this number Hn of R. I put n as the subscript because we're going to think mainly of as n as fixed, and we want to let R vary. The size of the matrix is fixed. So for instance, Hn of 0, well here I'm fixing the line sum to be 0. So that's 1. The all zeros matrix is the unique matrix whose rows and columns sum to 0. There's an example. Now let's look at 1 by 1 and 2 by 2 matrices. They're very easy to do. If we have a 1 by 1 matrix whose rows and columns sum to R, then it's this matrix with one entry R. And so H1 of R is 1. And 2 by 2 is not so much more difficult. Let I be any number between 0 and R. That'll have to be this entry up here in the upper left-hand corner. But that forces, because the row and column containing I, those numbers to be R minus I, and then this has to be I again. So there's one matrix for each such I. There's R plus 1 choices of I. And so H2 of R is R plus 1. Well, I said I'm mainly interested in fixed n, but it's important to understand the case where R equals 1, because these are going to be the building blocks, as we'll see, for arbitrary magic squares. So R equals 1 means that every row and column of our n by n matrix sums to 1. So that means there's one entry in every row and column that's 1, and all the other entries are 0. These are just so-called permutation matrices. We can choose in n ways where to put the 1 in the first row. Then in the second row, the 1 cannot be in the same column, so there's n minus 1 choices. And similarly, in the third row, there'll be n minus 2 choices all the way down to the last row where we have 1 choice. And so Hn of 1, the number of n by n magic squares with line sum 1, is n factorial, the product of the integers from 1 to n. The number of permutations of n objects. Well, I'm going to be expressing a lot of these formulas in terms of binomial coefficients, so let me quickly review them. If we have integers 0, less than or equal to k, less than or equal to n, I will define the binomial coefficient n choose k. I'll just define it by this formula. N times n minus 1 down to n minus k plus 1 divided by k factorial. Of course, many of you know that this would count the number of k element subsets of an n element set. Well, notice if we let k be fixed, then n be arbitrary. For instance, n choose 2 will be n times n minus 1 over 2. That's just a polynomial, quadratic polynomial, 1/2 n squared minus n. Or we'll also be looking at binomial coefficients like n plus 2 choose 3. Right? That's n plus 2, n plus 1 times n divided by 6. That's a cubic polynomial, polynomial of degree 3. So in general, n plus I choose k will be for fixed I and k will be the polynomial of degree k, or n plus j choose k. Thinking of n as varying and j and k as fixed, polynomial in n of degree k. Okay, so now let's get serious and use a real mathematical result, the so-called Birkhoff-von Neumann theorem. Garrett Birkhoff proved this in 1946, and then independently von Neumann gave a very elegant proof in 1952. Any n by n magic square in this very weak sense that I've defined them, whose row and column sum is R, is a sum of R permutation matrices. Of course, these will be n by n permutation matrices. So this is the Birkhoff-von Neumann theorem. It's not so obvious. why that should be true. So here is an example, 3 by 3 magic square with line sum 3. This should be the sum of 3 permutation matrices, and this is one way to do it. So these permutation matrices are the building blocks for all magic squares, because every magic square is a sum of them. So now let's try to use this to count 3 by 3 magic squares with line sum r. Well, it's going to be a sum of r 3 by 3 permutation matrices. There's 6 3 by 3 permutation matrices. So if all these sums of these 3 by 3 permutation matrices were all distinct, then, well, this is a very basic combinatorics question. How many ways can we choose R of these 6 matrices allowing repetitions? And that's just the binomial coefficient, R plus 5, choose 5. So if all the sums were distinct, we would get this for the number of these magic squares, H3 of R. But there's a relation among them. They're not all distinct. We have the sum of these 3 equals the sum of these 3, which happens to be the all ones. These two sums are the all ones matrix. So the all ones matrix can be represented in 2 ways as a sum of permutation matrices. So this sort of naive estimate is too big. We have to subtract off the consequences of this relation. Now, we'll call a relation like this among these permutation matrices a syzygy. This comes from this Greek word susugos, which means yoked together, applying to oxen. So it means they're connected in some way. It's also used a lot in astronomy to denote 3 heavenly objects, usually planetary bodies in our solar system, that are in a straight line. So this picture shows the Sun, Venus, and the Earth in syzygy, right? A syzygy between these 3 objects. It's some kind of special relationship that holds among them, and the 19th century mathematician kind of generalized this to these other kinds of relationships, like between these permutation matrices. So this syzygy that we found between the 6 3 by 3 permutation matrices, that the sum of 3 of them equal the sum of another 3, means that we get an overcount. And it turns out, to compensate for that relation, to subtract off the matrices that have been overcounted, we have to subtract, well, the number of, this other binomial coefficient, R plus 2, choose 5, the number of 3 by 3 magic squares which have all their entries positive, so that they have we can subtract a matrix of all ones from them, still get a magic square. And so, when we do this subtraction, we'll get this polynomial, a certain 4th degree polynomial. Or in fact, we can factor it a little bit into 2 linear polynomials and a quadratic. Now, it turns out that there's no further syzygies that is not a consequence of the one I wrote down previously. And so this is the end of the story. That is, this is the correct formula for H3 of R. And this result, the determination of H3 of R, was first accomplished by Percy Alexander McMahon around 1916. He developed this general method for solving lots of similar kinds of problems, which he called the syzygetic method. And this theorem of his was, I guess, the first real theorem on this function hn of r, the case n equals 3. I could mention McMahon is also was the author of a 31-page booklet called Magic Squares and Other Problems on the Chessboard in 1901. And here is what he looks like. McMahon did a lot of work in combinatorics, very excellent work, which is not really appreciated until after his death. Well, what about arbitrary size, n? Well, basically, just based on this result of McMahon for n equals 3, in the trivial cases n equals 1 and 2, Anand, Dürer, and Gupta in 1966 came up with this conjecture that hn of r is going to be a polynomial in R. The degree of the polynomial will be n minus 1 squared, and they can even say something about the zeros. It has, the polynomial is, well, since it's a polynomial, we can evaluate it at negative integers, even if they don't have any direct combinatorial significance. And the values at -1, -2, up to -n plus 1 are going to be 0. And they also conjectured this symmetry property. hn of r is -1 to the n minus 1 times hn of -n minus r. So here's h3 of r rewritten, and you can check that it satisfies this conjecture. It is a polynomial of degree 4, and it vanishes at -1 and -2. That explains these two linear factors. And then you can check it also has this symmetry property. So let's try to do this sysagetic method for 4x4 magic squares. So we start out with a 24 4x4 permutation matrices. If there are no relations among them, then this n should be an R, but we would get R plus 23, choose 23 R by R magic squares. This is a polynomial of degree 23. But, of course, if there's relations for 3x3s, there's going to be some for 4x4. And in fact, it's quite a bit more complicated. There's 178 independent syzygies among the 4x4 matrices. So we can subtract off all of the ones that we've overcounted due to that, but it's worse than this because these syzygies have relations among them. They're not independent. There are relations among these first-order syzygies are called second-order syzygies. There's 1,837 of them. But the second-order syzygies have relations. 7416. Then you can go on. 1644 fourth order. It's not, it just looks like it's blowing up, and there's a priori there's no reason why this process is ever going to terminate. You know, it just doesn't look like a very good method. Anyways, at the next step, there's 25,144, 35,562, 42,204, and this. Then finally, at the 14th step, there's one relation, and that's the end of the story. So that proves, essentially, that the number of 4x4 magic squares with line sum R is a polynomial in R, because each of these syzygies just introduces some binomial coefficient correction. So we get these sums and differences of binomial coefficients. Well, I should say, I've given a very informal, not really even a definition, but discussion of these, what higher order syzygies might be. If you really want to do it rigorously, you have to use the language of commutative algebra. which I will not get into. But in 1890, David Hilbert, one of the greatest mathematicians of the first part of the 20th century, proved his famous syzygy theorem, which implies that, in particular for magic squares, that this syzygy process will come to an end in at most n factorial steps. So for 4 by 4, and at most 24 steps. It actually took 14 steps, but Hilbert would give a bound of 24. So that is enough to prove that these functions, Hn of R, are indeed polynomials in R. Well, actually, there's a little bit of problem if the order of the syzygies is too high. It only gives us for R sufficiently large, and you need a little bit of extra arguing to show it'll hold for all R. But essentially, this syzygetic method does prove that Hn of R is a polynomial. Now, there's more sophisticated results in commutative algebra that came after Hilbert, like the theory of Cohen-Macaulay rings and this Ausland-Buchsbaum theorem and the depth of modules. And as a consequence of this work, that this chain of syzygies for n by n magic squares actually takes exactly this many steps, n factorial minus n squared plus 2n minus 2. For n large, it's just a little bit less than n factorial, so it's a huge number of steps. For n equals 4, we'll get 14. For n equals 3, this is 1, just one step. So here I've repeated the number of syzygies at each step for n equals 4. 14 steps. And, well, it's not at all clear what these numbers are. And in fact, nobody knows a simple way of describing them for n by n magic squares. This Hilbert syzygy theorem does not really give much insight into the actual value of these numbers. But there's one thing you can easily see from these numbers is their symmetry. Right? You read the same backwards as forwards. This sequence is palindromal, 1, 178, 1837, and same in the other direction. So why is this? Well, one can show that this holds, again, for all n by n magic squares, these numbers of syzygies at each step will be a palindromic sequence. And the basic reason for that, and go through all the commutative algebra that's behind this, is the following. Let's J be the n by n matrix of all ones. Then if M is an n by n magic square whose row and column sums are R, then that's true if and only if M plus J is an n by n magic square with positive entries in row and column sums R plus M. It turns out that if we take these numbers of syzygies, if we read them in the opposite order, they would turn out to be the numbers of syzygies for figuring out how many n by n magic squares there are with positive entries. But because there's a simple relationship between the ones with positive entries and arbitrary ones, just add one to every entry to get positive entries. The sequences are the same when we read them backwards and forwards. In more sophisticated, commutative algebra language, it means that a certain ring that's associated with this problem is a Bornstein ring. Now the symmetry result is exactly what you need to deduce. If you see what effect that has on the actual polynomial, it implies the rest of the unknown Dürer-Gupta conjectures that the value of the polynomial minus 1, minus 2, up to minus n plus 1 is 0, and the symmetry property. Now this is, well, okay, I'll come to that in a second. Let's see, what if we wanted to do 5 by 5 by this method? 5 by 5 magic squares. Well, one can show that the number of syzygies, the total number of them using this method, is at least 5.7 times 10 to the 34th. So I don't think anybody's ever going to explicitly figure out what these syzygies are. And kind of never know the exact number. According to some website, this is a key to forbidden knowledge. Now let's look at, there's another interesting, completely different approach for trying to compute the number of magic squares. And let's put them in a canonical form. So it turns out that every 3 by 3 magic square has exactly one of these 3 forms, where A, B, C, D, and E are non-negative integers. So for any 3 by 3 magic square, there are unique values of A, B, C, D, and E. And a unique choice of one of these 3 forms, which gives that magic square. Well, this is something that if you stare at this long enough, you can see why that is the case, although it does take a little bit of thought to see exactly what's going on here. But for instance, just here, in this first magic square, this 1, 1 entry of the matrix is greater than or equal to the 2, 2 entry, because we've added this non-negative integer e to A. While here, we've added e plus 1 to the A in the 2, 2 place. So this number is strictly greater than this. So these two were just joint. At least that proves there's no overlap between these 2 types. Some more work, you can see why you get every one exactly once. And this gives a different kind of way of writing this number hn3 as a sum of binomial coefficients. We just have to get these matrices to add up to R, have lines on R, we just have to choose A, B, C, D, E to add up to R. Very elementary combinatorial problem. How many ways can you choose 5 non-negative integers whose sum is R? Here, since we have this plus 1, we have to choose A plus B plus C plus D plus E to add up to R minus 1, because each line sum is A plus B plus C plus D plus E plus 1, and here they have to add up to R minus 2. So we're going to get this sum of binomial coefficients for H3 of R. Another way of writing this same polynomial, R plus 4, R plus 4, etc. Although, so, can some kind of thing like this be done for any size, n by n? Getting the canonical form of these types so that the number of each in each class is some simple binomial coefficient. And it turns out that this is possible to do for any n, and this is proved by a geometric argument using the theory of shellability. Now this actually gives a more elementary proof that Hn of R is a polynomial. You don't need this commutative algebra in Hilbert-Syzygy theorem. Machinery, the geometric machinery of shellability is more elementary. We have to regard, I made a little typo here, but we regard the n by n magic square as lying in n square dimensional vector space, because it has n squared entries or coordinates, r to the n squared. So it's some kind of geometric object in n squared dimensions. And that's the kind of geometry that comes into this shellability picture. Well, by 4x4 magic squared, what will happen if we try to do this technique? Well, the number of 4x4 magic squares is this linear combination of these binomial coefficients. That means that this Schelling technique, well, there's 352 binomial coefficients, and all that is the sum of these red coefficients is 352. So that means there's going to be 352 cases for the 4x4 magic squares. Like there were 3 cases here. For 4x4, there's going to be 352. And I don't think anyone has ever written them down explicitly, or there's any real point in doing so, but we know that is possible. For 5x5, the number of different cases is over 4 million. Now, these red coefficients also have the symmetry property, 1, 14, 87. They're the same backwards as forwards. This turns out to be equivalent to the symmetry exhibited by these numbers of syzygies. So this would give another explanation of the symmetry of these polynomials and why they vanish for certain values. Now, there's another property that these coefficients have that in these in this kind of formula, when you use these kinds of binomial coefficients, and you break it up into these different disjoint cases, namely, not only are these numbers symmetric, but they're unimodal. They increase and then decrease. Well, since they're symmetric, that means they have to increase up to the middle and then decrease. 1 plus equal to 14 plus equal to 1 to 87 plus equal to 148. You know, it turns out that this unimodality property is true for any n, and it's maybe the deepest result known about this polynomial Hn of R. It really is a very high-powered machinery. If you torque varieties, intersection homology theory, Hard-Lefschatz theorem, you have to study for many years to understand these topics. Well, we can consider some variations of this problem of counting n by n magic squares. For instance, we could look at symmetric magic squares. These are just symmetric matrices of non-negative integers whose line sums are R. So here's an example. The line sum is 8. It's a 4x4 matrix, and it's symmetric. It's equal to its reflection about the main diagonal. For instance, this diagonal here is symmetrical, a palindrome. All the other diagonals parallel to it. So let Sn of R be the number of these n by n symmetric magic squares of line sum R. Well, it's not a polynomial. S3 of R is a certain polynomial in R for R even, but it's a different polynomial for R odd. The difference is pretty small, only in the constant term here, but the previous argument proof breaks down. You remember it was originally the syzygetic method. It was based on this Birkhoff-von Neumann theorem that every magic square was a sum of permutation matrices. It was the fact that the permutation matrices have line sum of 1 that made the thing a polynomial. For symmetric magic squares, the correct theorem is that for any n, there are two polynomials, Pn of r and Qn of r, such that Sn of r is Pn of r and r is even, and Qn of r and r is odd. So, exactly what happens here. Now, why are there two cases, r even and r odd? Well, if we're going to be a polynomial, the proof that we used before Burkhoff von Neumann went through, it would have to be the case that every symmetric magic square is a sum of symmetric permutation matrices. That's just not true. Here is a symmetric magic square. It is a sum of two permutation matrices, but those permutation matrices are not symmetric. However, what we do have is that twice every symmetric magic square is a sum of symmetric magic squares of row and column sum of 2. So this 2 here is not important for the argument. It could be any number here. It's this 2 that's really essential. The building blocks of the symmetric magic squares have line sum of 2. That means it's going to be essentially two kinds of polynomials for n even and n odd. And actually, it's easy to see this if you know the Burkhoff von Neumann theorem, because we know that our symmetric matrix M can be written as a sum of permutation matrices. So 2m, well, m is symmetric, so it's equals its transpose is the same as m plus m transpose. And so we can just transpose, so m plus m transpose is p1 plus p1 transpose up to pk plus pk transpose, and these pi plus pi transpose is a symmetric magic square with line sum of 2. So that proves this assertion at the top. And it's the fact that these building blocks have line sum of 2, which means there's going to be these two cases. Okay, now we can look at many other variants. Let's consider, for instance, following the first lecture this morning, n by n magic cubes. And now, again, I mean in this weak sense, the lines just mean orthogonal lines, rows, columns, and pillars, you could say. They should sum to R. The entries are non-negative integers. What's going to happen here? Well, there's no analog of the Burkhoff von Neumann theorem. And there's no trick like we use for symmetric magic squares to get some multiple of these magic cubes to be sums of small magic cubes. The best we can do is using some very general result, having to do with AR polynomials of any rational polytope, say. But this general theorem implies that for any n greater or equal to 1, there is some p, depending on n, and now we have p polynomials, tn 0 up to tn p minus 1, such that INR, the number of these magic cubes of line sum R, is this polynomial, the ith polynomial tn I of R, if R is congruent to I mod p. Or in other words, if when you divide R by p, you get a remainder of I. So for ordinary magic squares, the value of p was 1. We had just one polynomial. For symmetric magic squares, 2. But for magic cubes, this is the best that's known. It's just there's some p, and it's not known what this p is. Here it is for the 3 by 3 by 3 case, which is the only, well, the biggest case that's been computed. It's beyond our computational ability to do 4 by 4 by 4, even though there's some very sophisticated computational methods for doing this kind of thing. This still cannot handle 4 by 4 by 4 cubes. So here p equals 2, so there's going to be one polynomial for r even, which is this nice looking polynomial of degree 8. And for r odd, it's very similar, only the last two terms are different. Instead of 10032r plus 4480, we get 8142r plus 1645. Okay, a little bit early, but I have come to a sad part of my talk because it's the last slide. Thank you. Right. Yeah. No, I would say yes, there's a very good algorithm for doing that, connected with finding matchings and bipartite graphs. But it's true, there's a polynomial time algorithm for finding such a decomposition, or just given any n by n matrix. Well, just given any set of entries of an n by n matrix, do those entries contain some permutation matrix? That can be done in polynomial time. Well, the number of conventions, you want to know if there's some multiple dimensional integral which will give the number of conventional matrices, I mean all the entries distinct. Go. Yeah. Right. Well, if you just wanted to count, that would be another variation I didn't discuss. If you just wanted to count these weak kinds of magic squares, but also have the diagonal sums this equal to r, then again by this very general theorem, you get the same behavior. That the function is going to be a polynomial on congruence class is mod p, but again it's not known what p is. And presumably p is going to go to infinity as n goes to infinity, but that's not known. Now, if you want the entries also to be distinct integers, you can also put that into the picture and get the same kind of behavior because you have linear inequalities. You just say some entry doesn't equal this something. But if you want them to be all the integers from exactly 1 to n squared, that is completely traditional magic square, then that's a really very special situation, and it doesn't really fit into this theory.
Thank you very, very
Yeah,
much.
thank you.
VGA.
Oh, I understand. Okay, sure. So just swap the VGA.
Is this working? Yeah, you can tell it's fine. Okay, this is actually the first time I've lectured from a wheelchair. I've had increasing difficulty walking. Last night it was raining and I was stepping in rivers, you know, by the curb and everything. Today, this morning, I found walking much harder than I've ever felt it before. Anyway, doubtless I'm going to be using wheelchairs many times in the future. I'm going to talk really about magic squares, and in particular the magic square that appears in Melancholia 1, Dürer's magic square. I'm going to talk about the history of magic squares before Dürer's time. They seem to have been an Eastern discovery. There's a legend in China about the magic square of order 3. The order is the width of the square, you know, which is called the low shoe. It's unique up to symmetry. And let me draw it for you. Let me see how close I can get to this. I'm going to put the numbers in. Sorry? Oh, okay. I'm going to draw the low shoe. Now, there's a tradition, by the way, there was a tradition of naming the magic square of order 3 after Saturn, either the god or the heavenly body, the planet. I think, I won't say heavenly body, it sounds so sort of heavenly and bodyish. I'll say planet. The word planet originally just meant wanderer in the sky, as distinct from the fixed stars. And the moon and the sun were called planets in particular. They're both wanderers. They don't stay in the same place against the stars. So if we use that old-fashioned interpretation of the word planet, we get a nice short name for them. And the traditional, well, anyway, the unique magic square of order 3 is associated with Saturn, traditionally. All the old authors say, we do this, but we don't know why. For 4x4 it's with Jupiter, 5x5 with Mars, 6x6 with the Sun, and so on. Now, you notice, really, the Sun sort of swaps with the Earth. We now think of the Earth as going around the Sun, but, you know, this adopts a geocentric viewpoint. You're looking at these things against the sky as seen from the Earth. And this ordering is the descending order of the period of the object. Exactly which period is a little bit hard to say, synodic or, you know, sidereal or whatever. It's basically, it doesn't matter which period you take, except for the rather funny fact that the Earth and the Sun get swapped in this convention. And there's an intriguing connection with the names of the days of the week, which I'll say later. So here we go. The method I'm going to use here is what I call the step-up or drop method. What I now call the step-up or drop method. If we step up from here, we get to that place there. We go outside the square, but we transfer it. You know, we view the square as next to lots of copies of itself on either side. So once I step up here, I'm stepping up to there. But now, I can't step up from place 3 for a different reason. I'd step on top of somewhere I've been before. So I drop. Step up or drop. Here I can step up. Here I can step up. I can't step up here, I would get to the 4. So I drop. Then 8. 9. So I'll just draw these two vectors. That's step up, and that's drop. And this is your first priority, and this is your second. So I'll put a double arrow there. That's the unique magic square of order 3. It's usually given the name the low shoe. There's a story, there's a Chinese emperor was sitting on the banks of the Yellow River. It's called the Yellow River because of some yellowish mud that gets mixed in with it, so it actually is yellow. And a turtle rose from the river with this pattern carved on the back of it, not using these digits, of course. And then the emperor noted it down and then took it back home to his palace and asked his wise men about it and so on. How much truth there is to that story, one doesn't know. Now, the step-up or drop method works for any odd size, any odd order. I'm going to illustrate it. Now, I'm going to illustrate it next with the 7 by 7, which traditionally they associated with Venus. You start at the middle of the top row, step up when you get to here, step up. Oh no, oh. 2, 3, 4, 5, 6, 7. When you do it with a really big number, you suddenly realize what the times you have to drop are. That when you've just passed, in this case, a multiple of 7. 8, 9, 10, 11, 12, 13, 14. We're going to drop now, and so on. Well, I won't bother writing the whole thing, and you can see the method very easily. There are lots and lots of methods for odd order magic squares, and I discovered in an old book, in a century-old book, about 10 years ago, the one that I like most, which I call the odd diamond method. And it's very nice. I wish I could find the book in which I discovered this odd diamond. Okay, I'm going to draw the diamond in here. I take the midpoints of the edges of the square and join them like this. And now I fill in the numbers here. 1, I'm going to draw them sideways, it's much easier for me, I mean diagonally slanting. 3, 5, and then keep on, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25. I think it's beautiful that all the odd numbers arrive in the middle of that diamond. Well, now it's going to be a bit of a mess, and I don't want to overlap the other parts of this thing which have various other sizes marked on them. I'm now going to continue with the even numbers on a diamond that goes up here. Okay, I'm not drawing this all. So what were the even numbers? I missed them out before. It's now 2, 4, 6, 8, 10, 12, etc. 12, 14, 16, 18, etc. I mean, so I fill out the odd numbers and then I transfer them, so to speak, into the square. So here I have 2, 8 and 4 at the top, and I transfer them to the bottom. If you're really clever, you can do it without setting up this initial square here. And it's really rather nice. All the odd numbers arise in the central diamond and the even numbers outside it. And, you know, it looks nice, I think. especially if you've been accustomed to drawing the odd numbers in red and the even numbers in black or something. That works. I wish I could find out the book in which this happened, in which I read this. It was published about a century ago. I don't quite know how about is, maybe 10 years, from 1910 or 20 years from 1910. It was by a bunch of enthusiasts for magic squares. About 7 or 8 people had articles in it. It was reproduced from typewriter script, quite early for something to be reproduced from typewriter script. And I've not seen it anywhere else. And, usually I have seen anything about recreational mathematics, quite a lot of times, and I've only seen this in one particular place. So that's the odd diamond method. Well, now I'm going to switch to even order magic squares. Unfortunately, they're not so easy to write out unless the square is what, or the order is what we call doubly even, meaning it's a multiple of 4, sometimes called evenly even. And there's a nice method there, and I'll come back to it when I discuss how Dürer probably found his square, or at least possibly found his square. Magic squares came from the East, as I've mentioned. Dürer's is really quite early. There are 1 or 2 more in Western Europe before his day. In particular, a man called Moscovici wrote about magic squares. But I feel that Dürer was still remarkably early, at 1514. Okay, well, I'm not going to give you Dürer's square just yet. I'm going to give you instead what I call the crisscross method, which works for doubly even squares. What we do is write the numbers in order across the square, except that I'm going to do 2 passes. First I'm going to do the squares that are not crossed out, and then I'm going to do the ones that are crossed out. So in the first pass, I say 1, but I don't actually write it. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. And then I'm going to, on the second pass, I'm going to do the numbers I missed out in crossed out squares. So now I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's the crisscross method. Well, it isn't, that's only for an order 4 square. For an order 8 square, or any multiple of 4, I would do the same thing, except that each 4 by 4 subsquare, I would draw this crisscross in. And then I write the numbers from 1 to 64 in this sort of same method. 1, 2, 3, 4, 5, 6, 7, 8, etc. All the way down, and then I would go back 1, 2, 3, 4, back all the way again. Oh, by the way, of course, it would land up at 62, 63, 64 in the first pass. And that will give you a square of any doubly even order. Singly even orders have been a great bugbear. It's tremendously hard to sort of dream up a rule that is fairly simple and that will do all singly even numbers. Of course, I addressed my mighty mind to this problem and eventually found a rather nice rule. Is this 10? Yes, this is 10. Oh yes, let's talk about the days of the week for a moment. What's this ordering? This ordering is by descending order of dignity. Saturn takes 20-something years to go around the Sun, or equally to go around the Earth. It's the most dignified planet. And then Jupiter is the next one, Mars the next one, and then the Sun is the next one. Really the Earth, but we call it the Sun. And then Venus, and then Mercury. Mercury takes 88 days, Venus takes 200 and something days. And then the Moon takes 30 days, about. And then, if you want to go up to, the Moon is the one traditionally assigned to 9 by 9 magic squares. And they didn't assign a planet to 10 by 10 magic squares. The first thing that did that was Sputnik in 1956 or 7. And so we've assigned the name Sputnik to 10 by 10 magic square. So I'll just start off a 10 by 10 magic square. This is a rule I found myself, but I sort of copied it from a rule of a person called Strachey, I think Christopher Strachey, in Rousebull's Mathematical Recreations. Rousebull says that Strachey wrote to him in 1919, giving his rule. I sort of turned it inside out and given a mnemonic for it, and you might not recognize it as the same rule. If you're interested in these things, I should advise you to look at Strachey's rule and see if you can see what I've done to it and why this one is the same. I call my rule the Lux rule. So we have this rather stylized L. I divide my 10 by 10 square into a 5 by 5 square of 2 by 2 squares. And in each of the 2 by 2 squares, I put either that stylized L, or the U, or the X. And they tell you how to put 4 consecutive numbers in the appropriate square. And I'm going to do the step up or drop method on the 5 by 5 square. And, well, let's just do it. I don't see any better way of explaining it than to do it and watch. So I start at the middle square of the top row. You may remember that instruction. But now I'm putting 4 numbers in there. 1, 2, 3, 4, the first 4 numbers. And then I step up and I get to up here, which is down here. And then I fill in the next 4 numbers. 5, 6, 7, 8. Across means, well, I hope you see what it means. Then 9, 10, 11, 12. Now I'm stepping up still, and I get to this left-hand side here. 13, 14, 15, 16. Those L's should really have a sort of extra little piece going back, 1, 2, 3, 4. But then I couldn't call it the Lux method. 13, 14, and then I'm stepping up from here to 17, 18, 19, 20. Now I can't step up, so I drop 21, 22, 23, 24, dot, dot, dot. And the last four numbers, which will be 97, 98, 99, 100, will go here. 97, 98, 99, 100. I'm not going to fill in all the 100 entries. If you want to, you can do that yourself. Okay, so I've given you now at least one method to write a magic square of every possible order from 3 upwards. There is no magic square of order 2, as several people have remarked already today. A magic square of order 2 with the integers from 1 to 2 squared. And the magic square of order 1 is actually done by the step up or drop method that you don't actually get around to dropping any time, or stepping up, come to think of it. So that's that. Have I got some blank paper here? I've got some, yes. Well, this will do. Okay, so I'm going to pause and say something that's got no connection with magic squares, no connection with Dürer as far as I know, but it's very interesting. It's this. Let's draw a circle here. And now I'm going to divide it into 7 parts, roughly equal. Now I'm going to put the names of the planets in the order of dignity that I just mentioned. And here is Saturn. And after this we have Jupiter coming in basically towards the Sun, except with this funny thing. This is Mars. Here is the Sun. Remember, it's in a sense that the Sun and the Earth have swapped places. And then here is Venus. And here is Mercury. And then here is the Moon. Now these magic squares are not the only things that have been named after these things. The ones that we know are the days of the week. Well, here I have to swap between languages a little bit because the English names for some of the days of the week after the long weekend are the Scandinavian equivalents of the Greek and Roman gods mentioned here. So watch. Saturday, Sunday, Monday, Mardi, Mercury, Jeudi, Vendredi, and back to Saturday. We get this, well, it's not very well drawn here, but it's a rather nice 7-pointed star. How does that happen, you ask? I hope you're asking. Well, it's very interesting how it's happened. At least this is the traditional story of how it's happened. It is that each hour of the 24-hour day was devoted to one of these planets, let's say, or deities. So if the first hour of your day is devoted to Saturday, then 24 hours later, what has happened? You've gone 3 times round the whole circle, okay, which gets you to 21 hours, and then 3 more hours left over to get you to 24. So that explains why the days of the week are in this really rather peculiar order. You know, when you know that they're named after gods, you've got more to say. Why are they in the order that they are? In the English names, we have this rather funny thing, and I don't quite know why it happened or how it came to happen. The names, well, the sun and the moon. Let me go in the order that we know of the days of the week. Sunday, Monday, they're pretty obvious. But I want to say there was a long weekend because Saturday, Sunday, Monday are named after the Roman or Greek gods. And then we switched to the Scandinavian ones. We have Saturday, Sunday, Monday, Tuesday, T-U-W, Tuesday, Woden's Day, what's this, Thor's Day, Freya's Day, and then back to Saturday again. So for some reason we switch. We have a long weekend of Roman gods, who are immediately derived from the Greek gods, not much difference between them. And then suddenly we go all Scandinavian and have the other ones. I think that's a very interesting little thing. Now, what was I going to say? Have I said everything? I can't have said everything. Oh, yes. Sorry? Yeah, that's good. Thank you for putting me on the right thing. I don't know how Dürer is square. But I have a theory as to how Dürer is square, because it is very nicely related to the crisscross method. I'm not sure that this can be how he got it. I really don't know how old the crisscross method is, but Dürer square, just got to find another piece of paper. Here is oh, wait a minute, I ought to have my crisscross square somewhere. Now here's the crisscross square. Oh, this is good. Never mind. I've got beautiful. I've got enough space. Yes, here's the crisscross square. Yes, I know, but I want to have it on the slide. I don't think I'll use transparency. So I'll outline in the middle of this 6 by 6 square enough space for a 4 by 4 square, which will turn out to be Dürer's. If you look at this, 14 and 15 are in the wrong order. He wants 15, 14. That's why we're celebrating the quincentenary in 2014. So you can just interchange these two middle columns. And so let me leave the columns on that I'm not going to mess up. 16, 5, 9, 4, and 13, 8, 12, 1. I'm sorry, I've not got such good motor control. Every now and then my numbers come out terribly. So I'm now going to just interchange the middle columns. So instead of 2, 3, I have 3, 2. Instead of 11, 10, I have 10, 11. Instead of 7, 6, 6, 7. And instead of 14, 15, 15, 14. And then Dürer neatly outlines those. And this is actually Dürer's square. So it could have been obtained this way. However, I don't quite know why Dürer should do it that way. It's not obvious that interchanging the middle two columns of a magic square gives a magic square. The condition for that, so to speak, you see, the rows and columns stay the same in a way. They're differently ordered, but the two diagonals might have got messed up. But they don't get messed up because 7 plus 10 is the same as 11 plus 6. So it doesn't matter if we do that. So maybe that's what Dürer did. I think it would have been simpler if I had been Dürer. What I would have done is just reflect the whole square left to right. That's that. Anyway, there's a little theory about how Dürer selected his particular one. And if you have a better one, then you're free to give it. I think I'll finish early since I seem to have run that. Somehow, normally this is not the problem that faces me or anyone else. Namely, well, I used to tell my students always, when they were going off to give talks, possibly to get a job, carefully prepare whatever you're going to say, write it all down, and then divide it by 4. And then, moreover, it only gets improved if you divide it by 4 again, and eventually, when what you're going to say will fit on, slightly more than a postage stamp, you've got about the right amount of material. Otherwise, you're going to be ending up, going at the end of your lecture. I seem to be short of material now, so I'm almost going to stop. But I am going to tell you a story first of my friend Alan Baker, who got the Fields Medal at the Nice Congress quite some time ago. And he was very nervous of how to give his acceptance lecture. And so he asked, could he come round to my hotel room, which was next to his hotel room, and give me a version of the lecture on the night before. So he did. And as he had beautifully prepared slides, and as he put his slides down, I asked various questions, and so on. And it went wonderfully. And we were assured he would get through in time. And then on the day, next morning, the following thing happened. He slammed a slide, one of these transparencies onto the machine, and said this and that and the other very quickly. And before anybody could absorb the slide, he whipped it off again. His work involved really, well, typically, you write down something and you multiply it by a polynomial involving a parameter p to be determined, and then you differentiate it k times, where k will be determined later, and then you do something else, Really rather complicated stuff. But you just had about 10 seconds to see this described on the thing. And I was sitting near the front and trying to catch his eye and get him to slow down. But he was so nervous, he never looked up at all. So he never succeeded in slowing down. And then he got to the end of his lecture, and it was about 20 past the hour. And he looked up, and he saw the clock, and his face fell. He didn't know what to do. I would have ad-libbed and told a few jokes and so, which I'm doing now, roughly speaking, and fine. But Baker didn't. I mean, he wouldn't do that. He didn't know how to. And then he had a brilliant idea. He said, thank you. And everybody applauded like mad. And then as they went out, they said it was one of the best lectures they'd ever heard, which it wasn't. It was just one of the shortest lectures they'd ever heard. And they didn't feel bad at applauding it and so on, because it was about very good mathematics that had got in the Fields Medal and so on. So, you know, they felt virtuous in a number of ways, and they got out to lunch, you know, or whatever it was, you know, a good 40 minutes before they should have done. So, thank you. It wasn't one person. No, it was a bunch of, let's say, 6 or 8 enthusiasts for magic squares who each wrote a chapter. What's the title of the book anyway?
Old Magic Squares course, but he did something with inlaid diamonds. And that's what made me think of Hendrix.
Yeah. Oh, by the way, in the
And he wrote tons of stuff
yeah,
on the DVD that Harvey Hunts produced just before he died,
yeah.
which has got all sorts of stuff from Hendrix on it.
As far as I know, the word diamond does not appear in the book I'm quoting. That was my sort of name for it. But then, okay, thank you then.
But I'll think about it.
Yeah, shout up because. Yeah. Okay. The answer is you put L's in them. Let me find that. Oh, I can never find things. Oh, well, here it is. Here's one. You have, suppose we've got 4m plus 2. Suppose that's the order of our square. Then we have n plus 1 rows of L's, with a modification I'll mention in a moment, and then 1 row of U's, and then n minus 1 rows of X's. This is rather small, so that means that, you know, in our case, 4m plus 2 equals 10 means that n is 2. So, but if you think about this, the n plus 1 rows of L's takes you down to the central row. So you go all the way down to the central row. I still have a modification to make in a moment. You go all the way down to the central row in L's, then have 1 row of U's just below the central row, and then fill everything else in X's, aren't they? But then you, well, this is already outlined them. The central square, the symbols in the central square and the one below it are interchanged. The central square should have been an L, and the one below it should have been a U. And the reason why it works is it's really very easy to check it. You see, you're adding this to 4 times a magic square of half the order, if you understand me. So let's just ignore that. We know that that magic square will be magic. So I'll just write down the differences, which are 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, etc. Sorry, it's rather boring hearing 1, 2, 3, 4 all the time. But Now, you notice that horizontally, each 2 by 2 square has one row 4, 1 and another row 2, 3, or the reverse order, it doesn't matter, but they add up to 5 anyway. So all the rows work. Okay, that's that. And then vertically what happens? Well, the ones outside this 3 by 3 square, oh sorry, 3, 4, the wrong way around. This adds up to 6, which is one, you know, the norm, so to speak, is 5. What it should add up to is 5. This adds up to 6, which is one more. This adds up to 4, which is one less. And conversely, this adds up to 4 and this adds up to 6. So now we see that the columns work everywhere. And now the only things left are the 2 diagonals. And now, in general, if I look at a diagonal entry, I'll draw it rather big here. This is 2 units overweight, this 4, 3. But this which is 1, 2, is 2 units underweight. So the diagonal squares outside the 3 by 3 thing in the middle work. And now you just check that it works here. This is adds up to 7, 4, and 4, which is 15, which is just right, 3 5s. So it's a very easy proof that the Lux method works. I found it very hard when I first saw Strachey's method to check that it did work. It's because, well, it's hard to say what happens. Instead of doing this, for instance, where I have a 5 by 5 square of 2 by 2s, Strachey has a 2 by 2 square of 5 by 5s, and then the cancellations are of numbers that are not near to each other. You know, here I just have to look at numbers near to each other, and I see that this is too high by 2, this is too low by 2. You know. So it's sort of more or less visible as it works. The books, apart from Rouse Ball, that I know of, do singly even squares, which are the hard case, by the bordering technique. You put the middle numbers into the middle. Suppose you're doing an n plus 2 by n plus 2 square, and you already know how to do an n by n one. You put your n by n one in the middle with all its numbers increased so that it uses the middle n squared numbers. And then all you have to do is arrange the things above and below, and, you know, and at the left and the right and in the diagonal places sort of cancel each other. And there's no nice rule for doing that. I mean, it's easy to do in practice, but I don't know a nice general rule, and I've not seen one in any book, although I think I've seen 3 or 4 books that describe the bordering method. They all just say it's easy. And it is. But, you know, I like the assurance. I'm a mathematician. I like the assurance it's going to work, not be told it's easy to do, even if it is easy to do. Okay.
Any more questions? Well, let's see how it
Let me thank you for inviting me and so on. I love the idea of talking at a conference on an artist. Oh, by the way, I'll answer the question that I think somebody addressed to Jeff Legarius. Do I think that Dürer is an artist or a mathematician? Yes.
lavalier, or do you want to just use the microphone right here? Do you want to use the lavalier microphone, or would you rather prefer to use this one?
Yeah, I can use it. I guess I'm probably one.
All right, you can just put this right in my pocket.
Okay. Or here?
Well, you can inside.
Okay. So is there a clock here to see how much I do stand? Oh, no, okay, so it's 25. Okay. Sure. Okay.
You have also a laser pointer if you want. This one is
Yeah.
a pointer, and this one is advanced.
And this one?
This one's
No, the back one. This one?
This one I don't actually know what it does. I would suggest not pushing it.
This one? Or this one?
Yeah, stay away from that. Laser pointer, advanced.
Sure, please.
Okay, it's our pleasure to welcome our next speaker, Professor Klein.
Alright, so the title of my talk is Are Black Holes Real? And first of all, let's make a few pictures. So this is a picture which I got from the internet. So it belongs to NASA. And obviously it's supposed to be a black hole there in the middle, but of course you see only light. So anyway, here is another, something that maybe looks somewhat more closer to what you might think is a black hole, but it's still white. Here is another thing that you believe that there is somewhere in the middle, there must be a black hole. Again, you see a lot of light, so it's not so clear what that means. And finally, you see an object spiraling around something that looks more like a black hole. In any case, black holes, by definition, are not to be seen. And also, from, I mean, you could say, okay, you don't see, but they have effects on other objects around them. But in order to see an object falling in a black hole, it would take infinite time from our perspective. So time in relativity is, of course, as everybody knows, is relative. And even though the object that falls in real time, according to its proper time, it will take infinite amount of time for us to see something falling. It's a well-known redshift effect. So anyway, how do we know that all these things are black holes, since by definition black holes are not to be seen? Right? So that's sort of the thing that I want to talk about, but I want to put it in a larger perspective. In particular, to connect somehow to this beautiful drawing of Dürer, in which, of course, we see a lot of mathematical objects, and you see that that angel who is very melancholic, obviously, which, of course, in the vision of Dürer, it represented sort of the genius looking at the world and trying to understand it, and trying to understand it with mathematical objects. So this, of course, brings you immediately to the Pythagorean and Platonic view of the world, according to which reality should be understood using numbers or other mathematical objects, such as the ones you see here, or the magic square that we heard the beautiful presentation of John. So, from this perspective, so I want to make this broader point, namely that somehow there is, of course, a physical world here, the world of perceptions. Physical world, and there is the mathematical world in the conception of Pythagoras or Plato, and which has sort of its own reality. Reality, of course, it's a reality of consistency, mathematical and logical consistency. Objects in this world have to be consistent with each other. And anyway, you have somewhere here you have physics sort of in between. So physics is sort of a way of translating perceptions of the physical world in mathematical language. So anyway, so we have this kind of triangle between these three things. You can say these three worlds if you want. And of course, the story of black holes sort of fits in this picture, but it's not the only message that you can relate to this picture, because essentially the entire history of mathematics and physics is intimately tied to this. So that's sort of the thing that I want to discuss, and I'll start with a preamble in which I'll talk a little bit about the history of general relativity, just to illustrate exactly this point. Okay, so first of all, the content of my lecture is I'll have a preamble in which I'll discuss the history of relativity, of general relativity, which is, of course, intimately tied to the notion of black holes. Then I'll discuss notions of reality, which is very much like essentially what I already said, but I'll go a little bit more in details. Black holes, I'll define what black holes are. Then I'll talk about three major problems in the theory of black holes, which I claim are intimately tied to the notion of reality of black holes, even though these questions are pure mathematical. So let's start. So first of all, the preamble is a brief intellectual history of general relativity. And I start with geometry. So classical geometry starts as an attempt to find, it's a first attempt, in fact, to find a mathematical description of physical space. So it is a theory of physics, actually. It started from observations. The Dürer theorem, of course, was initially just an observation. And then it grew into this incredible, beautiful body of geometry as we know it, of classical geometry as we know it, and as it was to a large extent formulated by Euclid. Then, of course, you have much later the development of algebra as a framework of symbolic manipulations based on natural operations, so for addition and multiplication. So algebra, as we all know, is just this. I mean, it's just a formal manipulation with this, using these natural operations. So again, there is a connection with reality, but of course all these developments takes place within the framework of mathematics. So same thing as in the development of geometry. It started from observations, but it sort of became an object here, and it developed according to sort of the inner logic of mathematics, rather than having much to do with observation. In fact, for a very long time, geometry developed essentially as an art in itself without much contact back to reality. Of course, another major thing that happened was Kepler's three mathematical laws concerning the trajectory of planets around the sun. And of course, as we all know, it's based on the classical work of Apollonius, which was connected with sort of purely mathematical interest in conic sectors. And Kepler was very mathematical and sort of very mystical, in fact, thought that there has to be, he was very Pythagorean, thought that the motion of planets has to have sort of very simple understanding in terms of mathematics, and he tried many things, but finally he got to this wonderful laws. And of course, they were also based on the astronomical observation of Tycho Brahe, as we all know. So in fact, he had many, as I said earlier, he had many other attempts to do this, but they did not fit the astronomical experiments of Tycho Brahe. And the search actually took, I don't know, 20 or 30 years. Later, in 1637, Descartes writes down his analytic geometry, which is the synthesis between algebra and geometry, which sets the stage for the development of calculus. Indeed, calculus would have been unimaginable without this formulation of Descartes. And calculus, of course, was later developed by Fermat, who introduced the notion of derivative, in fact, Leibniz, Newton, etc. 1687, we have Principia. Calculus allows Newton to derive Kepler's law from the universal laws of gravitation, and thus set the foundations of mechanics. And of course, mechanics is later developed by great mathematicians such as Euler, Bernoulli, Lagrange, Jacobi, Hamilton, and it continues through dynamics, what is called dynamics. It continues to be extremely active area of mathematics, right? So again, you see another example of something that starts from observation. It's taken by physics. Physics, in a sense, it's a synthesis between experiment and mathematics. A mathematical formulation of mechanics is given, and then somehow this is taken within mathematics. It's taken by mathematicians and developed within the framework of mathematics. So it becomes really a subject of mathematics. Dynamics is a subject of mathematics, just like geometry. 1740, Euler, Bernoulli, Fourier-Laplace. So this is a long period of time. 1740 until much later. All these people write down the first partial differential equations. So before the dynamical equations written here were ordinary differential equations rather than partial differential equations. So the first partial differential equations are written as mathematical embodiment of physical laws governing extended mechanical systems, which are typical to continuum mechanics. So fluids, elasticity, and so on and so forth. Magnetofluid, and all sorts of things which are connected with continuum mechanics. And of course, PDE continues to be an extremely active area of mathematics. So the first PDEs are written down, but of course the theory of PDEs is a major part of modern mathematics, with many connections with all sorts of things, geometry, topology, even algebraic geometry, and so on and so forth. Now, Gauss in 1827 writes his monumental theory of surfaces with a modern concept of curvature at its center. So this was, again, in a certain sense, it comes from the inner development of mathematics, but with some kind of experimental interest in mind too, because he was interested in making measurements of geographic measurements on the Earth, and he wanted to find sort of a theory. Anyway, so it's a synthesis between an interest of the physical world and a development within mathematics. Of course, there is much more to say. I'm just going very fast. This is just a very brief introduction to all this. A lot more can be said, but in any case, 1853, Riemann generalizes the notion of curvature to higher dimensions. He also introduces a modern concept of manifold, and of course, you have the birth of Riemannian geometry, which is a great field of modern mathematics. And again, there's another subject which is now pure, you can view it as pure mathematics. 1862, Maxwell translates the empirical laws discovered by Faraday concerning electricity and magnetism. And he does that in the framework of PDEs. He writes down the Maxwell equations. Based on mathematical considerations, he proposes a new law, which was not originally in Faraday, which leads to the new concept of fields. So it leads to electromagnetic waves, I'm sorry. Well, the Maxwell equations, of course, is a fundamental system of equations in modern physics. It also plays a major role in mathematics. It has led to, for example, together with other developments, it has led to the theory of differential forms and Hodge theory. Okay, so Hodge theory is, in fact, a sort of a Riemannian version of the Maxwell equations. So, 1892, 1984, people look at the discrepancy between the Maxwell equations and mechanics. More precisely, Lorentz finds out the invariance property of the Maxwell equations, the so-called Lorentz transformations, which are inconsistent with Galilean transformations. Again, this is sort of a mathematical artifact about the equations. You have one system of equations, you have another one, you look at them, they have different groups of transformations which leave the equations invariant. And, well, that's a serious difficulty. You have to find something that connects the two. And of course, this is exactly the thing that led to relativity, led Einstein to formulate in 1905 his theory of relativity based on the so-called relativity principle, which is nothing else but postulating that Lorentz invariance is more fundamental than Galilean invariance. That's it. That was nothing else than that. And then sort of showing that Galilean invariance sort of follows in situations where you have small velocities relative to the velocity of light. So in 1905, 1908, so here is another example of something which sort of comes in physics, but then it's immediately taken by mathematicians. Poincaré and Minkowski are great mathematicians. They translate the relativistic principle in the language of geometry, while space and time, according to Einstein, are relative. The Minkowski metric, which was introduced by Minkowski, and you could say also Poincaré in some sense, is absolute, right? So this plays later a fundamental role in the discovery and mathematical formulation of general relativity. So Einstein, who at the beginning was quite dismissing of these mathematical, pleasantries, he found later on that Minkowskian point of view was fundamental because obviously general relativity is based on the notion of metric, in particular of Lorentz metric. All right, so 1907, 1915, this is the great period in which Einstein sets up his foundations of general relativity. The Einstein field equations is a system of partial differential equations which unifies the notions of space-time, gravity, and ties the two in principle to any other form of matter. So the Einstein field equations have sort of a left-hand side, which is purely geometric, and the right-hand side, which corresponds to the energy momentum tensor of any other field which is present in the space-time. So this was one of the great theories, together with quantum mechanics, which was developed at the beginning of the 20th century. General relativity continues to be developed by both physicists and mathematicians. So again, just like any other branch of, say, physics, at the beginning, it becomes a branch of mathematics. And in fact, to a large extent, I mean, even though physicists are still interested, they are not mainly interested in order to quantize gravity, but a classical theory of relativity is due to the fact that the equations are nonlinear, have this complicated geometric structure, they are of great interest to mathematicians, and it's really a subject of mathematics, as far as, just like all the other examples that I gave. So anyway, the moral is that the genesis of general relativity is a magnificent example of the interaction between observation, experiment, physical deductions, and inner developments in mathematics, which I want to emphasize. And of course, I'm a mathematician, and when I will talk about the theory of black holes, I will talk it again from the perspective of mathematics. Okay, so now these notions of reality, which I have already mentioned, perceptual reality is, of course, totality of consistent objects and events experienced by our senses, effect events which can be experienced by our senses. So, in other words, through experiments, people can make experiments, repeated experiments. Physical reality then is a totality of consistent objects and events predicted by mathematical theory, deemed physical, namely consistent with perceptual reality. And finally, so the examples, of course, are molecules, atoms, elementary particles, quarks, black holes, all have been predicted theoretically by mathematical considerations before being validated by experiments of observation. So again, this is a clear example of this interaction that I talked about, and which, in a sense, you can already see magnificently hinted at by Dürer. Now, mathematical reality is totality of consistent mathematical objects, as I have already mentioned. Here is a sort of a cartoon picture of the relationship between these three worlds. You have perceptual reality with Newton's and an apple falling on his head, and Einstein playing a guitar, And anyway, and then you have various equations which are related to various physical theories that we know, and those also have a reflection within mathematical reality. Of course, mathematical reality is in a sense much bigger, right? So you have geometry, for example, which corresponds started here. You have classical mechanics, which started. Well, I guess I don't have the equation of classical mechanics. Anyway, you have general relativity, which corresponds to this. These are the famous Einstein field equations. Schrödinger, and so on and so forth. And of course, but you also have other things in mathematical reality, like number theory, algebra, and so on and so forth, which are not necessarily tied to physical reality. But what I want to emphasize is somehow the developments may start here, which are direct images of physical reality, but then they are expanded and they lead to all sorts of things, and sometimes they lead to extraordinary things which later can have an impact into physics. And of course, that's exactly what happened with Riemannian geometry. Riemannian geometry developed within mathematics, the framework of mathematics, later on was found to have a tremendous impact in physics, and there are many other examples which I guess I will not go through. Right, so now here is again general relativity now. So I want to emphasize here that general relativity is a field of mathematics, and it's developing in connection. It has intimate connections with geometry, with partial differential equations, and other parts of mathematics. And again, it starts here, but it develops outside it. And again, that's sort of the picture that I wanted to make. And as I said, the same picture can be made by many other fields of mathematical of physics, which became mathematical subjects. All right, so now here is Melancholia again. I just want to emphasize that you get a sense of the same picture, which I gave you. It's a beautiful. Of course, maybe I'll make some remarks at the end about why this angel is melancholic. Why sadness? I mean, after all, scientists are not sad. Scientists are always sort of very energetic and active. But there is this melancholy here, which is kind of mysterious. Maybe we should. Maybe I'll make a few words at the end. Right. So, okay. So now I come to the real subject of my talk, which is can reality be tested by mathematics? Okay. So again, of course, the notion of reality was, as we saw. I made these distinctions between various notions of reality. So, of course, I have to make it more precise what I mean by this. So, can physical reality be tested by mathematical means? So, here is an example, black holes. So, now I come to the concept of black holes. They are specific solutions of the Einstein field equations, which are at the heart of general relativity, as I said. So they exist as mathematical objects here. There's no doubt about them. They're absolutely, they're perfect, crystal clear, like any other objects within mathematics, like algebraic geometry or Riemannian geometry or whatever. They make perfect sense. They are beautiful. But are they? Of course, the question is: are they really? Do they have anything to do with physical reality? Right? So they exist as real, rich, and beautiful mathematical objects which deserve to be studied for their own sake. They are also consistent with indirect astronomical observations. At least that's what we are told by astrophysicists. But are they real? Right, so, okay, now first of all, what is a black hole? So now, unfortunately, I'll have to use some mathematical jargon here. Of course, we are talking about metrics. So G is a metric, it's a Lorentz metric. Right? So I mean, Lorentz means it's not positive definite like in Riemannian geometry, but it has signature minus plus plus plus. Okay, so this is like Minkowski space. So in the same way as Euclidean metric is sort of the fundamental model of Riemannian geometry, because everything locally, everything looks like Euclidean, locally on a manifold, a Riemannian manifold, everything looks Euclidean. The same way, anything on a Lorentzian manifold, everything looks like Minkowski space, right? So, anyway, so this is what the Lorentzian metric is. And the equations which I'm looking at are Ricci. So this is a path of curvature. So you can define something with a metric, just like in Riemannian geometry. You can define the curvature tensor, and then you take a trace, that's a Ricci curvature. Now, this is not the most general Einstein field equations. Einstein field equations are more general. I'm looking at the so-called Einstein field equations in vacuum, in which case the equations really take this simple geometric form. Okay? But somehow, these equations are already incredibly interesting and hard in themselves, and without really adding any math. So if you want to look at more complicated matter fields, you can do it. In fact, there are black holes for the Einstein equations tied to the Maxwell equations. Right? Einstein-Maxwell equations is also a concept of black hole, but I'm not going to talk about it. This is the simplest case, and it's already, most of the story is already in here. All right, so what is a really black hole? And in fact, I'm talking about external black holes, because I'll be interested in observations outside the black hole. What happens to an observer which lives outside black holes rather than in the black hole. I'll say a few words about what happens in the black hole too, but the definition here is that of an external black hole. So this is an asymptotically flat, means things look like Minkowski space as infinity, globally hyperbolic. This is like a sort of a notion of completeness in Riemannian geometry, so let me not say more words about it. It's a Lorentzian manifold with a boundary diffeomorphic to the complement of a cylinder in R1 plus 3. And, but it's such that it's stationary. Stationary from a geometric point of view simply means that there exists a Killing vector field, which is asymptotically time-like at infinity. And Killing means that the linear derivative with respect to t of the metric G is equal to 0. And there is, of course, this notion of completeness. There is another notion of completeness, which I will leave it for a moment. Maybe I'll say a few words later. So that's the definition. You see, it's a mathematical definition, and makes perfect sense. And then once you have that, there are in fact examples of such. So again, I mean, just like whenever you define a notion, you like to find examples. Here is an example, and that's a Kerr family. So this is a family of solutions, which is a great, has also a great history itself. It's a explicit solution of Ricci flat equal to 0. Okay, it's not that complicated. I mean, of course, you see, you have a metric which is Lorentzian because you have minus here and plus plus plus, but it's very close to, say, Minkowski metric written in polar coordinates in some sense, except that you have these coefficients here, depending on two parameters. So you have a parameter A and M. These are two real numbers. And as you see, the coefficients depend on R and N and A and so on in this form. So these are very simple algebraic expressions. And you see immediately, well, first of all, you have to show that this is a solution of the Einstein vacuum equation. It has to be Ricci flat. Now, the fact that it's Ricci flat is highly non-trivial, right? So, you know, it will take quite a bit. It will take more than a whole course, 2-hour lecture, maybe 4, to actually show that this is indeed a solution of the Einstein vacuum equation. But it is a solution, and then it's easy to see that it's stationary. Right? So in other words, this vector field d over t is Killing. That's obvious because the coefficients don't depend on t. So that's by inspection. And it's also axisymmetric because, again, the coefficients here do not depend on phi. Okay? So it really corresponds to a rotating black hole, so, which is, again, the fundamental object that people identify as an notion of black hole. All right, so there is a simpler example, which is Schwarzschild, which was in fact discovered way before Kerr. The Kerr family was discovered in 1963. Schwarzschild discovered this immediately in 1915, immediately after Einstein formulated his theory of general relativity. And here you just have A equal to 0. The metric looks a lot easier in this case. As you see, and it's also clear that it's spherically symmetric. spherical symmetric, and it's also stationary. In fact, it's static, which is something related, I'm not going to say. Here is a picture of the Schwarzschild solution. So the metric looks like this. Again, you see it's a very simple metric. It satisfies the dimensional equations. And, well, again, it's a long history this picture has a long history in the following sense. The original formulation of the equations, which makes sense in these coordinates that I wrote about here, does not only make sense in this region. So it's a region up to r equal to 2m, because at r equal to 2m you have a singularity, right? So it looks like there is a singularity here. This is r equal to 2m. In reality, it turns out that this is not a singularity. It took a long time for people to understand that's not a singularity. In fact, you can change coordinates in such a way that nothing is singular in this region, and therefore you can extend the metric inside this region, which is a black hole region. So this is a black hole region. This is a true black hole. You see a singularity at r equal to 0. This is a true singularity in the sense that the curvature of the metric at r equal to 0 is actually infinity. Right? So this is a true singularity. Now, what differentiates the black hole from the exterior of the black hole? Well, it's the fact that if you are an observer, what does it mean to be an observer? The observer sort of is a point which is moving either around a time-like curve, like this, or a null curve. Now, null curves are represented at 45 degrees, time-like are represented like this, space-like directions are represented like this. So you see that light itself cannot escape, because if you are here, the light will just move towards the singularity, and of course the same thing will happen for any time-like observer. So any person who is unfortunate to fall here will necessarily experiment this incredible curvature singularity. Anyway, so of course this is. I mean, there's a lot more to say about this picture, but I don't have much time, so I think I'll. Right. Okay. Right. So here is another picture of the same space-time, which is a Schwarzschild space-time, but now it's it's a so-called conformal picture of Penrose. So it's a Penrose diagram where you see the same kind of black hole region. You see r equal to 0. Again, you see everything at 45 degrees corresponds to null curves or null geodesics, and null geodesics are the trajectories of light. So light particles go along this kind of, either go at 45 degrees this way or 45 degrees this way. Of course, this picture is vastly simplified because the space-time is 4-dimensional, and here we have only a 2-dimensional thing, right? But it's the way it is. Unfortunately, diagrams are not perfect, but they give you a sense of what's going on. Now, this is a conformal compactification in the same sense that, as we know, the sphere is a conformal compactification of the Euclidean space, say R3, right? And however, because this is a Lorentzian manifold, the compactification is more complicated, and instead of having a compactification by just one point, you have a compactification by a 3-dimensional. So this is a 3-dimensional boundary at infinity, which is called scry, and which are endpoints of light moving in this direction. So light moving in this direction will end up in this boundary, which is a conformal boundary. So it's of course an artificial boundary of the space-time. But of course the beauty of this picture is that you see now the whole space-time within a boundary domain. This is the external part of the, so this is what I call the external black hole. And we, essentially, whenever we talk about the black hole, we sort of assume that we are somewhere here, and where we look at observations which have to do with, the only thing that we can experience in some sense is the event horizon. By the way, I didn't say, this is called the event horizon. This is exactly r equal to 2n that we thought was singular before. But in reality, as I said, it's not a singularity. You can cross this r equal to 2n, and then once you cross it, you are in the black hole, you are dead. There's nothing you can do. You cannot escape. If you are here, even very close to the black hole, you can push in this direction, and happily, or fortunately, you can get out. Okay, so that's a situation. Now, there are all sorts of interesting things to be said here. For example, one of the things that I'll mention earlier, a little bit later, sorry, is that in these regions there are no singularities. This is a perfectly smooth space-time. There are absolutely no singularities. That's where we live. We believe. I mean, we believe that we are not in a black hole. And of course, in this region you have a singularity. Now, this is external Kerr. So the same thing. So here I talked about Schwarzschild, but something similar happens to Kerr. And I'm not going to go into too many more details. There are some interesting things. Yeah, but so maybe I'll say a few words. You see, I mentioned earlier, this is a very interesting feature of the Kerr black hole. So I mentioned earlier that a stationary solution is a solution of the Einstein vacuum equations, which admits a Killing vector field which is time-like at infinity. So it's time-like. Infinity in this diagram is here. This is a sort of the event horizon. The black hole is here, and T is this Killing vector field that we mentioned earlier about the Kerr has a stationary Killing vector field, which is exactly this one. And you see, it's time-like. It moves in this direction. But now the remarkable thing about T is that for the Kerr solution, so this is remarkable thing of the Kerr solution, is that as you approach the event horizon, in other words, as you approach the black hole, T becomes in fact space-like. Now this has incredible consequences, in particular because the energy, the concept of energy that we have in physics is intimately tied to this T. And that's the one, the fact that T is time-like leads immediately to positive energy. While the energy, the same kind of energy here near the black hole will be negative, which means that you can extract energy from the black hole. So therefore, if you can imagine sort of in the future, sort of a way to generate energy is you go very close to the black hole, you put there sort of energy station, and you'll have infinite sources of energy. Of course, that's science fiction at this stage, but who knows? Anyway, so now I'll get now to the. So I gave you a sense of what black holes are, right? So they are stationary solutions of the Einstein equations. We have example of these stationary solutions. They are the Kerr solutions. And again, the Kerr solutions are really, first of all, I mean, it's hard to see anywhere in physics solutions such as the Kerr solutions of very complicated equations like nonlinear equations like the Einstein vacuum equations being so simple and at the same time so relevant from a physical point of view, because the black holes, these Kerr solutions are really sort of the bread and butter of what people call black holes. So whenever an astrophysicist thinks of a black hole, he thinks about exactly the Kerr solution. So he has exactly these two parameters, and all the measurements that he makes are relative to these parameters. Now, as I said, there is another kind of black hole solution, which is the Kerr-Newman, corresponds to Einstein equations coupled to Maxwell, where you have three parameters, but it's very similar. Now, so what are the tests of reality that I mentioned earlier? Well, okay, so here I finally come to this issue. How can you test the reality of black holes from a physics point of view, but within the framework of mathematics? Well, I claim that there are three tests of reality. First of all, rigidity. So rigidity is simply the question, is a Kerr family unique? In other words, are there any other stationary solutions of the Einstein vacuum equations which are of the black hole type, which I have defined, and which are not Kerr solutions? So this is the question of rigidity, and of course it's a question that comes up in many branches of mathematics. In geometry, rigidity is all over the place. But it also comes out here in general relativity, and it's tied to the question of reality, as I will explain in a second. But maybe more important than rigidity, though they are connected, you cannot prove stability without rigidity. Even more important than the question of stability from the point of view of reality of black hole, yet even more important than rigidity from the point of view of reality of black hole, is the issue of stability. Are black holes stable? So what does it mean to be stable? Right? Well, okay, so Einstein equations, Einstein vacuum equations, but more generally Einstein field equations, are system of nonlinear hyperbolic equations, which means that you prescribe an initial, you have to prescribe an initial value problem. So in fact, any solution of the Einstein vacuum equations can be parameterized by initial data. Okay, so this is the initial data that I have here. Okay, so you start, in fact, with a 3 Riemannian manifold, a metric G0, which is, sorry, sigma 0 is a 3-dimensional manifold, G0 is a Riemannian metric, and K0 is a 2-tensor, a symmetric 2-tensor, which corresponds to, in fact, to, maybe I'll explain here. But I don't have, I think I took away the, anyway, it doesn't matter. So it's just like in mechanics, where you have to specify both the position and the velocity of a particle. Here you have to specify the value of the Lorentzian metric. So you think of a solution of the Einstein equation. This is the space-time, and you have to specify the restriction of the Lorentzian metric to a given space-like hypersurface. That's why you get this thing, which is Riemannian. So if you restrict a Lorentzian metric to a space-like hypersurface, you get a Riemannian metric. And the second fundamental form would be essentially the time derivative of the metric G restricted again to this. It's a second fundamental form from the point of view of geometry. And you are starting with such a thing, and you want to solve this equation. Okay? It turns out, just like in Maxwell theory, so in Maxwell theory you prescribe the electric and magnetic field, you also have to have some constraint equations. You cannot prescribe E and B arbitrarily. You have to have some constraint equations. Just the same way here, these sorts of things have to satisfy some constraint equations in order to be consistent with the Einstein equation. So anyway, so an initial data set is a triplet between a 3-dimensional Riemannian manifold with a metric G0 and a second fundamental form K0, which verifies the constraint equations. Now, the constraint equations are interested in its own right. In fact, they play a fundamental role in many things in Riemannian geometry. For example, the positive mass theorem is really nothing else but a theorem about the initial data set. Right? For those of you who know the positive mass theorem, and of course, the positive mass theorem has led to many other beautiful things in modern Riemannian geometry. They really have to do just with this constraint equation. But in any case, the problem is not to solve the constraint equations. The problem is to start up with an initial data set which verifies the constraint equations and then solve dynamically the equations. Now, imagine that you start up with the initial data set of a Kerr solution. So you take a Kerr solution. Of course, it has an initial data set associated with it. Right? So that would be, and I make a small perturbation of it. And suppose that if I make a small perturbation, well, first of all, I want to see that I can solve the equation, but at least for a short time, it can be solved due to a result of Yvon Choquet-Brouard in 1852. It's in fact Dürer and Yvon Choquet-Brouard who started the discussion of initial value problem in general relativity. This was really the great achievement of the French school of Dürer and Yvon Choquet-Brouard. And the main result, which was proved by Yvon Choquet-Brouard in this regard, is that if I start up with a general initial data set, I can always solve at least for a while. Okay? Anyway, so, but here the issue, of course, you want to solve for the whole time. And the issue is that if I start up with a small perturbation, really very small perturbation of the initial data of the Kerr solution, I may converge to something entirely different. In fact, things can blow up, and there is no stability whatsoever. If there is no stability whatsoever, then I claim that there cannot be any physical reality to the Kerr solution, because the Kerr solution will be simply a mathematical artifact. It will exist here, but not here, or here. Okay? So that's what I think that, I claim that stability is a fundamental issue that has to do with reality. And of course, it has to do also with rigidity, because you cannot prove stability without first understanding rigidity. So rigidity is part of stability, in fact, and will formulate a conjecture which, in fact, embodies both. But in any case, These are the first two. Now collapse. So what about collapse? Now, of course, we know from physics again, I mean, reading there's a lot of stuff about black holes. We know that stars can collapse to black holes. So you can have matter which collapses to a black hole. So in other words, you can have, from a mathematical point of view, you can translate it by saying you start up with initial data set which don't have any black holes, right? So you can sort of verify somehow. There are no black holes here, and later on a black hole will form. So you want to understand how this can happen mathematically by solving the Einstein equations, studying some initial conditions. You want to find criteria of collapse. How can things collapse? So these are the three problems which I claim are really tests of reality. Now, in addition to these three major problems, I want to say a few words about further sort of a bigger vision of mathematical general relativity, which has to do with probably some of the deepest conjectures which are comparable to all, for example, the seven Clay conjecture of mathematics. And in a sense, maybe I find this even, I mean, from my point of view, is even more basic and more important and more sort of capable to lead to interesting mathematical developments than other things, than some of the other seven Clay conjectures. In any case, never mind the conjecture, never mind the Clay conjecture. Here is a weak Cosmos censorship, which says roughly the following thing. You see, the Schwarzschild, we saw that if you are within the black hole, you have a singularity necessarily. So, in other words, no matter what you do, you will see the singularity here. However, if you are outside the black hole, then, and this is a conjecture, so now it's a general conjecture, not just for Schwarzschild or for Kerr. I want to look at a general space-time, in other words, something which corresponds to general initial conditions. You may have singularities, but the conjecture says that singularities have to be covered by a black hole. In other words, the singularity can never be seen by an observer at infinity. It doesn't generate anything which will destroy somehow the life of an observer which is moving far away from the black hole. So anyway, this can be made mathematically rigorous, exactly what the conjecture is, and it's one of the great, I think, great conjectures. You see, it's a conjecture of regularity. Okay, there is another one which is called strong cosmic censorship, which maybe I'm not going to say anything about. It's something which says something about the nature of the singularity that you see here, but let me not say it. But I'll say a few words about the final state conjecture, which is in a sense even bigger than the cosmos censorship conjecture. Namely, this conjecture says the following thing. It's called the final state because it tells you what are the final states of any initial data. I start up with any initial data. It has to be asymptotically flat. In other words, the initial data has to look flat at infinity. Well, you start out with initial data, equations are extremely complicated. There are lots of things that are going to happen. You can have black holes, you can have many black holes which rotate around each other, they go away, they coalesce. You can have black hole coalescing. Inside the black holes, you have maybe singularities according to cosmic censorship and so on. But finally, the idea of this cosmic censorship conjecture is that you are going to see asymptotically, so for large time, whatever time means in the context of relativity, you are going to see only in any compact region of the space-time, you are going to see only asymptotically only one Kerr black hole solution. Okay, so everything converges to black hole. Now, what is the rationale for this conjecture? Well, the rationale is that somehow this is very different from what happens in Newtonian mechanics. You generate gravitational waves. So, for example, if you have a black hole interacting with another black hole, that will generate gravitational waves. And as all these gravitational waves move out, you are going to get a stationary solution. But the only possible stationary solution, according to the rigidity conjecture, is a Kerr solution. So this is really nothing more than this, is sort of the heuristics of why we expect such a result. Of course, this is far, very far from a true heuristic argument, because there are many, many things that can go wrong with this. In particular, if the stability conjecture that I mentioned earlier, if the stability is wrong, then this will also be wrong. Okay? So, I don't know how much time I have, but I presume I'm close to the end. So, all right, so these are the problems, and what I want to maybe say a few words about what has been done about this. So, these are three problems in which there's been a lot of progress in recent years, and particular progress done by mathematicians. For example, the rigidity conjecture is true in the static case. The static case is really the case of Schwarzschild. So it's, anyway, let me not make it precise. Let me just simply say that the conjecture in the case of static simply says that if space-time is static, then it must be Schwarzschild. Okay? Now, in the general case, which is, so this is essentially, in other words, this is completely understood. So the rigidity conjecture is completely understood in the so-called static case. Now, in the axially symmetric case, so the conjecture again says that the Kerr family is unique, exhausts all stationary asymptotically flat, regular vacuum black holes. So the only assumption I make is stationarity. But of course I know that the Kerr solution is both stationary and axisymmetric. So you could, in principle, make another hypothesis in the rigidity conjecture. You can also look at the case where you have stationarity and axisymmetry, and then you want to show that the only solution you have is a Kerr solution. And this is also well understood. So this is a result of Carter-Robinson, which is very well understood, and it's one of the beautiful results in general relativity, which is in fact based also on the theory of partial differential equations. In fact, it's based on the elliptic theory of partial differential equations. In fact, the equations in this case really reduce to harmonic maps. And of course, harmonic maps are well known to people in Riemannian geometry. Now, Hawking also proved the result if you assume analyticity. So he makes an analyticity assumption about the space-time and then concludes that you have rigidity. Now, analyticity, however, is a cheap assumption. I mean, in fact, by assuming analyticity, really you almost kill the problem. It doesn't. The problem really becomes trivial. And there is no reason whatsoever to assume analyticity. In fact, given that the Einstein equations are hyperbolic equations, analyticity is really almost a ridiculous assumption. The very notion of domains of dependence and finite propagation speed don't make any sense in the context of analyticity. But analyticity is still an interesting statement in the sense that if you are looking for any other explicit solution of the Einstein vacuum equations, then you are not going to find anything else but the Kerr solution, because analyticity presupposes that if looking for explicit solutions, you presuppose that you are looking for something which you can write down explicitly in terms of analytic functions, elementary or analytic functions. So this tells you, so it's interesting only insofar as there can be no other explicit solutions, but of course it doesn't mean there cannot be other solutions which are not analytic. So, so this is the sort of thing that I've been working with Alexakis and Ionescu, my colleague from Princeton, and we have various results. In particular, we proved that in the non-analytic case, which is the correct case, if you are close enough to a Kerr solution, and close enough means many things, can mean many things, many way of defining what you mean by close enough. But let me say, there are certain geometric ways of measuring how close you are to a Kerr spacetime, and in that context, the rigidity conjecture is true. So again, this is something that we can do. Then there is the issue of stability, and maybe I'll finish because I don't have too much time. With the stability, even the formulation of stability, the correct formulation of stability is something problematic. because of the following thing. So imagine that you have a Kerr solution. So this is the Penrose diagram of a Kerr solution. And you look at initial data. These are your initial data. You take initial data here. And I'm not interested in what happens within the black hole. I'm more interested in what happens up to the event horizon. So in other words, I set up initial data of Kerr. So this will be exactly the data of Kerr. And I make small perturbations in this region. I can even think of myself of making a very, very tiny perturbation, a smooth compactly supported perturbation somewhere here. And of course, the perturbation will evolve using the Einstein equations. And the question is what happens with the perturbation in a long time. And the conjecture says that small perturbations of a given Kerr for a given A and A has to be less than n. That's very important. A has to be strictly less than n. The case A larger than m is actually unphysical for many reasons. Initial conditions have maximal future developments. It means they can be developed for a very long time, which converge to another Kerr solution. So the conjecture is that you do have stability, but you don't necessarily converge to the original one, but to most probably to a different one. In other words, you may start up with A and N, but the final A and N of the space-time to which you are approaching will be very different. Now this makes the problem extremely difficult because you cannot even talk about linearization in a given space-time because you don't know a priori, you don't know where you are going. Okay? So this is a great problem, and I'll finish with just telling you a few things about what we know about the power. First of all, there is a result of Christodoulou and myself from the 1990s about the stability of Minkowski space. Now Minkowski space is an example of, say, a trivial example of a Kerr solution. It's a case when A is equal to 0, M equal to 0. And in that case, so if I start up with initial data which corresponds to Minkowski and I make a small perturbation, then nothing bad can happen. Okay? And that was sort of an important result of the development of modern dynamics theory of general relativity. And the belief is that somehow the methods which we use in the global stability of Minkowski space will be also relevant in the general case. Now, however, we have very little in the stability of Minkowski space. The only results which are known, there is a result of a physicist, Whiting, from 1989, which shows, with a lot of hard work, that so if you look at special linearized equations, so not non-linear, so you don't treat the true equations, but you look at some linearization in Kerr, and you, because of the fact that Kerr has symmetries, you can decompose the solutions of these linearized equations. You can decompose it by separation of variables. So you can do separation of variables, and you get very complicated system of equations, and you can show that for each mode in this separation of variables, for each mode, you have some kind of stability. But this mode stability does not, by itself, does not give you at all, does not give you anything about the full solution. In other words, if you try to take back and sum all the modes, there's no reason you have stability. Okay, so this was a result of Whiting. Now, remarkable progress has been made recently in the last 10 years by various people. In particular, we are now able to understand the case of just a wave equation. All right, so maybe I'll finish with this. Oops, I think well, anyway. Yeah, so I'll finish with this. So I just imagine that you have your Kerr solution. So this is the true Kerr solution. And you are studying some simple equation, like, so L phi is equal to 0, which is linear. So in particular, it could be just a Laplace-Beltrami operator associated with this metric, which is in fact a wave operator because the metric is Lorentzian. So you don't know a priori even the fact that phi is bounded. Even this is, in other words, if you start up with initial conditions which are very, very small, let's say, and smooth and compactly supported, these things can become large. And what these people have done is to show that this cannot actually happen, that you do have, in fact, linear stability. In fact, you can there is a remarkable new result of 2014 by my colleagues Lafave-Rodniansky, and there's the student of Rodniansky, is Schlappmann-Rothman, which show that for those kind of equations, you have complete stability for all values of A. But it's much easier to treat the case when A is small. This was done before by the people that I mentioned there. But this particular result is very deep. And this is finished. The full problem of stability, however, is far from being solved. So I'll finish. Yes. Well, so it's an external black hole. So if you remember, okay. So let's go here. Yeah, here. You see, this is the space-time that I'm talking about. I'm talking about the external part of the black hole. So I take away the black hole, and I'm only interested in this. So from a topological point of view, that's what it is. It's yes. No, I mean it's a totally different. It's a totally different thing, wormhole. So it's not. There's nothing to do with this subject. So wormhole has to do with closed time like geodesics and so on and so on. It's a totally different story. I mean, closed time like geodesics are. Oh yeah, sure. But it's a different problem. Yeah, of course you can ask. General relativity is a huge subject. I mean, I think it's one of the most remarkable new subjects of mathematics, and we'll see a lot of things. I mean, there are many problems. I mean, there are problems due to cosmology. So there are cosmological problems, for example, which I didn't talk about. I mean, I picked up a very small part of general relativity, but very relevant from the point of view of subject of mathematics. Yes. String theory? Well, that's not reality. I mean, that's just mathematics at this stage. I mean, we'll see if it has anything to do with physics. I mean, that remains to be seen. But right now, it's just mathematics. Which is fine. I mean, developments within mathematics could lead later on to something here. But right now, it's too early to tell. Yeah.
I think the title of your lecture was a question, and if I got it right, you didn't quite answer it.
Oh, a question. Right, so we don't know. We really don't know. So the issue of stability is not well understood. I didn't talk about the collapse. Rigidity is also not understood. So there are lots of open problems in this field. And the most important one, which is the issue of stability, I expect that in the next 20 years we'll be able to do it. But by the way, I forgot to say something about melancholia. Right? Yeah, but maybe I'll answer some other questions and then I'll as there are other questions, yes.
Many years ago, the physicist Dürer and Friedrich wrote a paper in which they suggested that these partial singularities would transform away with different variables. And then that whole thing seems to have disappeared. Is there anything?
Well, I mean, there is a theorem due to Penrose, it's called the Penrose singularity theorem, which shows that this singularity, the Schwarzschild singularity, are stable and they will not go away. Right? So, yeah. Right.
Well, you said that Seneca was cheaper than much, and so you have to do it privately, and thank you very much.
But I wanted to say about the melancholia. So she's melancholic because she could not yet solve the stability problem. Yes.
You need to make sure that your definition that you propose.
Oh, yeah, yeah, sorry. Yeah, this one you also need, right?
Thank you. So my talk is actually closely related in spirit, if not exactly in detail, to Sergio's talk. Is this working? In that I'm going to talk about geometry, really the geometry starting with Gauss-Riemann, its relationship to physics. I'll talk about topology, and the relationship between geometry and topology and the relationship of topology and physics. So the modern perspective on geometry, as far as I'm concerned, begins in the first half of the 19th century with the work of Gauss, which Sergio was already talking about, and his student Riemann. When topology actually started is open to question or debate, and it took a longer time. Certainly Riemann, Gauss's work, and in particular Riemann's work, we would now view it as topological in nature. But in fact, as an independent subject, at least in my view, topology didn't start until, well, the work of Poincaré around the turn of the century, the turn of the last century. But the 20th century and the first decade, the first 14 years of the 21st century have been a time of tremendous advances in both geometry and topology, and also in its connections to physics. So in this talk, what I want to try to do is trace some of this history, the last 200 years of history, geometry and topology, and hit some of the high points. And along the way, the themes I want to emphasize are very closely related to the things we've been just hearing about. Well, I'm going to talk about the difference between geometry and topology. That's often a confusing subject to non-mathematicians. I want to talk about the ever-increasing level of abstractions in these subjects and the power that abstraction brings. I think Sergio's diagram over here is also a reflection of these worlds. This is the more abstract version, this is the intermediate version, this is the reality we actually live in. And then the interplay, as I said, of geometry and topology with theoretical physics, which was certainly a theme of the last talk. Well, the prehistory for all of this is Euclid, his geometry. He formulated a series of axioms to capture what we would now call plane geometry. But in the way it was presented, it's a synthetic version of geometry. You have undefined objects called lines and points, and they satisfy certain axioms that are supposed to be obvious, at least if you're thinking about the plane, and then you make deductions from those axioms. So, for example, one of the axioms was two lines meet at most one point, and given 2 points, you can draw a unique line through those 2 points. The one axiom that caused trouble from the time Euclid introduced it until the middle of the 19th century was the parallel axiom, which says, given a line and a point not on the line, you can draw exactly one line through that point parallel to the given line and through the point. And so this is not a local axiom, because whether or not 2 lines are parallel, that is, don't meet, is really something you can only tell when you extend the lines forever in both directions. So you can't see it in a local picture the way you can check do all the other constructions in Euclidean geometry. So there were big questions. Does this follow from the other axioms? Is it consistent? And so on. Well, in the early 19th century, people began to seriously question Euclid's axiom, and Lobachevsky, working synthetically and axiomatically, began developing the axioms if you assume the contrary of the parallel postulate. And more in a modern way, Bolia and Gauss constructed models that satisfied all the Euclidean axioms except the parallel axiom, but at least if mathematics is consistent, those models were going to be consistent, and hence Euclid's parallel axiom was not a consequence of the other axioms. Bolia published his work in 1932. Gauss never published it, and in fact there was some dispute when Gauss learned of Bolia's work. People asked him, well, what do you think of it? And he said, well, to praise that would be to praise myself. But of course, he'd never said anything to anybody about his model of non-Euclidean geometry, though I think people today, usually when Gauss claimed something, even if he'd never said it publicly, after he died, you opened up his journals and you find that indeed everything he said he knew, he did know, often quite a bit before anybody else. Anyway, here's one version of this model. It's called the Poincare model. So lines are either straight lines through the center of the disk or circular arcs perpendicular to the boundary. Points are points. Two lines are parallel if they don't meet, and I've drawn through this point X two lines parallel to L. And in fact, you can draw infinitely many parallel to L. One of the things Lobachevsky showed was once you had two parallels to L, there would have to be infinitely many of them. So this model convinced people that the parallel axiom was in fact independent of the others. But we have a real switch of perspective at this point, which is to move from synthetic geometry to a much richer version of geometry, which involves calculus rather than formal synthetic axiomatic approaches. And Gauss started this study by studying surfaces. This is in the 1820s. Surfaces in ordinary three-dimensional space, but surfaces that can be curved and bumpy and so on. And what he discovered was a fundamental property of these surfaces, their curvature, and that's now called the Gaussian curvature. He showed how the curvature could be computed by doing computations of area near the point. And in fact, I've drawn pictures of the three possibilities for Gaussian curvature. If a piece of the surface looks like this, it has positive Gaussian curvature. A piece of the surface looks like this, it's flat. Actually, strangely enough, this one's flat too. And a surface that looks like a saddle has negative Gaussian curvature. Gauss's description of curvature was take the area in a small ball around the point, so there's a point up at the top here. Take this ball, which we think of as small, compare the amount of area in this ball to the amount of area in a plane disk of the same radius. Now you probably all have intuition that this piece of surface has less area than a ball in a disk in the plane with the same radius. You ever taken a cap of an orange peel and you squash it flat? What happens is it tears, usually in three different pieces, because there's not enough area in the orange peel to fill up the area of the disk. So when you push it flat, you're pushing it to the same size disk in the plane, but it's had to tear open because it doesn't have enough area. When there's an area defect, when there's not enough area, as in this case, you have positive curvature. If you take this saddle and you push it flat, I don't know, this probably is not as familiar to you, it will in fact double over itself. It's got too much area. The plane clearly has exactly the right amount of area. This does too. And the way you can see that is, think of it as being made out of paper. Cut it open, unwrap it. It's a flat sheet of paper. So it has exactly the same area as the flat surface. So it has zero Gaussian curvature. So at every point So if we have a surface in 3 space, well, let me back up one. So at every point of the surface, you can do local measurements and compute the Gaussian curvature, which may vary as you move around the surface point to point. Okay. Now, how did Gauss actually talk about these areas, distances? How did he do the measurement? So his idea was a very simple one. You have a surface in ordinary three-dimensional space. If you have so here's the surface. If you have a curve on that surface, at each point, it has a tangent vector, which is telling you the infinitesimal motion at that point. And that tangent vector has a length. Well, if you want to know how far you go, as you know, you take speed times time, and you get length. So you simply integrate your local speed, that is the length of these tangent vectors, over the curve, and that tells you the length of the curve. So you can define the length of a curve on a surface in this way, and then you can define the distance between 2 points by taking all possible curves that go between those points and taking the one of the shortest length. So in this way, you have an infinitesimal notion, this notion of speed or length of tangent vectors leading to a global notion of distance between points, and that's the metric as Gauss introduced it. Now, one technical remark related to something Sergio said, and will come up later, is that this notion of how we measure lengths of tangent vectors is given by a quadratic form on that two-dimensional vector space, and it has to be positive definite in this Gaussian or Euclidean world. So we have this notion of geometry now that's infinitesimal. It's given by a notion at every point of the space, this length of tangent vectors. And from that, we've constructed distances, but we can also compute angles, we can compute areas, so on. And as I told you just a couple minutes ago, the curvature, as Gauss defined it, is computed by studying what the area looks like in an arbitrarily small neighborhood of a point. In fact, one of those beautiful theorems in this whole subject says that you can integrate the curvature over the entire surface to give an interesting global quantity called the Gauss-Bonnet theorem. If you integrate over the surface the Gaussian curvature, you get up to this universal constant 2 pi, you get the Euler characteristic of the surface, which is 2 minus 2g, where g is the number of holes in the surface. I'll come back to that a little bit later. But this is our first indication of deep connection between geometry, which is the left-hand side, the sum over the entire surface of its curvature at every point, with a purely topological quantity, which is the number of holes in the surface. So we're seeing a connection here between topology and geometry. Now, as I indicated a couple of minutes ago, this is a fundamental change in perspective in many ways from the Euclidean synthetic approach to geometry. So we're no longer working synthetically with undefined objects satisfying axioms, but now we have spaces which have independent definition, and we're doing mathematical constructions on them. Also, we're no longer assuming that our geometries are homogeneous in the sense that they look the same everywhere. In Euclidean geometry, it doesn't matter where you are, the axioms are exactly the same. The notion of straight lines translate. These Gaussian surfaces may not have that property. And lastly, we're focusing now on measurement, which is, after all, where the term geometry comes from, actually Earth measurement, which Gauss was quite interested in. So he was interested in measuring in this abstract mathematical framework distances, angles, area, rather than thinking about abstract axioms of points and surfaces, points and lines and their properties. Of course, with this change in perspective, we've vastly expanded the notion of what surface geometry is about. It's no longer just about the flat Euclidean plane, it's about a whole host of surfaces. Of course, Euclidean geometry is now seen as a special case of Gauss's geometry when the surface in 3 space is just a flat plane. And the shortest paths are the usual Euclidean straight lines. You recover Euclidean geometry in this case, and this is a case of Gaussian curvature 0, flat geometry. But this hyperbolic model that I produced a few minutes ago also has a Gaussian type metric. There's a notion of a length element at every point that defines the metric in which the straight lines are exactly those circular arcs that I wrote down. This turns out to be the surface of constant Gaussian curvature -1. So the Euclidean case is a case of Gaussian curvature 0. This Lobachevsky non-Euclidean geometry is a case of Gaussian curvature -1. Though I'm cheating a little bit because this surface, the constant Gaussian curvature -1 surface, cannot be embedded in three-dimensional space. So it doesn't quite fit in Gauss's original framework, though pieces of it can be embedded in three-dimensional space. The whole surface can't. Okay, and then, of course, the spherical geometry that we haven't talked about, the round sphere, which is a nice surface in three-dimensional space. And that's the case of Gaussian curvature +1. These are pictures of crocheted hyperbolic pieces of hyperbolic space. And I think you can see quite clearly why the entire hyperbolic space can't be put inside three-dimensional space. There's too much of it. And you see it beginning to curve around, and it's going to meet each other. If the crocheter had tried to make this any bigger, those pieces would start overlapping each other. And there's a beautiful theorem in mathematics. Memory serves, it goes back to, is it Hilbert? No, this is right. Prove that, in fact, you cannot embed too big a piece of this hyperbolic space into three-dimensional space, as this crocheting shows. By the way you crochet these things is, I'm not an expert in crocheting, but instead of doing a rectilinear crochet, you add extra knots or loops or whatever they are ever so often. So you have more area because of these extra knots, and that's what leads to the hyperbolic geometry. Now the three examples that I was just talking about, the sphere with Gaussian curvature +1, the plane which is flat, and the hyperbolic or Lobachevskian space, which has constant curvature -1, these are in fact homogeneous geometries. They look the same everywhere. And this is Euclidean geometry, of course, with its axes, was concerned exactly with that kind of geometry. But there are many, many other surface geometries. Think of the surface of the Earth, for example. It has peaks, it has valleys, it has passes. It's not at all homogeneous. The peaks have very high positive curvature, the passes have negative curvature, and so on. Nevertheless, it's a perfectly good Riemannian surface, Gaussian surface to study. It fits in Gauss's geometry, does not fit in the Euclidean geometry. The other thing that this change in perspective did was it allowed us to apply the whole mechanisms of calculus from Newton, Leibniz, and others, differential equations, both ordinary and partial differential equations, because we're defining things locally, and we now have all of calculus at our disposal, something we don't have in the synthetic version of geometry. And one example of that is the notion of geodesics. So this is what replaces straight lines in Euclidean geometry. Geodesics are length minimizing paths on your surface, and they turn out to be exactly those paths that solve a second-order ordinary differential equation that you can write down, and the coefficients in the differential equation come from this quadratic form that defines the metric. Flat surfaces, they turn out to be the usual straight lines. On the round sphere, they're the great circles, but they exist on all these surfaces. They're going to be hard to predict. It's going to be hard to predict where they go if the surface is bumpy enough, but as long as you haven't punctured the surface anywhere so they're missing points, and as long as the surface goes on forever, it doesn't have any edges, these geodesics will always exist. Starting at any point and in any direction, you can continue a shortest path forever. Okay, so far, we've been doing a very abstract form of geometry and brought in calculus, but it's all been on surfaces. As Sergio mentioned, Riemann, he said 1853, I thought it was 1854, we'll have to debate that later. Riemann presented his thesis. So he was assigned, he had to pick 3 topics, and he gave those 3 topics to his thesis advisor, Gauss, who then picked one. And Gauss picked the topic, on the hypothesis that underlie geometry. He said to Riemann, well, your other topics were in areas where I know you've been thinking about, that I know you've been thinking about for a while. As far as I know, you've never thought about geometry, so it'd be interesting to hear what you had to say about that. Well, what Riemann had to say about that lasts till today. So he gave a complete generalization of Gauss's ideas of surface geometry to all higher dimensional spaces, and it's the foundation to the approach to geometry that's still used today. So the first thing he had to do was define higher dimensional spaces. And I'll come back to Poincaré's view of higher dimensional spaces in just a few slides. The definition that Riemann gave was fairly abstract and inductive. He said, okay, well, suppose we know what n-1 dimensional spaces are, and we want to make n-dimensional spaces. How do we do it? We simply take a 1-parameter family of varying n-1 dimensional spaces. And that'll be an n-dimensional space. Now, there's one comment at this point that just fascinates me. I have no idea what Riemann meant, or what he had in mind. He said, while it might be interesting to study what happens if the family of 1-dimensional spaces acquire a singularity, we don't need to do that today. Now, there's a whole development in topology that's based on the idea of functions on an n-dimensional manifold and the kind of singularities they develop. So the level sets of the function would be a family of n-1 dimensional spaces exactly as Riemann had thought, but there would be a singularity where the function has a singularity, and this has been one of the most important and powerful tools in modern topology, the theory of Morse functions. Anyway, he didn't pursue that. He just said it might be interesting to think about. The other thing that he did in giving this abstract definition was he jettisoned Gauss's requirement that Gauss had surfaces in ordinary 3-dimensional space so he could see them. Riemann now is talking about higher dimensional spaces, and he doesn't need them embedded anywhere. He's giving an intrinsic definition of what these spaces ought to be like. Okay. So I've drawn 2 pictures here. We can think of the 2-sphere as a 1-parameter family of, well, essentially circles. Start at a point, and the circle grows out of the point until it hits the equator, and then it slowly shrinks back until it finally hits a point. So the 2-sphere is a 1-parameter family of circles, as I say, with these sort of interesting things happening at the end. Well, we can do the same thing 1 dimension up. What is the 3-sphere? How do you picture the 3-sphere? Well, we can't actually see it. Our 3-dimensional space, which we have pretty good imagination of, is everything but 1 point missing. There's 1 missing point from the 3-sphere. It's a little hard to imagine what happens out in that point. But from Riemann's perspective, you simply take a 1-parameter family starting at a point, small 2 spheres develop, get bigger and bigger until you hit the equatorial 2-sphere, and then they shrink down again to a point, which is the North Pole. So the 3-dimensional sphere, in complete analogy, is a 1-parameter family of 2-dimensional spheres, even though we can't really see how all this works. Okay. So that was Riemann's definition of n-dimensional spaces. Then he wanted to generalize Gauss's notion of geometry in these n-dimensional spaces. So So once again, he abstracted. Gauss, because his surface was in 3 space, he knew what the length of tangent vectors were. A tangent vector was just a vector in ordinary 3 space tangent to the surface. So he could use the length of that tangent vector in 3-dimensional space. Well, Riemann's spaces are no longer, they're not in some ambient Euclidean space. So Riemann's definition is simply to say we have a notion that's given somehow of the length of these tangent vectors. And a collection of notions at every point is the Riemann metric tensor, and the structure is a Riemannian metric. And again, it has to be given, as in Gauss's case, by a quadratic form on each tangent space that's positive, definite. Well, Riemann didn't stop there, so there's the definition. There's the generalization of Gauss's definition. He went on to study curvature. So Riemann showed that with his notion of Riemannian metric, at a point in your higher dimensional space and in any 2-plane direction, you have a Gaussian curvature. It's a complete analogy with what Gauss did. But furthermore, that all these various Gaussian curvatures in different 2-plane directions at a point fit together to make a mathematical object with a lot of structure, a tensor. It's called the Riemann curvature tensor. And Riemann went on to show that, at least locally, this Riemann curvature tensor was all the information in his metric. So it determines the metric, at least locally. He also extended Gauss's notion of geodesics, basically the same equation, a second-order ordinary differential equation using the coefficients come from now the Riemann curvature tensor instead of Gauss's. Now Riemann understood that curvature was related to force. In fact, he expressed the idea in this way. He said, if you have non-zero curvature in your Riemannian metric, this means that no matter what local coordinates you choose to put on the space near this point, geodesics are not going to be straight lines in that coordinate system. They're going to bend. That's one consequence of curvature. But the bending of straight lines, geodesics, will be experienced as a force because it's a deflection from what you would expect naively, the straight line paths of Newton. Now this is something we know on the Earth. There's something called the Coriolis force. It's what causes hurricanes in the northern hemisphere to always spin this way. What kind of force is it? Well, it's not a force at all. It's a reflection of the fact that the Earth is not an inertial coordinate system, it's rotating. And because it's not an inertial coordinate system, when you write things down in that coordinate system, you have an extra term that bends things. Well, that was exactly the point that Riemann was making. That when there's curvature, there's no way to write down a coordinate system in which the geodesics are all straight lines. So curvature is related to force. Of course, this idea recurs in Einstein in a way that I'm sure Riemann did not suspect. So the study of these higher dimensional Riemannian metrics is called Riemannian geometry. It's one of the most central and active areas of modern mathematics, and Riemann's foundational definitions, his curvature and his theorems about the curvature in geodesics remain central elements in the study to this day. So Riemann presumably never thought about geometry before Gauss told him. He thought about it, and 150 years later, we're still living on it. Now, I focused on Riemannian geometry. There are many other kinds of geometry, just to list 3 of the most important. There's complex geometry. So implicitly here, I've been working, the number system has been the real numbers. You can replace the real numbers with complex numbers, and complex numbers in some ways are much richer and more powerful than real numbers, and you get interesting geometries, complex geometries. There's a geometry that comes up a lot in physics and is now a separate branch of mathematics called symplectic geometry. it's well suited to the Hamiltonian approach to mechanics, and it also is instrumental in quantum field theory. There are generalizations of Riemann's curvature and Riemann's geometry to other more abstract mathematical objects, which I won't try to define. Principal bundles, connections, curvature, principal bundles and connections, which have curvature just like Riemann's metric has curvature, but in a much more abstract setting. Let me talk briefly about the relation of all this to general relativity. I'm basically covering the same ground that Sergio did an hour or so ago. So after Einstein had developed special relativity, he went on a 15-year search for the correct mathematical formalism to generalize to general relativity. His breakthrough came when a mathematical colleague told him that what he was searching for seemed very close to what Riemann had done 50 years earlier. And with one minor twist, which also came up for Sergio, namely this quadratic form that measures lengths of tangent vectors is no longer required to be positive definite. In fact, it has one positive direction and all the rest are negative. This turns out to be exactly what Einstein needed, and with that, he formulated general relativity as a four-dimensional space-time continuum, space and time are mixed, with a Riemannian type metric, which has this, it's no longer positive definite. Light follows geodesics, light like geodesics in this geometry. Mass creates curvature, and mass, as Einstein predicted and was established in 1939, mass, i.e. curvature, bends light in exactly the way Riemann had understood curvature would account for force in a simpler context. Now, this isn't the only connection between geometry and physics. In fact, all of modern-day theoretical physics makes use of geometry to form the context in which the theories are formulated. And as Riemann intuited, curvature is a central feature in the way mathematics is connected to physics, represents force. So we've already seen general relativity, the theory of gravity, as an example of the interplay of geometry and physics. But at the other extreme, there are three forces, one of them electromagnetism, and the other two that work inside the nucleus, much shorter range forces. And these are understood through a physical theory called the Standard Model. And it's formulated in terms of principal bundles, connections, and curvature playing a central force role there. So all the forces that we know about in nature, gravity through one geometric expression, and the short-range forces plus electromagnetism through a completely different set of mathematical constructs. This is the basis in which one formulates physics, and often the interplay between studying things here in mathematics and studying things in physics plays out in these other examples exactly the way Sergio was talking about for general relativity. And let me just editorialize for a second. The modern developments in fundamental theoretical physics in the last 25 or 30 years has been string theory, superstring theory. If you go to physics departments, you'll find debate, if not outright hostility to this. It's not physics, it's not physics. It's completely accepted in all math departments as a great intellectual enterprise, which has taught us a lot about mathematics and produced beautiful conjectures and questions inside geometry for us to work on. So it's completely accepted inside mathematics, not as a theory of the universe, but as a great intellectual benefit, boon to mathematics. The physicists still have their doubts. Anyway. Let's switch now from geometry to topology. As I said, it was implicit in the work of Gauss and certainly in the work of Riemann, who was defining the entire dimensional spaces. But as far as I'm concerned, its independent existence is due to the work of Poincaré in the between 1890 and 1905. So Poincaré began a systematic study, topological study of higher dimensional spaces. And I found, in reading Poincaré, one thing I found very strange was it was almost defensive in proposing this or saying he was going to carry out this study. He said, today no one doubts the importance of higher dimensional spaces. While we cannot directly perceive them, we can give them rigorous mathematical definition and subject them to rigorous mathematical study. All of my investigations in geometry and physics have led me back to their study. Now, I would never start a paper on higher dimensional spaces this way because it's so obvious. But I guess it wasn't quite so obvious even in Poincaré's day, 1900. So much of what he did in topology, Poincaré was motivated by the classification of surfaces, which had been accomplished in the latter part of the 19th century. So just to remind you, surfaces is a list of surfaces. I'm simplifying. I'm thinking only about orientable surfaces and only about closed ones. Anyway, here they are. This is the simplest surface of all, the sphere. It has this genus, G is equal to 0. Then there's the surface of the donut, G is equal to 1. Then there's the two-hole donut, G equals 2. Here's a pretzel with 3 holes, and so on. There's one surface for every G. G is the number of holes. And every surface is one of these, and these are all distinct surfaces. So that's a complete classification of these surfaces. Poincaré wanted a complete classification similar to this for higher dimensional spaces. But before I get to that, let me just try to emphasize the difference between topology and geometry. And there are several ways to think about this. First of all, in a topological space, these notions that Gauss and Riemann were talking about, distance, angle, area, size, volume, those have no meaning. These are geometric notions, they're not topological notions. What you're not allowed to do, so in topology you're allowed to move things around, stretch them out, deform them. What you're not allowed to do is cut the space or tear it, because that pulls apart the notion of closeness, and that's what topology is the notion of closeness. Any continuous deformation doesn't change the topology, though it can well change the underlying, well change the geometry if there is one. So I like to think of topological spaces as made out of something like rubber, that used to be a standard thing you would say, or taffy, something that can be pulled, stretched, but not torn, whereas geometric spaces are made out of a more rigid material, like steel or paper. Now, the modern perspective on all of this is one modern perspective, one starts with a topological space which may have extra structure, like a Riemannian metric, a way to measure distances of the lengths of tangent vectors, or a complex structure, or a symplectic structure, or lots of other structures that I haven't talked about that arise in geometric and physics questions. So we've concentrated on Riemannian geometry, which concerns topological spaces with the extra structure of Riemannian metric. And as I said, deformation doesn't change the topology, but can well change the geometry. So let's go back now to topology. And let's think about the difference between the topology of the two-sphere and Riemannian geometry on the two-sphere. So as long as the surface doesn't have any holes, it is a two-sphere topologically. But there's a huge number of Riemannian metrics, I say uncountably many. In fact, there's a multi-dimensional family, an infinite multi-dimensional family of Riemannian metrics. Or said another way, there are uncountably many essentially different Riemannian surfaces, all of whose underlying topological surface is the two-sphere. So these metrics could be round, elliptical, bumpy, like the surface of the Earth, but they're all on the topological two-sphere. And so this distinction between topology and, in this case, geometry can often be important. If you ask a geometer, you present a geometer with a geometric space, his first question is probably going to be, what's its topology? Not because that answers everything he wants to know about the space, but that tells him what context he's working in for his geometry. So he wants to know what the underlying topology is, and then on top of that, he'll try to understand more refined questions. So if we think about the actual Earth, and think about its geometry as a function of time, in fact, the geometry of the Earth changes. I'm thinking of the surface of the Earth changes. We have erosion from storms and wind. We have earthquakes and volcanoes that add to the surface, deform the surface. So the geometry is changing all the time, but the topology is the same. Another reason you want to know what the topological classification, where you are in the topological classification. That's a discrete classification, and then once you're in that, you can try to understand more about the geometry. And what I said about the two-sphere is true for all other surfaces, and indeed all higher dimensional spaces. There is one distinction between surfaces and higher dimensional spaces. Surfaces always come with a nicest metric, or given the topological type of the surface, there's a nicest metric that you can associate with it. In the case of the sphere, it would be the round one, and the other surfaces, well, of torus, it's a flat one, and in the higher genus surfaces, it's actually this Lobachevsky negatively curved metric. Higher dimensional topological spaces have huge families of metrics on them, Riemannian metrics on them, but in general, you can't pick out the nicest one. There isn't the nicest one, or even a small family of nicest ones. All right, let's go back to Poincaré's topological study. His idea, he wanted a classification of spaces of higher dimension analogous to the classification of surfaces. So he introduced, well, to some extent they were already around, he introduced algebraic invariance associated to topological surfaces. Invariant means that if you deform the surface but don't change its topology, you don't change this algebraic in a number or whatever it is. And a particular one that he was quite fond of and is very important is homology, which measures the number of holes in the space. When I was talking about surfaces, I was talking about one-dimensional holes you could wrap a loop around. Well, higher dimensional spaces may have one-dimensional holes, but they can have higher dimensional holes. Holes you can wrap a surface around. Holes you could wrap a three-sphere around, and so on. So you have holes in each dimension. The number of those holes is measured by homology, and one of the fundamental theorems about manifolds is so-called Poincaré duality, which in this formulation says, for example, a 6-manifold has the same number of 2-dimensional holes as it has 4-dimensional holes. Or a 7-manifold has the same number of 3-dimensional holes as 4-dimensional holes, and so on. Poincaré also introduced a group which the French still call the group de Poincaré, which is we call the fundamental group, which is made out of loops and is a more refined way to study the one-dimensional holes. So Poincaré wanted to use homology and his fundamental group, various ways of counting holes, and his hope was this would be enough to distinguish higher dimensional spaces if they were different. So the listing of higher dimensional spaces would be to list these number of holes they have in various dimensions in some way, and that would tell you what the space was of the topological equivalence. Well, he thought maybe that was biting off too much to try to do that all at once, so he said, okay, surfaces are understood. What's the next dimension? 3. Okay, in dimension 3, what's the simplest surface? The sphere. So let's start there. If you have a three-dimensional space, there's a typo, and it has no holes that you can wrap a loop around, then is it topologically equivalent to the three-sphere? He didn't actually formulate a conjecture, he just asked a question, but it was clear from context he thought the answer was yes. Well, he said, this is a very interesting question, but to investigate this question would take us too far afield. Indeed, it took us 100 years afield. And it turns out the answer is yes. We'll come to that. So, from this beginning, the importance of homology, Poincaré's duality, the fundamental group, this question of what higher dimensional spaces look like. The 20th century was devoted to these questions, and an incredible amount was learned. Many of these questions were generalized, answers to the generalized questions, partial answers were found from various perspectives, but Poincaré's original question remained throughout the entire century unanswered. In one of the twists of fate, in 1960, Steve Smale realized that there's an analog of Poincaré's question in every dimension, and if you just skipped over 3 and 4, which turned out to be problematic, he saw how to resolve his questions in dimensions 5 and higher, using exactly the sort of ideas Poincaré was suggesting one should use to answer the question in dimension 3. And indeed, going back to these Morse functions, which maybe Riemann had additive. Anyway, so he solved the analog of Poincaré's conjecture for the question for all spheres in all dimensions 5 and higher. Very counterintuitive, right? It's easier to study higher dimensional spaces than lower dimensional spaces that we have more chance of seeing. But Smale's techniques, and the ones that Poincaré was suggesting, did not work in dimensions 3 and 4 because there's not enough room to move things around. Well, after Smale's work in 1960, the next 15 years, over the next 15 years, a theory, just called surgery theory because you cut things out and sew them back in and so on, basically realized Poincaré's goal of classifying higher dimensional spaces in terms of algebraic topology. But it was far beyond anything Poincaré had in mind. In fact, in the technical sense, you can't classify these spaces. But much was learned. We learned exactly how much you could know and beautiful algebraic characterizations, characterizations in terms of algebraic topology. And interestingly enough, these characterizations involve higher dimensional generalizations of the Gauss-Bonnet theorem relating to curvature and topology in the guise of what are called characteristic classes, as introduced by Chern and Jay and Montreal. Well, if we think about Poincaré's question, this left dimension 3 and 4 unresolved. 5 and higher, Smale took care of in one fell swoop. In 1982, Mike Friedman established the 4-dimensional version of Poincaré's question by taking the higher dimensional techniques and managing just to squeeze them down into dimension 4. In fact, it can't be done smoothly or differentiably. It has to be done purely topologically. Nevertheless, that resolved Poincaré's question about spheres in all dimensions except the dimension in which he had originally posed it. Well, the nature of the answer in dimension 3 is very, well, the answer in dimension 3 is the same, yes. But the method of attack, or proof, is completely different from the higher dimensional techniques of Smale and Friedman's 4-dimensional proof. It uses geometry. So in the early 1980s, Richard Hamilton introduced a differential equation using the curvature to deform or evolve the Riemannian metric. So it's a partial differential equation. You start with an initial condition, a metric on one of these spaces. You deform that metric using its curvature. In fact, using its Ricci curvature, the same Ricci curvature that came up in the last hour. And not surprisingly, that equation is called the Ricci flow equation. You flow the metric using the Ricci curvature. Interestingly enough, this equation was also discovered at almost exactly the same time by the physicist Dan Friedan, because it's a naturally occurring flow in quantum field theory, a renormalization group flow. Okay. Well, in 2003, 98 years after Poincaré had formulated the conjecture, Grisha Perlman, using Hamilton's Ricci flow in exactly the way that Hamilton had imagined one should, Perlman showed that if you start with a topological three-dimensional space with no holes, that's the hypothesis of the Poincaré conjecture. We have a three-dimensional space with no holes. We take an arbitrary Riemannian metric on it, and we apply the Ricci flow equation from Hamilton. What happens? What happens is that manifold eventually begins to shrink. And it shrinks and shrinks and shrinks, and at some finite time, it shrinks to a point. But as it's shrinking, the metric is becoming rounder and rounder, which means, in fact, that this three-dimensional space with no holes has a round metric. And once it has a round metric, it's easy to see that it's the sphere. So the manifold has a homogeneous round metric, and therefore is topologically the three-sphere. Hence, our three-dimensional space with no holes, in the end, is topological equivalent to the three-sphere. And we saw that by starting with an arbitrary Riemannian metric and deforming it through this partial differential equation to find the good metric. In fact, Perlman extended his arguments to cover all three-dimensional spaces, and it turns out that they're all accounted for by homogeneous Riemannian metrics in dimension 3. So in dimension 2, there's a very tight connection between homogeneous metrics and surfaces. There's an analog, slightly weaker connection. I won't try to formulate it explicitly, but all three-dimensional spaces are accounted for by these homogeneous spaces, and that correspondence between topology and geometry breaks down in the higher dimensions. It's just nothing like this can be true in higher dimensions. Well, I'd like to be able to explain the Ricci flow equation to you. It's an incredibly beautiful equation. It's an incredibly powerful equation, but it's not easy to visualize, even for mathematicians. But there's an analogous equation which is much easier to think about, much easier to study, but has many of the same properties. It's called the curve shrinking equation. So we start with a curve. The one I started with is this one that mostly is on the outside. Here it is. And I've drawn at each point on the curve a normal vector to the curve, and the length of that normal vector is given is how the amount of curvature of this curve at the point, and it always points inward. So these points here, you see that the curve is curving in this direction, so the tangent vectors point up. Okay? You deform this curve via these tangent vectors. So this is the infinitesimal motion of this curve. Now, so what happens after a small amount of time? I've drawn, say, at time 1, what the deformed curve will look like. And then at time 2, and time 3, so on. What happens is, no matter what curve you start with, embedded curve you start with, in a finite amount of time, well, first of all, it eventually becomes convex. So we see a convex one here. And once it becomes convex, it then shrinks down, always staying convex, shrinks down to a point, and as it shrinks to a point, it gets rounder and rounder. So it's a partial differential equation, which structurally is very closely related to the Ricci flow equation, and which has this very analogous property of shrinking to a point and becoming round as you shrink. So that's my analog of the Ricci flow equation. If you get this picture of curves, then you have some idea of what Ricci flow is doing. just one last twist on this argument, Poincaré suggested that his equation should be attacked in purely topological terms. That's what Smale did in higher dimensions. That argument has never been successfully carried out in dimension 3. It just doesn't seem possible. Well, who knows, tomorrow somebody may do it. But these ideas of geometry, in particular non-Euclidean geometry, comes in as an essential piece of the solution, and that's related to Poincaré's work on Fuchsian and Kleinian groups. So I'm sure that while Poincaré might have been surprised that the direct attack didn't work, he would have been pleased to know that Kleinian groups had something to do with these. So I tried to describe some of the high points of geometry and topology over the last roughly 200 years. I've tried to give you a sense of the nature of each to explain their differences. I've tried to explain how both of these mathematical subjects are intimately tied up with modern-day theoretical physics. All of these are rich and vast topics, focus for researchers all over the world. Progress has been enormous. I think if Gauss and Riemann and Poincaré could see what we've achieved, they would be heartened. And indeed, the progress is only accelerating, and I'm sure it will continue to do so. None of us can see around the corner, but I'm sure we're going to learn amazing things, much of it related to physics. Thank you. I'm sorry, say again? The uniformization. Yes, yes. It did it using partial unitary. Yeah, exactly. And that's very much tied up with all this hyperbolic geometry that comes in. Right.
Is there any concern over the fact that the geodesic definition is sort of numerically unstable?
Not to me. Yes, well, right. I mean, it's a critical point of the Euler-Lagrange equation. So it's going to have. I mean, there's no force pushing you back. And that's always true of these. Right. Anything that's a variational comes from a variations problem.
Okay, well, let's thank our speaker. Do you have any other items you need here on the stage?
No, it's just mine.
Okay, great.
Manuscripts. And this is the handout for at the end. No, that's fine. There we go. Thanks. All perfect.
Okay. Well, let's welcome our guest speaker again.
Okay. It's wonderful to be here. Thanks for the invitation. I had to sort of run the Euler lecture in Berlin yesterday. That's why I could come only today. So I even more appreciate David and Gregory run this wonderful Dürer colloquium here, of which I missed the first half, unfortunately. But I think we shouldn't forget to have a round of applause for the two of them for putting this together and for everybody who is involved in that. I should perhaps start with a word of caution. If I'm invited here to talk about Dürer, then I should perhaps first say that I'm not a Dürer expert and I have not studied the Melancholia for the length of my time. And somehow I got drawn into this being asked. But there's some reasons I feel why I should actually talk about Dürer, and I should talk about the Melancholia. Of course, being asked by David and Gregory is a good reason. There's a few others. So this is this piece again. I'm sure you've seen it a few times, and there's various other renditions of this around. One of the reasons why I should talk about that is because I'm German. And growing up German in my generation, in my wallet, of course, I would have Dürer, like perhaps in this form. This may be a little too small for you to see, but this is 5 marks, 1970s, with this beautiful woman on it. And I don't think we know her name, but she's a young woman from Venice, painted in 1505 by Albrecht Dürer. And this means various things. This means I'm deeply connected to Dürer already that way, as all Germans of my generation are. I'm also very much connected to telling stories in images. I'm a geometer, perhaps a different kind than the ones you've just had on the stage, but I think we should think and even communicate mathematics in images, so this will be an image lecture. Actually, I just recently did a book called, which you could translate like Mathematics That Can't Be Art, or Mathematics There's Nothing to It, so the German title is a bit ambiguous, intentionally so. But also, I'm a geometer, and people know me for my work on polytopes, and here's just a little polytope that appears in a paper I'm very proud of with Alexander Schwarz, a student of mine a bunch of years ago. It's not a Dürer polyhedron, of course, but it is a polyhedron. And this means I will be talking about polyhedra and Dürer and the Melancholia from the polyhedron theorist's perspective, at least for a part. So here's the plan for today. The title of my lecture was supposed to be 3 Giants, 5 Stars, Some Mistakes. And I'm supposed to talk about Leonardo, Dürer, and Kepler. So the 3 stars, of course, or the 3 giants are Leonardo, Dürer, and Kepler. And since mathematicians can't count, I also brought Gauss along. The 5 stars you will see in the course of my lecture. And there will be lots of mistakes in there, and we'll have actually fun in pointing out some of them, and from some of them you can actually learn a lot. So that's the plan. We'll start with Leonardo, then there will be several sections on Dürer and Melancholia. I have to tell you about the Great German Revolution of 1522, 1525. You may not have learned about it because it's not in the history books yet, which is a big mistake. Then we'll get to Kepler and to Gauss, and this will span the last 500 years because my Gauss story ends in 2011, actually on December 4, 2011 to be precise. Let's start with this. We start with this painting. And so I start with, in this part number 1, with a polyhedron, which is still a different one. Not the one I just showed you, and also not the Melancholia one. This is a painting, a well-known painting, so well-known to all the art historians who know it well, showing a well-known mathematician, well-known to all of those who know him well, Luca Pacioli. Actually, the economists know him well. Luca Pacioli was, as you can see here, a Franciscan monk who was also a mathematician. He was traveling Italy in times where this was difficult and dangerous, teaching at basically all the universities Italy had at the time. This is a portrait that shows him in the year 1495, so we are a few years before the Melancholia. And now we could point out a lot of different things already from this portrait, which makes it very interesting. So the portrait is due to Jacopo de Barbari, a Venetian painter with German roots. Actually, it is signed somewhere in the corner, that's why we know it. Also the year is clear. It shows Luca Pacioli pointing out things by Euclid. You can't see this very well, but this is basically the first printed edition of Euclid, and we can even identify what's on there, and also this drawing. Here it says Euclides on the wood here, and there's various models around. Then there's a dodecahedron on top of this very fat book. And there's only one possibility what this book is, namely it's Luca Pacioli's his own book, the first book he wrote, published in 1494, called Summa, and that contained the sum of all the mathematics known at the time, basically. And the reason why the economists know him is because it contained the first sort of textbook treatment, complete treatment of what was known as the Venetian method, which is double entry bookkeeping. What we do even now still, and that's why the economists know Luca Pacioli. Now, who is that young man in the back here? Apparently the books say that this is the Duke Guidobaldo de Montefeltro, who was a huge benefactor to everybody at the time. Nick McKinnon, who wrote a very interesting paper about this painting, claims that this is not Guidobaldo de Montefeltro, but it is actually Albrecht Dürer. And he gives various indications why this could be plausible and should be plausible. There's some indication even in the looks. I mean, Dürer had ginger hair, and there's various characteristics that fit. On the other hand, it doesn't really quite seem plausible that this is Dürer, because Dürer and Pacioli met only later than this painting was done, so Dürer would have been added later, and we're not so clear. Nick McKinnon also claims that the only person who could have painted this glass polyhedron here in this masterful way would be a math student that Luca Pacioli had as a friend and flatmate at the time. And this math student, who wasn't very good at math, he was close to 50 and was learning the basics of Euclidean geometry and that sort of stuff, is someone you still know. It's Leonardo da Vinci. So this must have been a quite interesting apartment with this Franciscan monk. Leonardo was 7 years later. There was a young boy who was helping Leonardo with the paintings and whatever was the story there. We don't know. But this glass polyhedron is interesting. It's called the Rhombocube. Oops, I always get this one wrong. Rhombocube. Thanks. Rhombocube octahedron. The name was known at the time because Kepler was the one who named these things more than 100 years later. How do we, I imagine this thing in the following way. You start with a cube. That's the only one, so that's really easy to imagine. You shave off all the edges. So there's 12 edges, so you cut off all these edges. And then you also cut off the vertices of the original cube. And what's left at the original vertices is triangles. So you see a triangle here. The next triangle is over there. There's a triangle over here. That's hard to see because of the reflection. And the next one then is down here, and so on. So McKinnon said the only one who could paint this so masterfully with all the reflections at the time was Leonardo. We don't know that. I think actually someone should really do a very serious study of this painting and all of its elements, and based on McKinnon's paper, this would be fascinating and we would learn a lot from that. There's other people who say that this rendition of the Rhombocube octahedron is actually awful because all the reflections are wrong. We don't know. It's presumably painted from a model. They did have glass models at the time, but none of them survived, so this is rather hard to tell. Sort of for comparison, this is Porphyry, the same thing, computer graphics, modern times. So the perspective isn't really that bad, but we can also see, even in this lighting, that this is not quite the same on the left and the right. So there's quite some difference. Okay, the Rhombocube octahedron. I want you to recognize this, and I brought you basically 3 pictures of that polyhedron, because it's a fascinating polyhedron. Here's the next rendition of the same thing, and this is now from Luca Pacioli's second book and next book, called Divina Proporzione. He finished the manuscript in 1498, and the drawings for all the plates in the back, even for the manuscript, were done by Leonardo himself for his math teacher. And so this is a masterpiece by Leonardo, who was not only an amazing artist, but was also very interested in geometry, at least, and necessarily so. And this is one of his pieces. Actually, it may well be that Leonardo was the one who invented this sort of framework view of polyhedra, so you could draw them so you see what's inside. Apparently, Pacioli invented these starred or stellated polyhedra, where you take this sort of thing and then you put a pyramid over each of the faces. So this is the stellated cube, Rhombocube octahedron, in, again, a masterful version by Leonardo, which is also interesting because it has a major mistake in there, which was discovered only rather recently by a Dutch sculptor, Rinus Roelofs, who noticed the following. So this is the same thing, but now with these red corners here. That's everywhere where you expect a pyramid over a triangle. And here we see that, and here we see that, and here we see that. You might also notice that this is basically the same perspective on this thing as we had in the glass model before. So there is some correspondence between this painting and then this later rendition. But if we look at this closely, then we see that down here, Leonardo got it wrong. He should have had a pyramid over a triangle, but clearly he did a pyramid over a quadrilateral. So it's not only the perspective isn't quite right, but really the combinatorics is wrong. So we caught Leonardo at a mistake, which of course is wonderful and doesn't make him less of a genius, definitely. I don't know whether you've seen this polyhedron before. Everybody, of course, should know the classics. But also, since I come from Germany, there's this company in Herrnhut in Saxony, where for many years this is again the computer graphics corrected version of Leonardo, and then you get the choice if you can have a Leonardo original or a modern computer graphics, which end you want to take. This is these Christmas stars, which are sold from Herrnhut in Saxony, and so popular all over the world. They export a lot of them, certainly in the US and also up to Japan. If you look at it, it's again this polyhedron that Pacioli invented and Leonardo painted, the rhombocuboc-octahedron with pyramids erected over the faces. So there's 8 pyramids over triangles. That's the smaller ones, like this one here. And then there should be 6 plus 12 is 18 of the bigger ones, sort of pyramids over squares, but here there are only 17 because one is missing. That's where we have the cord for the light bulb in there. That's the modern times version of these things. I showed you this mistake by Leonardo, which of course is deplorable. Other people say, no, Leonardo can't have made a mistake. It was certainly intentional. He wanted to fool Pacioli, or sometimes he did mistakes in this thing so people couldn't copy it. Whatever. The same mistake you find in the engraving version of that published a few years later, when the book was eventually printed. Anyway, this is sort of the modern day version, and before we criticize Leonardo for little mistakes in his drawing, this is the logo of the company who sells the stars. And if you now look at, you can call this artistic freedom, but if you look at it as an expertise in drawing geometric figures, which actually they sell for a lot of money, then we can see that actually things have deteriorated since 1498. And we'll have a few more indications about that. So, okay. Remember the rhombic cube octahedron, it will come back. And that's the end of part 1 of my lecture. And we should go to Dürer's polyhedron. Dürer's polyhedron, of course, is the one in the Melancholia, very prominently in there. And I've learned also, since my lecture here was announced, I got phone calls from several people from all over Germany who apparently for many, many years have been studying this engraving and have tried to figure out the symbolism. And there is dozens of papers published about trying to interpret these things. Many of these interpretations I find very interesting, and many of them I also find convincing, but they also contradict each other wildly in various ways, starting out with the title of this object. So it does stay interesting. And the situation, if I look in this, is like a bit like in the Dire Straits song for people from my generation, where they say from Speaker's Corner, there's 2 men who say they're Jesus, so one of them must be wrong. Okay, let's go into interpretations. So here's the polyhedron, the Dürer polyhedron, and I just wanted to show you 5 theories of what this is and why this polyhedron. First, let me mention that this is very interesting. First, the polyhedron that Dürer chose, because it's not what we see all over that time, basically up to Euler, namely uniform polyhedron. This polyhedron has really different types of vertices. It has these vertices which are in a triangle here, and there's the 3 vertices in the triangle down here that you can't see at all, because that's what the thing stands on. And then there's these vertices which are not in triangles, but they're only in pentagons. Right? So this is not what they call an Archimedean solid. We will get there. So already for that reason, it's interesting. So here again is my way of describing and imagining this polyhedron. You take a cube. Again, the cube is the only one we can imagine without having a graphics. You put it on a tip, sort of put it upright. Then you stretch it up there, and then you cut off the top and the bottom. Then you get this. At least that's one way to get it. You might argue that we don't know that the bottom is cut off. It might also just be sticking somewhere in the ground there, but actually it isn't. That's one thing we can prove. But here's theory number one. Theory one says that this is a crystal you find in nature called calcite or calcspar. This is a graph from an atlas of crystal forms from 1913, 100 years ago, which lists this as calcite number 17, so it is a crystal form. Theory number one. Actually, that's a theory I learned via Brieskon and Hilzebor. People have been looking at that, also German mathematicians. Here's theory number two, and that's something you can see. So this is a manuscript page from Dürer's manuscript books, which lies in the city library in Nuremberg. And I asked him to make this photo for me because there was only a bad photo in the literature, so this is a better one. And what you find there is his drawings of various polyhedra, and the theory was that this one here shows the face of the Melancholia polyhedron, and one thing you can learn from that, it seems important that all the vertices lie on a circle. There's a further theory which says that these 5 vertices are a subset of the 10 vertices of a regular tendon. From that you can calculate what the angles are, and that's the 72 degrees that come up here. There's another paper which says that it has to be 79 degrees, and so on. So various theories around, but theory number 2 says this construction of you stretch the cube and cut off the top and the bottom is done in such a way that in the end all vertices lie on a sphere. So it should be an inscribed polyhedron, which is not clear from the Melancholia, but there is a ball in the lower left corner of the copper engraving. So inscribed polyhedra in some sense were interesting, but they were studied in the middle of the 19th century systematically. So here's what you find on the lower right corner of the same manuscript page. This is drawings of other Archimedean solids. So Archimedean solids are polyhedra which are put together from regular triangles, squares, pentagons, and so on. In such a way that they have the same structure at every vertex. And this is Dürer doing some of these. Theory number 2. Theory number 3. This is something I learned from a paper of someone called Hideko, published in 2009. And his claim was that the stretching factor that Dürer did to pull out the polyhedron and then the cube and then cut it off is the stretching factor that you need for the daily problem of doubling the cube. It's the cube root of 2. And apparently the numbers somehow roughly figure out, and this daily problem was something that Dürer was interested in. So it's not completely implausible, but you don't have to believe it. Anyway, here is a drawing that is in Hideko's paper, and again I got myself a better copy of this. And this is Dürer drawing clearly his polyhedron, and you also see it is cut off on the bottom and lies on the plate. And very clearly this is a drawing towards the Melancholia, which somehow shows the construction of the object. Interestingly enough, for example, the vertices are labeled and a few things like that. If you compare it with the drawing in the copper engraving, you might notice it's not the same polyhedron, or at least not the same drawing of it. It's a mirror image, right? The sides are reversed. I don't know whether that's intentional, because that's what he wanted to have in the engraving, or whether this sort of going from the sketch to the copper engraving is a process where reversed sides are reversed. So things are possible. We'll see other things also where the sides are reversed in this drawing. Next theory, number 4, I learned from Ernst Theodor Meyer, and he's told me he would be coming. Well, very nice. You also made it from Munich, who has written about the Melancholia and brought various theories, and this is from one of the things that he has also to be found in the internet, which explains that this polyhedron, if you take it, has interesting projections. If you project it down, you find this drawing, which basically contains the Star of David in there, even in roughly the right colors. If you project it in the other direction, you find vertices that fit on a square grid. And so there might actually be a connection between the geometry of the polyhedron and the geometry of the magic square in there. Not proven, but possible, hard to prove. Someone would have to systematically work through all the, not only the published but also the unpublished papers and notebooks by Dürer that lie, some of them in Dresden, some of them in Nuremberg and so on, whatever we know there. What I also learned from Dr. Meyer is that in the Freemason community there has been huge studies, and they are very fond of, in particular, this Melancholia, which has lots of symbolism which you can at least associate with Freemason traditions. Again, it's something we won't discuss in detail here, and certainly I wouldn't be competent to do that, but it's certainly interesting. Theory number 5, if we talk about speculative theories, is something, I don't have a picture here, an image, although that might have been interesting, and it's one I learned from George Hart, who, if he isn't here, you should at least know him here in New York. He's a sculptor, a mathematician, and he was one of the people who did the Museum of Mathematics design and contents. And I quote George Hart, "One might speculate that the cube represents masculinity, and truncating one in an upright position may have some Freudian symbolism." I think it's an interesting interpretation. So if you think of that, well, in this context, as I learned from Dr. Meyer, you can interpret some of the Melancholia as being connected with the regular 17 gone, which would be Gauss, and which is somehow 300 years earlier. So if Dürer managed to get Freudian symbolism in there, then he was 400 years earlier. So you see, Dürer was ahead of his time. Okay. We stay with Dürer a bit, but I now have to tell you about the Great German Revolution of 1522, 1525, which should still be a model for how revolutions should work. This is a revolution which consists, it was entirely peaceful, at least in the beginning, as some revolutions, and it consists in the publication of 3 amazingly important books. And the first of these books was this one, title page from a later printing, 1522. Adam Ries, who is a calculation master, publishes his little Rechenbüchlein. This was a little book of teaching the Germans how to calculate. Now, I could say more about these computation masters. This was a profession at the time on the market. To do your trade, you had to compute things correctly, so what things would cost, and you would get a computation master to do that for you, because people didn't know their arithmetic themselves. And with this little book, published 1522, had some 100 printings, and during Adam Ries's lifetime, and 120 printings altogether. That's how the Germans learned how to compute, how to do calculations. So what you need on the market in math: basic arithmetic, interest, the rule of 3, And that sort of things they could learn from that book in German. And perhaps that's why it was so successful. And I think the economic power of Germany in the 16th, 17th century, in some sense, started with this book, so it was influential. The second book of the Great German Revolution from the same year, 1522, is known as the September Testament. It was the first part of the Bible in German by Martin Luther. Very influential, also led to war later. There's not much math in there. So the only thing I brought for you is a wonderful quote, usually attributed to Luther, which, this is old German, so I translate for you. It says, medicine, says Luther, makes people sick, mathematics makes them sad, and theology makes them sinful. You laugh at the sinful, but our topic today, of course, is why mathematics would make them sad, right? And we can discuss that later. So much for Luther. And the third book of the Great German Revolution was published in 1525, and it was this one. This is, again, so this is the title page. Here it is a bit larger, so you can read it. Again, it's ancient German. It's called Unterweisung der Messung mit dem Zirkel und Richtscheit. So this is teaching the measurements with compass and ruler. And was published in 1525, as you can read here, by Albrecht Dürer, who taught the Germans, and in particular, not only the painters, but also the architects, how to do geometry correctly. And there's exercises in there, for example, for how you have to do inscriptions on a wall if you want that people see all the lines in the same height. So there's an inverse tangent function in there, again, a bit early. But Dürer draws it. But I wanted to sort of get the second topic of my lecture besides the polyhedron on this occasion. So Dürer does classical geometry. He says, you know, if you know your Euclid, you can skip the first two chapters. He's teaching Euclid, whom he has learned perhaps from Pacioli even. He teaches classical Greek mathematics, which included the conics. Things like you can get the ellipse and hyperbola and parabola by cutting a cone. And this is Dürer's drawing. And you see here the circular cone. This is a view from the top. And if you cut this by a plane which is not horizontal, then you get an ellipse. Classical construction. Now the question is, do you like the ellipse? Now we all know that an ellipse has two symmetry axes. This one more looks like an egg, actually. Indeed, Dürer calls it the egg line, and he may have had the impression that an ellipse should have a sort of an egg of larger curvature and of smaller curvature. So a bit of curvature flow is missing there. So this is a construction of an ellipse which is approximate. It's not bad, but it's not correct. On the other hand, several things. One is Dürer did know the difference between an approximate and an exact construction. And he calls this approximative. The approximate constructions he calls mechanische, and the exact ones he calls demonstrative, so he knows the difference. And this is clearly an approximate drawing. For example, it does give a very good approximate construction for the trisection of an angle in the same book, so there's a lot of mathematics in there. On the other hand, if we criticize this drawing of an ellipse, and I just skipped the ellipses in the drawings of the lecture before, then I can switch to first Dürer and some faults in that. And then we can go to more ellipses of Dürer, where you might see that up here actually this ellipse has a similar fault perhaps, and the same here in the scales. And actually there's more ellipses in the painting. This here is at the left in the etching. And approximately right, but there might have been really a misconception about this egg. On the other hand, if we say this was the status of knowledge and of craftsmanship and of understanding of these things in 1525, what progress have we made until 1985, where this is published in the Fat Handbook of Applicable Mathematics, edited by Lederman, Wiley, where this intersection of a cone and to get an ellipse is so amazingly wrong. So this would have been my correction of how this perhaps should have been, that we say, please, before you criticize Dürer, look at how we are doing ourselves. I would say this is a shame. If you want to have more of this fun, go and get this volume from the library, the Geometry Volume Handbook of Applicable Mathematics. Has lots of pictures of similar quality and qualities. Okay, so much for the Great German Revolution. So this was Dürer's book, English title, A Painter's Manual. So he was teaching craftsmanship of his time. From this book, we owe Dürer one more thing, one thing he apparently invented and a great problem he posed, which is still an unsolved problem, older than Poincaré's problem and still not solved, for example, namely the unfolding problem. What Dürer does in this book from 1525, so this is 11 years after the Melancholia, is he explains all the regular and Archimedean solids, where some of them you also find in Pacioli's book, others you find in Dürer's book. It's not the same collection of solids. And he gives drawings, starting out with the regular solids. And in this section, I actually brought you 5 nets of Dürer polyhedra. And this is the first one. Of course, you recognize, I don't know whether you would recognize the icosahedron from this here. You surely recognize the icosahedron from this one here. Although if you compare these two views, then again you can find out that this is masterfully done, but it's not quite correct. Because if you look at D and F here, they're not quite on the outside here, and so actually if the drawing was quite correct, they would not, this vertex would not be on the circumsphere. So one can criticize Dürer a bit for this drawing of the icosahedron. On the other hand, who are we to do that? If you look at the logo of the Mathematical Association of America, in the version that you find on the publications of the MAA, between 1972 to 1984, so for 12 years, until Branko-Grünbaum, University of Washington, noticed that this is a badly wrong rendition of the regular icosahedron in the logo of the MAA. When he discovered that, they corrected it. And just to show you what's going on here, these 3 lines should be parallel, really. And in the corrected logo, yes, they are. And in the first one, no, they are not. So again, why should we criticize Dürer for his drawings? Here's another one, Dürer's nets. So Dürer apparently invented this way of presenting a polyhedron as a fold-out model. That's what we call a net. And the problem that's around since Dürer's time is the question whether you can take any polyhedron and cut it along edges in such a way that you get a fold-out paper model. It's not so clear. This is a very interesting polyhedron. Also because it's not an Archimedean one. Dürer notices, for example, so what is this? This is something that if you build it together, it looks like a cube, actually like a die, which is rounded off at the vertices. And the vertices have been cut off in such a way that there's, at each of the 8 vertices of the cube, there's a regular triangle, but then there's also 3 more triangles. Dürer notices that this is not regular triangles in there, and writes so. He says, Sie haben aber nicht all gleich Seiten, so they do not have all 3 equal sides. You might still notice that again this net is not quite correct. So what happened here at this vertex, for example, and it hasn't been cut and it's still flat in the plane. So what we learned, for example, from John Morgan's lecture or from Gauss or so is that that shouldn't happen. So it's not quite accurate, but it presents you what's going on in a very plausible way. Here's another one, again from Dürer's book. You remember this polyhedron? So that's the rhombocube octahedron in a very nice net. You might notice that there's of course many different ways to create the net depending on which edges you cut. And this is one of them. This unfolding problem by Dürer has inspired a lot of research in recent 20 years. It's still unsolved. Fukuda noticed in the early 90s that you can even unfold a tetrahedron in such a way that it overlaps in the plane. So that's Fukuda's tetrahedron. So it's not so clear how we have to cut open to not get overlaps. This here is images from a major study that a student of mine did in the mid-90s, Wolfram Schlickenrieder, with just also examples of polyhedra and how they overlap. And he studied basically all the ideas that Wolfram and I had at the time for rules that tell you how to unfold polyhedra. And he could prove that none of these rules works for all examples that we had. But for each of the examples, he could construct one of the rules would work. So problem is still open. So this shows you that he also studied some more complicated polyhedra. So this is a random polyhedron given by vertices on the sphere, and down here it overlaps. So this is not a correct net for this polyhedron. You don't want to exercise to find a correct net for this one. Here is another one. Actually, this is Dürer, although it's not in the book from 1525, but it's only in a later edition using drawings from his Nachlass, his leftover papers. And this one, of course, is again a polyhedron that you know very well, because it's the classic design of a soccer ball, actually. Interestingly enough, Dürer, he gives very little data for his polyhedra. He just tells you basically what modern days we would call the F factor. He says how many vertices and how many edges and how many faces it has. For this one, he says it has 62 vertices, where you might calculate in the end that that's not the correct answer. So Dürer made little mistakes with his arithmetic at certain points as well. And this is the 5th one of the Dürer polyhedra I brought for you. Actually, that's a net that apparently you find nowhere in his writings. So I generated it for you. But this is the 72-degree version of one net for the polyhedron as a fold-out version. So much for Dürer's unfolding problem. There's recent work by Ezra Miller and Igor Pak. There's recent work by Mohamed Gomi. If you look at it, it's an exciting problem in discrete geometry, and it's still not solved. We are waiting for new ideas. Section number 4 of my lecture, and I'll speed up a bit since we're getting into the evening. So now this is time shift, basically another 100 years after Pacioli and then Dürer. Kepler amazingly really tried to explain the world with regular polyhedra, which is quite amazing. And he meant that quite literally. This is Johannes Kepler, a German mathematician from Württemberg, who also on the side dabbled as an astronomer. And the main thing I want to show you today is sort of three of the major discoveries, mathematical discoveries of Kepler. But of course we start with his astronomical discoveries and what's the timeline, which basically comes from three books he did. The first one, 1596, Mysterium Cosmographicum, the cosmographic mystery, which basically in the whole book explains this theory which says that the 6 planets are on orbits whose radii are given that in between the planet spheres fit the regular polyhedra. So it's a theory that somehow didn't make it quite to modern day, but Kepler came up with that with 1596 and defended it quite vigorously. And he thought he had sort of solved the riddle how the proportions should work between the planets. He had various explanations why the polyhedra come in the order that they come. So the order is in the inside you have Mercury, around Mercury you have the octahedron, then comes Venus, then comes the icosahedron, then comes Earth, then comes the dodecahedron, then comes Mars, the tetrahedron, then Jupiter, and then the hexahedron, the cube, and then Saturn. That's all the planets. He also mentions on the side in a later book that there could be further planets. He also notices that the radii and his computations don't quite fit together with the astronomical data, but he felt that it fitted so nicely that it was really convincing evidence. He argues through the whole book. It's interesting reading. I have it here, German version. That was my plain reading. Next book, 1609. That's the one which has the first two of the Kepler laws, celebrated by this German stamp from 2009. Again, I would invite you to study the ellipses and see whether they are convincing or not. And then 1619, his third book, Astronomia Nova, the New Astronomy. And this also contains the third Kepler law, but in particular it contains a lot of exciting mathematics. And here is sort of three math pieces that we learn from Kepler. Before we go to the math, this is again a drawing from this book, so even 20 years later he was still explaining this theory that the regular polyhedra give you the distances between the planetary orbits. At that time he knew the data didn't quite fit that, but he also knew that the planets were not on circles but on ellipses. We are back to the ellipses again. And that means there's sort of a large radius and a small one in each ellipse, and these distances given by the Platonic solids are somewhere between the small and the large ones. So he says it fits very, very well. Anyway, Discovery 1 from Kepler's book from Astronomia Nova 1619. So this is a plate from the back which somehow collects all sorts of things that are in there, including this interpretation of the Platonic solids to be connected with earth, fire, air, and so on. The first discovery that goes to Kepler is today known as the Kepler star polyhedra, at least 2 of the 4 that exist. This is modern computer graphic versions, amazing objects that Kepler discovered. Although actually if you go into art history you can find them 100 years earlier in St. Moritz in Venice, but still this is the Kepler Poisson polyhedra, the 2 that Kepler discovered. That's discovery number 1, and he was going for star polyhedra, rather than just the usual one. So we wanted to collect stars in this lecture, right? Here's two. Second discovery is that he discovered, in some sense, the duality between the polyhedra and exemplifies that in the book in the Platonic solids with, again, a very interesting interpretation. He describes this, if you can see some of the Latin words there, as conjugia, a marriage between these various polyhedra. The male ones are the ones that have more vertices than faces, and the female ones are the ones where it's the other way around. The tetrahedron is androgynous for the same reason. So this is Kepler's interpretation of this marriage between various of the Platonic solids. We don't have to buy the interpretation, but the insight in this duality, of course, is amazing. And the third thing that Kepler did in this book is not only he gave the names to all these Archimedean solids, but he completed the classification and proved they were all of them. And so the Platonic and the uniform polyhedra is basically, it's the Platonic solids, it's the prisms and antiprisms, and then there's 13 pieces, and here are the 13 ones. The drawings are not quite perfect, but the combinatorics is right. And here in there again is number 10, the rhombocube octahedron. So much for Kepler, so we are in 1600. And the rest of my story I want to do rather quickly, but so Kepler was around 1600. Now we go 200 years to arrive with Gauss. Now again, being German, I know Gauss from my wallet because later, this is before we got the euro, everybody would have these 10 marks bill in their wallet showing Gauss. A beautiful bill, which has all kinds of symbols on there. For example, here you find the bell-shaped Gauss normal distribution. There's also Gauss measurement thing somewhere on the bill and so on. You might also notice that there's something wrong with the portrait, at least if you compare it with the original. You see that, again, this is a mirror image of what it should have been, but apparently on a bill, people always have to look to the left. Well, perhaps I could check with the dollar bills. Never mind. So this is Gauss, the great geometer. And perhaps we should remind ourselves what Gauss got famous for when he got famous. Well, he did the 17 one as a young, basically nearly a high school student. But the thing that really made him famous was not his number theory book from 1801, which people didn't understand at the time anyway. But it was the construction of these ellipses which led to the rediscovery of Ceres, one of the planetoids, which had been discovered in the sky early in 1801, and then they lost it again after 2 weeks of observations because the guy who had found it got sick, and then they didn't find it again, and Gauss calculated and told them where to look in the sky, and that's where they found it, and that's what made Gauss famous as a 24-year-old in 1801. So this may be hard to see, but here in the upper left of the figure, you see Ceres wiedergefunden von Zach. So Ceres found again by Zach on December 7, 1801. Actually, this was drawn a few years later, where Gauss sort of recorded all of his drawings and computations in planetoid orbits and so on. That's also the time where he claimed that he had used the method and developed the method of least squares to do these computations. It's not so clear, has to be checked. Anyway, there's a few more ellipses for you to check for whether you like them. They are far enough away from circles to really see that they are not circles. This, after all, is at least Gauss's handwriting. not an artist, but a really great mathematician. This is 1801. If from there we want to sort of jump directly into the present, then this is 4th of December 2011, a protest demonstration on Bolotnaya Square in Moscow, very close to the Kremlin. And this poster, if you can read it, in Russian says, "We don't believe in Churov, we believe in Gauss." So you can realize Gauss is alive. Churov is the head of the State Election Commission, and this protest demonstration was 4 days after the elections. And you see people trust in Gauss, and they show this graph, which is supposed to prove that things are so far away from Gauss normal distributions that it has to be forged. I could tell you quite a lot about that, but it's off topic for my lecture about Dürer for today. So details about that actually are in the book about mathematics, images, and about art. I should rather end my lecture on the one hand by saying thanks also to people who support me and also my studies in geometry. In this case, this is the Collaborative Research Center Discretization and Geometry and Dynamics, where this is the logo DGD, and the German Science Foundation. And on the other hand, I felt I should bring you something, so to speak, some Dürer to take home with. And the Dürer to take home with, of course, is the Melancholia polyhedron, which as a fold-out paper model with the logo of the German Math Society with greetings from Germany, looks like this. And I don't only have this as a poster up here, but actually here is the cardboard from the Lufthansa hand luggage, sort of one for each of you, sort of, and I start with Herr Meyer, and you just hand them around. So for those of you like me who haven't been here this morning, this is the movie again, without the sound that goes with it, that was finished yesterday. So this is world premiere Melancholia in 3D. It runs a bit. Runs too quickly. We'll put it on YouTube, yes. It runs too quickly here. It's not on there yet. We'll put it there. It was finished yesterday, and we don't have the low resolution version yet.